Hi everyone, and welcome to our exciting new course on iOS 18 programming for beginners. In this course, you'll embark on a journey into the world of app development using Swift and Xcode, gaining crucial skills like building user interfaces, managing data, and coding functionalities. Expect hands-on coding exercises to supercharge your learning and keep things engaging. And, oh, don't forget to check out the link in the description for access to the GitHub repository where you'll find all the code and resources you'll need. Make sure to stick around till the end where you'll work on a final project to showcase your newfound skills. So, let's dive in and get started. Downloading and installing Xcode is the foundational step for any aspiring iOS developer. With Xcode, you gain access to the tools and resources needed to build amazing applications. So, let's dive right into the process of downloading and installing this powerful integrated development environment. First, head over to the Apple developer website. You'll find the latest version of Xcode available for download. Click the Download button. It's as simple as that. Just a heads up, depending on your internet speed, this might take a bit, so be patient. Once it's downloaded, locate the file, which will typically be in your Downloads folder. When you find it, double-click to begin the installation process. A window will pop up, and you'll want to drag the Xcode icon to your Applications folder. That's the key part. After that, it'll start copying, and voila! You now have Xcode installed. Next, go ahead and open Xcode. On your first launch, it might take a moment to set things up, so give it a second. Once it opens, you'll be greeted by a welcome screen. Here, you can create a new project or explore sample projects Apple provides. Friendly tone. Don't forget to check out the documentation. It's really helpful for getting familiar with all the features available to you. And there you have it. You're all set to start exploring the world of iOS app development. Now, let's get into creating your first app in the upcoming sessions. First things first, let's head over to the Mac App Store. Just click on the Apple icon in the top left corner of your screen and select App Store from the drop-down menu. If you're already familiar with the App Store, this part should feel like second nature. Once the App Store is open, just use the search bar and type in Xcode. You'll see it pop up in the results. Now, here's where the magic begins. Hit that Get button or the Install button if you see it available for download. This will kick off the download process, and you'll be well on your way to having Xcode on your machine. When Xcode starts downloading, enjoy this brief intermission. Depending on your internet speed, it could take anywhere from a few seconds to a few minutes. Don't worry, it's worth it. Xcode is a hefty application packed with everything you need to develop apps for all of Apple's platforms, including iOS, macOS, watchOS, and tvOS. Its powerful features and robust interface make it a vital tool in your developer arsenal. The figure titled Time to Complete Steps for Downloading and Installing Xcode presents a bar chart that illustrates the sequence of 7 key steps along with the minutes typically required for each. So, along the x-axis, we have the ordered steps: download Xcode, install Xcode, agree to license, run first app, explore Xcode UI, run in simulator, and finally, run on device. The y-axis shows time in minutes, with each bar clearly annotated by its integer value. Now, looking at these bars, a clear pattern emerges. The longest step is Run First App, clocking in at 15 minutes. This suggests that the initial project build and configuration can really take up a lot of time. Following that, Run on Device takes about 12 minutes, and we have 2 steps tied at 10 minutes each: Install Xcode and Run in Simulator. This really underlines how significant setup and environment execution can be as time sinks, right? Then we see Explore Xcode UI chilling at a mid-range 8 minutes, while the quickest step, surprisingly, is Agree to License, taking just 2 minutes. Yeah, that's quite fast. And the initial Download Xcode shows a modest 5 minutes. So, what does this distribution suggest? Although downloading is relatively quick, the installation and first run activities demand increasingly more time. Therefore, when you're planning your first setup session, make sure to allocate way more time for installation, as well as those simulator or device runs, and also for getting that first app to build and appear successfully. Taken together, these values illustrate a cumulative effort that's heavily front-loaded around setup and the first run, reinforcing the important lesson that patience during this crucial configuration stage can really lead to a smoother development workflow later on. Once the download is complete, the installation will start automatically, and you'll see a progress bar indicating how things are moving along. When it finishes, you can find Xcode in your Applications folder or easily access it using Spotlight. Just press Command plus space and type Xcode. Now, you might be thinking, great, I'm done, but hold on, there's a little setup involved. The first time you launch Xcode, you'll likely have to agree to a license agreement, so just read through it, and if you're okay with the terms, click Agree. This step is pretty crucial for using any development tools from Apple. Also, Xcode might prompt you to install some additional components. Definitely go ahead and let it do its thing. It'll only take a few moments, and trust me, these components are essential for running the application smoothly. Now that you have Xcode installed, let's take a minute to explore its interface. When you first launch Xcode, you'll be greeted by a welcome window offering several options. Create a new Xcode project, check for updates, or open a recent project. Creating a new project is where the fun begins. Click on Create a new Xcode project. You'll see a prompt asking you to choose a template for your project. Depending on what you want to create, you might select App under the iOS tab. These templates serve as your starting point for different types of applications. For example, if you're creating a simple single-view application, the app template will totally do the trick. After selecting the app template, go ahead and click Next. Now, you'll need to fill out some basic information for your new project. First up, choose your product name. Let's go with My First App for now, because, come on, we all remember our first attempt. How original, right? Next, select your team if you're signed in to your Apple developer account. But hey, don't worry if you're a beginner. This step is optional. In the organization name field, you can write your name or your company's name if you're feeling fancy. The organization identifier, which is typically in reverse domain name format, should look something like com.yourname. This identifier is really important. It's used to uniquely distinguish your application from others. Now, let's specify the interface and lifecycle of your app. For the User Interface option, select Storyboard. This choice is going to set up your app to use Interface Builder, making it way easier to design your app's UI visually. Then choose Swift as your programming language. Swift is an intuitive and powerful language that Apple designed specifically for iOS and macOS app development. It's time to make the leap into coding. Now, click Next and select a location to save your project. You can pick any directory that you prefer, but I highly recommend creating a dedicated folder for your projects to keep everything organized. After selecting a location, just click on Create, and like that, you've officially generated your first Xcode project. Let's take a quick glance at the Project Navigator on the left side of Xcode. You should see a file structure that contains the primary files for your project. The most important files right now are appdelegate.swift and viewcontroller.swift. These are the building blocks of an iOS application. Now, let's implement a simple label in our view controller. Below the line where we set the background color of the view to white, we will create a ULabel instance. This label is going to display a welcoming message to our users. So, first up, we'll set the text property of the label to "Welcome to my first app." That's a friendly greeting for anyone who opens the app. Now, let's align that text to the center, because we want our message to look neat and be easily readable on the screen. Next, we need to specify the frame of the label. This means we're defining its position and size in relation to the parent view. In this case, we're going to give it a width of 300 points and a height of 50 points, and be sure to center it using its center property. This way, it'll appear right in the middle of the screen, which definitely enhances visibility. Finally, we will call the addSubView method to attach our label to the main view, making sure it's visible to our users. Now, this step is crucial. If we don't add the label as a subview, well, it just won't show up on the screen. And that's it. With this implementation, we've set up a basic but effective UI element that really enhances the user experience in our app. Next, let's run our app and watch our code come to life. So, on the top left corner of Xcode, you'll find a play button. This is your run button. Go ahead and hit that. Xcode will build your project and launch the iOS simulator for you. Now, if an iPhone model isn't already visible, just select one from the drop-down list right next to the play button. All right, once the application launches, you should see a white screen with your welcoming message right in the center. Congratulations! You have successfully installed Xcode, created a new project, and even coded your very first app. Now, if you run into any errors at this stage, don't sweat it. Seriously, debugging is a normal part of the development process. Just double-check your code and look over any warnings or errors that Xcode highlights in the Issue Navigator. You've got this. Next, we will implement a button that enhances user interaction within our app. This button will change the text of the label when tapped, providing a simple yet effective way to engage users. So, to create the button, we first initialize it as a system-type UButton and set its title to Tap Me, just for display purposes. Now, let's position the button within our view by specifying its frame dimensions, making sure it appears centrally placed within the interface. Once we have positioned it, we need to set up an action that gets triggered when the button is interacted with. This is accomplished by linking the button's touch event to a method called changeLabelText. And hey, don't forget to add this method above the viewDidLoad function. The changeLabelText method will update the text of our previously created welcome label with a new message, "You tapped the button." When this executes, it provides instant feedback for the user's action, showcasing a dynamic aspect of the app. Through this button setup, we've introduced a foundational element of interactivity that enhances the overall user experience. Now, let's take a look at a simple SwiftUI code snippet that demonstrates how to create a basic user interface. In this structure, we define a view called ContentView, which conforms to the view protocol. The main component of any SwiftUI view is the body, where you declare what the view will display. Inside the body, we implement a text view that displays the message, "Hello, SwiftUI." To enhance the user experience, we apply modifiers to the text. First, we set the font to .large, making it more prominent and visually appealing. Next, we customize the text color to blue using the .foreground color .blue modifier, which helps it stand out against the background. And finally, we add some spacing around the text with the .padding modifier, preventing the text from being too close to the edges of its surrounding view. This modification process exemplifies the declarative nature of SwiftUI, where you can easily change how UI elements look and behave with just a few lines of code. With these simple steps, you create an engaging starting point for your app's interface while leveraging the intuitive capabilities of SwiftUI. Before we wrap up, let's make sure you're comfortable with the latest updates for Xcode. Apple frequently rolls out updates, and these come packed with new features, bug fixes, and performance improvements. So it's a great practice to check the App Store every now and then, or even better, enable automatic updates in your Mac settings. Staying current will not only enhance your development experience, but also keep your tools optimized for the latest iOS versions. Now, another recommendation is to dive into the extensive documentation provided by Apple. It's truly an invaluable resource. You'll find tutorials, API references, sample code, and integration guides all laid out for you. Whether you're looking to build a complex application or just mastering the basics, Apple's documentation has got you covered. As you continue your journey into iOS development, remember that practice is key. Regularly using Xcode, experimenting with coding, and not hesitating to challenge yourself with new projects, these are all important. Each app you create enhances your skill set, boosts your confidence, and prepares you for more complex applications in the future. Now, in summary, downloading and installing Xcode is just the starting point. From setting up your first project to coding your initial app, the learning process is incredibly rewarding. So, enjoy the ride, keep exploring, and transform your ideas into reality with the power of Xcode. To run your app on an actual iOS device, we need to shift from our development environment in Xcode to the handheld devices that users will eventually interact with. While the simulator offers some great initial testing capabilities, it simply can't replicate everything. Today, we're going to explore the ins and outs of running your app on a real iOS device and the benefits that come with testing hardware components and software APIs. So far, we've learned about downloading and installing Xcode as an essential first step for iOS development. We talked through obtaining Xcode from the Mac App Store and getting it installed. All that includes agreeing to a license and setting up necessary components. We also created a new project, set up our app's interface using Storyboard, and even wrote some initial Swift code to build and run our first application. And let's not forget, we introduced user interaction with a button and discussed the potential of using SwiftUI for more intuitive UI design in future projects. Now, let's dive into how to run your app on an iOS device, which will allow you to see real-world performance and behavior. First things first, make sure your iOS device is ready. You'll need either an iPhone or an iPad with the latest version of iOS installed. Connect your device to your Mac using a USB cable and ensure you can access it through Xcode. If this is your first time connecting your device, you might be prompted to trust the computer on your iPhone or iPad. Just follow the on-screen instructions and, make sure you unlock your device if it's locked. Once you've trusted it, your device will show up in the list of devices in Xcode. This displayed horizontal bar chart, titled Time to Run Your App on an iOS Device, lists 6 sequential setup steps on the vertical axis and shows the time in minutes on the horizontal axis. Each step is annotated with its integer minute value. Connect device, 3 minutes. Trust computer, 2 minutes. Launch Xcode, 1 minute. Select device, 4 minutes. Run app, 10 minutes. And trust certificate, 2 minutes. From this visualization, we can draw several clear conclusions. The single longest step, run app, takes 10 minutes, which accounts for roughly 45% of the total summed time of 22 minutes. This indicates that deployment and runtime syncs are the dominant time syncs. Then we have select device at 4 minutes and connect device at 3 minutes. These come next in the hierarchy of time consumption, while launch Xcode, being comparatively quick, only takes a minute. Now, if we group the two trust-related steps, trust computer and trust certificate, they total 4 minutes, which actually matches select device on its own. These patterns highlight that while some preliminary steps are quick, the actual deployment and run phase is where we see the bottleneck. So that's definitely something to focus on when estimating total setup time or troubleshooting delays. Oh, and those annotated bars make it super clear where you should prioritize optimization efforts. This way, you can effectively reduce overall setup duration in the most impactful manner. Now, let's see how we can implement the necessary permissions for accessing the user's location in our app's configuration. In the info.plist file, which is key for defining the app's settings, we need to specify the key NSLocation when in use usage description. This key is really important because it lets the user know why our app needs access to their location while they're actively using it. Following the key, we provide a string. This acts as a descriptive message. The aim of this message is to clarify to users why we're requesting their location data, assuring them that accessing their location will enhance their experience with the app. Now, it's crucial to craft this message thoughtfully, as a clear and informative description helps build user trust and encourages them to grant the necessary permissions. Remember, iOS will prompt users for permission when they try to use location-based features, so the message you provide can really influence their consent. By setting up this key value pair in info.plist, we're ensuring that our app meets the requirements for accessing that sensitive user information while being transparent about its intentions. Next, let's build our app. Click the Run button located at the top left corner of your Xcode window. It's going to compile all that app code and install it on your connected device. Now, just a heads up, the first time you run it, this process might take a few moments. That's because Xcode has to set up various components, so just hang tight. If everything goes smoothly, you'll see your app open on the device automatically. But, if something goes wrong, don't panic. Xcode will provide error messages or alerts. Pay close attention. Common hiccups can come from the development team configuration or device provisioning issues. If your app isn't deploying correctly, just go to the project settings and double-check that you've selected the right development team. This is crucial for code signing, you know? Once your app launches on the device, dive in and interact with it just like any user would. Test all the functionalities. Tap buttons, swipe through views, and enter some data. You know, it's so important to see how it performs in the real world, especially when it comes to user experience and speed. You might even catch things that you didn't notice while using the simulator. For instance, remember that hardware-dependent features like the camera or GPS will only work when you're running your app on an actual device. Now, let's take a look at how we can implement a simple data management solution within our view controller. In this example, we define a class called MyViewController, which inherits from UIViewController, so we can utilize all the features provided by UKit for building an interactive user interface. Within this class, we declare a variable called DataArray. It's an array of strings that will be used to store data in memory. This array serves as our data model. Now, when the view loads, the viewLoad function gets called, triggering the loadData method. This method showcases a simple loop that populates the data array with 1,000 items, where each item is labeled item followed by its respective index. While this implementation works well in a controlled environment like the simulator, it's absolutely essential to profile memory usage on an actual device using instruments. We want to ensure that such data handling doesn't lead to memory issues, which can be cumbersome. By profiling, we can assess how the application performs under real-world conditions, making adjustments as needed to optimize user experience in the final app. So let's keep that in mind as we move forward with our project. Now, let's implement a function that allows us to fetch data when a button is tapped. In this code, we define an action connected to a button in the interface using the @iBackground keyword. This means the function will be triggered the moment the user interacts with that button. When the button is tapped, the function captures the starting time using date, which will help us measure how long the fetch operation takes. Then we call fetchData, which is presumably a function that retrieves information from an API. This function takes a closure as a parameter, enabling asynchronous behavior. That means the app won't freeze while it's waiting for the data to come back. Inside the closure, we calculate the elapsed time by subtracting the start time from the current time. This helps us understand how efficient our data fetching is going. Then we use print statements to log the elapsed time and the response data to the console. This is super useful during development because it allows us to track the app's performance in real time on an actual device. Monitoring these logs can help us diagnose issues and optimize network interaction, ensuring a seamless user experience. User interface interactions are also a critical area of testing. Your app may look perfect on the simulator, but let me tell you, the touch interactions, well, there's something entirely different on an actual device. So take the time to test gestures thoroughly. Tapping, swiping, and pinch to zoom if your app implements such features. Real-world latency and response issues often creep in here. Make sure that all touch targets are large enough for users to interact with easily. Testing on real devices can really reveal hidden problems that you might miss if you're only using the simulator. Now, as your app interacts with services like location, the camera, or Health Kit, it's vital to test these interactions on an iOS device to truly gauge how they perform under various conditions. For instance, switching between foreground and background while using location services can impact how your app maintains an accurate location, which is definitely something you need to keep an eye on. So make sure you're thorough in your testing. It could save you a lot of headaches down the line. In summary, running your app on a physical iOS device is a crucial step in the development process. Now, the simulator, it's a fantastic tool for initial testing, no doubt. But real devices reveal those little nuances in performance, user interface behavior, and hardware interactions that the simulator simply can't fully emulate. By leveraging Xcode's capabilities for compiling, provisioning, and debugging, you can ensure that your app isn't just functional on a theoretical level, but truly performs seamlessly in the real world. Engaging with your app in this manner will really enhance user satisfaction and retention, leading to a more polished, finished product. From testing memory management to optimizing touch interactions, every detail, dramatic pause. So now, strap in and let's explore this fascinating journey of app deployment. Watch as your code transforms into reality on actual devices. Now, let's dive into the exciting world of Swift programming language. If you're ready to learn, buckle up. Swift is powerful, intuitive, and an essential language for iOS development. Today, we will explore how Swift handles simple values and types, really setting the foundation for your programming journey. So far, we've laid down the foundational steps for iOS development, like installing Xcode and creating a new project with an app interface using Storyboard. We emphasize the importance of testing on actual iOS devices for accurate performance insights. And we discussed how to prepare the app for deployment. Remember that managing code signing and permissions via the info.plist file is key. Plus, we dove into debugging tools and techniques for optimizing performance, ensuring a seamless user experience through real-world testing of UI interactions and those hardware-dependent features. And we can't forget, we highlighted the necessity of thorough testing, which enhances user satisfaction and the overall quality of the app. Now, let's pivot to the core aspects of the Swift language, focusing on its values and types. Now, let's explore how to define an integer variable in Swift. In this example, we'll declare a variable named age, and it's of type int. We're assigning it the value of 25. Now, this straightforward declaration really highlights the importance of type safety in Swift. By specifying the type as int, we're ensuring that this variable can only hold integer values. And why is that important? Well, it helps prevent unintended errors. Imagine trying to assign a string like 25 to age. Swift would actually stop you and raise a compile time error instead. This feature of Swift not only helps maintain the integrity of your data, but also aids in debugging, as these rules around types are enforced at compile time. As you continue your journey in Swift, you'll find that such constraints enable you to write more secure and reliable code, letting you focus on other parts of your application logic without worrying about accidental type mismatches. So you see, it's all about creating a robust foundation for your programming efforts. Now, let's dive into the world of floating point numbers in Swift, which are essential for representing decimal values. Here's how we can implement this. We start by defining a variable called pi using a type of double. This allows us to store a more precise representation of pi, approximately 3.1415. The use of double is crucial in scenarios where accuracy is paramount, like scientific calculations. Next, we introduce another variable named temperature, but this time we opt for the float type. Now, why float? Well, the float type consumes less memory than double, which makes it perfect for storing values like temperature that don't need as high precision. This distinction between double and float is particularly important when choosing the right type for your application's requirements. It's a key consideration in programming, especially for tasks related to scientific and graphic computations. By understanding these types, you're better equipped to handle data accurately and effectively in your Swift applications. The figure titled Fundamental Data Types in Swift displays a bar chart that quantifies the relative importance of 4 core Swift types: int, which holds 25%, double at a prominent 35%, string at 30%, and bool, the smallest, at 10%. Each data type appears on the x-axis, while the y-axis shows corresponding importance percentages with numeric labels above each bar. Now, if we take a look at the chart, we see that double is really the standout here, clearly emphasizing the focus on floating point precision and numerical computations. Coming in right behind it is string at 30%, which underscores just how vital text handling is in most Swift tasks. Int, while at 25%, shows that whole number arithmetic continues to play an important role, just a tad less dominant than its floating point and string counterparts. And then there's bool at 10%, indicating that while logical conditions are indeed necessary for programming, they occupy a smaller portion of this overall importance picture. From these proportions, we can conclude that when we combine the numeric types, int and double together, along with string, we actually hit a whopping total of 90%. This suggests that our instruction should really focus on numeric precision and string manipulation first and foremost, with double and string being the primary concepts, followed by int, while Boolean logic serves as a supportive topic, although less central. So there you have it. Now, let's explore how we can handle strings in Swift, which are fundamental for displaying and manipulating text in our applications. We start by declaring a variable named greeting that stores a simple string message, "Hello Swift." This demonstrates how easy it is to create and assign string values in Swift. Next, we'll write another variable, name, assigned with Alice representing a user's name. To craft a personalized message, we now implement string concatenation by creating a variable called welcome message. This variable combines both greeting and name using the addition operator. Additionally, we utilize string interpolation to seamlessly embed the name within the welcome message. This clever technique allows us to create dynamic and user-friendly output, resulting in a message that reads, "Hello Swift, my name is Alice." This showcases how Swift string manipulation features, particularly concatenation and interpolation, make it super easy to produce interactive and engaging text outputs in your applications. Now, let's take a closer look at how to work with Boolean values in Swift, which are really fundamental for controlling the flow of your program. In our code, we'll start by declaring a Boolean variable named isSwiftFun and assign it to value true. This declaration signifies that we're defining a state that can either represent something as true or false. Next, we'll implement a simple conditional statement using an if statement. The if checks whether isSwiftFun evaluates to true. If it does, Swift executes the block of code that prints Swift is indeed fun. This really demonstrates how the condition dynamically influences the output based on the Boolean value we set earlier. Now, if isSwiftFun were false instead, the else block would execute, prompting us with let's make Swift fun. This execution flow highlights the power of Booleans in making decisions within your code, allowing for a more interactive and responsive user experience. Understanding how to utilize Booleans effectively is crucial for writing logical conditions that steer your application's behavior. Now that we've got a grasp on Swift's fundamental types, let's dive into how type inference simplifies our coding experience. Here, we're going to implement a variable named message and assign it the string type inference is cool. Now, notice something interesting. We haven't explicitly defined the type of this variable. Instead, Swift automatically infers that message is of type string just based on the value assigned to it. This is such a great illustration of Swift's type inference feature, which really enhances readability by cutting down on redundancy in our code. Thanks to type inference, you can focus more on writing meaningful code without getting bogged down by specifying types for every variable. I mean, this approach helps maintain type safety while allowing for a cleaner coding style. By letting the Swift compiler deduce the variable type from the assigned value, developers can write more concise and clear code without sacrificing safety. So, understanding and leveraging type inference is crucial here, as it streamlines the development process and makes our Swift code more elegant and efficient. Now, let's take a look at how we can use constants in Swift to enhance our code's reliability. In Swift, constants are defined using the let keyword, which creates a value that remains unchanged throughout the execution of the program. For instance, we can declare a constant called maximum login attempts and assign it the value of 3. This means that anywhere in our code, this constant will reliably represent the number of allowed login attempts, ensuring that developers do not inadvertently alter this value at runtime. This practice not only prevents potential bugs related to changing critical values, but also communicates the intent clearly to anyone reading the code. Using constants helps maintain data integrity and simplifies debugging, as the programmer can clearly see which values are meant to remain fixed. Constants are especially useful for configurations or settings that should remain constant, making your code not only more understandable, but also easier to maintain. Deep breath in, then sigh softly. Now let's take a look at how to work with arrays in Swift, which are essential for storing ordered collections of values. Thoughtful pause. To declare an array of integers, we use the syntax that specifies the type of the elements the array will hold. In this case, that's int, followed by assigning it an array of integers. This allows us to efficiently manage groups of related data, like, say, a list of numbers. Next, we're going to write some code to access specific elements from the array. We can achieve this by using the index of the element we want, keeping in mind that Swift employs zero-based indexing. So this means the first element is at index 0, the second at index 1, and so forth. In our example, to fetch and print the second number in the array, we can simply use print numbers 1. This line will output the number 2, demonstrating how easy it is to retrieve values from an array based on their position. Understanding this array access pattern is crucial because you'll frequently use it to manipulate collections of data in your applications. Next, we will look at how to use dictionaries in Swift to store and retrieve data effectively. A dictionary is a collection that holds key-value pairs, making it an excellent choice for associating identifiable keys with corresponding values. For example, we can create a dictionary named Student Grades, where each student's name serves as the key and their grade represents the value. This structure allows us easy access to a student's grade based on their name. Now, let's see how we can implement this in our code. By defining student grades, we initialize it with a few entries, such as Alice receiving an A, Bob a B, and Charlie a C. This format allows you to quickly look up any student's grade. To retrieve Bob's grade, we use the dictionary syntax student grades, parentheses, Bob. However, since the information we retrieve could potentially be absent, we incorporate the double dash operator. This operator safely unwraps the optional return value, providing a default message, not found, if Bob's entry is missing. This enhances the robustness of our application by preventing runtime crashes. This way, we ensure that our code handles errors gracefully while managing key-value data efficiently. Now, let's see how we can implement a set in Swift. A set is a unique collection of elements, which means it ensures no duplicates, making it a really valuable structure for scenarios where distinct values are essential. So, in our example, we start by declaring a set called fruitSet, which stores strings representing fruit names. Initially, we populate this set with 3 fruits: apple, banana, and orange. Now, to demonstrate the dynamic nature of sets, we can insert grapes into fruitSet using the insert method. This action ensures that grapes is added to our collection while automatically managing the uniqueness of items in the set. Finally, we utilize the count property to retrieve the number of unique items within the set, which now totals 4. It's important to note that sets do not maintain any specific order, so the printed output may display these fruits in a different sequence than they were added. This feature highlights the unordered nature of sets and showcases their usefulness for handling collections of distinct items in Swift. As we round off our introduction to Swift, let's take a moment to appreciate how these foundational values and types are crucial for diving into more sophisticated features and programming paradigms, like object-oriented programming with classes and structures. Now, grasping how to handle basic data types isn't just a minor detail. It empowers you to implement logic, process data, and effectively manage program flow. On this adventure, you're not just learning syntax, you're immersing yourself in the very language of programming. Remember, whether you're building a simple app or a complex software system, mastering these basic building blocks in Swift will really help you navigate the vast ocean of coding with a lot more confidence. So, keep practicing, explore the Swift playgrounds. Yes, and get your hands on some cool projects. Your journey is just getting started. On our next session, we're going to dive deeper into control flow statements. Yes, you heard that right, where we'll explore conditionals and loops. These are really key components that will help us make our applications dynamic and responsive. It's like giving our code a brain, allowing it to make decisions and repeat actions based on various conditions. The journey is just getting started, and trust me, it's only going to get more exciting from here. Now, let's dive in to creating a new Swift file to encapsulate distinct functionality within our app. So, the code we're working with defines a class named NewClass, which acts as a blueprint for crafting objects that will showcase specific behaviors and properties. Inside this class, we've got a method named SayHello. Now, here's the cool part. When we invoke this method, it simply prints a cheerful greeting message to the console. This structure lays the groundwork for object-oriented programming in Swift, which means we can create instances of NewClass that encapsulate more complex behaviors as needed. By organizing our code this way, we're not just making it functional, we're also enhancing its readability and maintainability, especially as our projects become more intricate. Think of it as building blocks. Each class can represent different functionalities or features of your app, making it much easier to manage and develop over time. Such a modular design helps keep your code organized, allowing for the reuse of classes across various sections of your application. Now, as you're building your iOS app, I really encourage you to consider creating classes for different aspects of functionality so your code base remains clean and efficient. Such a modular design helps keep your code organized, allowing for the reuse of classes across various sections of your application. Now, as you're building your iOS app, I really encourage you to consider creating classes for different aspects of functionality so your code base remains clean and efficient. Now, let's see how we can implement image loading in our app using Swift. So, we're going to explore a handy code snippet that demonstrates a common pattern for safely loading an image from your app's resources. It all begins with something called optional binding. This is where we attempt to retrieve an image named logo.png using the UIImage class method named. What this method does is search for the specified image in the app's resource bundle. Now, if the image is successfully found, we safely unwrap it. That means the image variable will hold a valid UIImage object. We then assign this image to an UIView app, which we'll call ImageView. This process is really important because it ensures that our app only tries to set the image if it actually exists, which helps to prevent potential crashes that could occur from trying to use a nil value. By organizing your images in the Resources folder and loading them programmatically like this, you're not just keeping things tidy, you're promoting a clear structure in your project. This, in turn, enhances the user interface of your app with seamlessly integrated assets. It's a fundamental practice in iOS development, ensuring that your app runs smoothly and interacts pleasantly with users. Now, what we see here is quite telling. Code and asset management really take the lead. Source and resources together make up a whopping 55% of the distribution, emphasizing that more than half of the project's focus is on organizing and maintaining those source files and assets. The project navigator, sitting at 20%, plays a crucial role in providing access and organization across our code and those resources. On the other hand, we have info.plist at 15%, which represents a significant yet smaller part dedicated to application configuration and metadata. This highlights that while configuration is essential, it's not the mainstay of our daily project activities. And finally, the debug area, which at just 10% is the smallest segment on the chart, suggests that although debugging and runtime inspections are incredibly important tasks, they occupy a lesser portion in our project's perceived structure. So, from this distribution, we can conclude that prioritizing a clear organization of our source code and resource files should be our primary focus, while also managing our info.plist entries carefully. And let's not forget to leverage the project navigator and debug area effectively for a smooth development experience and easier troubleshooting. Now, let's implement the necessary entry in the info.plist file to request camera access from users. This is essential for any app that needs to utilize the device's camera, as it allows you to communicate the purpose of this access to the user. The specific key to include is NS camera usage description, which serves as a flag for the system to understand why your application is seeking permission to use the camera. So, in our entry, we'll pair this key with a corresponding string value that explains to the user about the camera's usage. For example, you might say, "This app requires access to your camera to take photos." This message pops up when users are prompted to grant this permission, ensuring transparency and building trust. It's really imperative to present a clear and concise reason for this access. Failing to do so could actually lead to your app being denied during the app review process. So remember to craft this message thoughtfully, as it plays a critical role in user experience and your compliance with App Store guidelines. As your project scales, source control becomes an essential tool for tracking changes and collaborating with others. Now, Xcode comes equipped with some nifty source control features that are integrated with Git, which means you can manage your project versions right from the interface. You can find this under the Source Control menu, where you can easily commit changes, push to repositories, and manage branches. Now, let's take a look at the Source Control Preference screen. This is where you can configure your repository settings, like defining remote repositories or adjusting your sync and commit preferences. Check out how it can look. In this screen, you can connect your project to a Git repository, allowing you to push your local changes and ensure that collaborative work stays in sync. And here's the best part. Having this capability integrated into Xcode means you can focus more on coding and less on managing your project outside of the IDE. So let's embrace this tool and streamline our workflow. Navigating back to your project, let's explore how to utilize additional features like groups to organize your files better. Now, Xcode does a decent job of auto-organizing files in the navigator based on their type, but here's the cool part. You can create custom groups to sort things out according to functionality or features. For example, imagine you're working on, let's say, networking tasks. You might create a group called Network where you can stash all your networking-related files, like your API clients and models, all in one place. To make a new group, simply right-click within the Project Navigator, select New Group, and then drag existing files right into that group. Keeping related files together, that's going to make for quick access and really boost your workflow efficiency, especially in larger projects. Finding files quickly, right? So, let's say you're deep into network calls. You could have your API manager.swift, network era.swift, and models such as user.swift all tidily organized in the network group. That way, making changes to your networking logic becomes as easy as pie. And who doesn't love that? Now, let's implement a basic button action that responds to user interaction. In the code, we define a function using the @IBAction keyword, which signifies that this function is designed to be called in response to a user action. In this case, that's tapping a button. The function is named buttonTapped, and it takes one parameter, _sender UT_button. This parameter refers to the button that triggered the action, allowing you to access its properties if needed. Inside the function, we have a simple statement that prints a message to the console: "Button was tapped." This serves as a confirmation that the button press was successfully registered. Using print statements during development is an excellent way to track the flow of your app and debug issues effectively. Now, in the context of the storyboard you created earlier, linking this code to the button ensures that whenever a user taps that button, this function is executed, allowing your app to interact responsively with user commands. This really demonstrates how storyboards can simplify connecting UI elements to the underlying code logic, making the app development process not just more intuitive, but also more visual. Now, let's take a look at how we can implement a function to handle user input when a button is tapped. In this code, we define an action method called submitForm, and this is linked to a button in our user interface. So this method will be triggered whenever that button is pressed. Inside the function, we begin by retrieving the text that's entered in two text fields, username field and password field. This gives us access to the user's username and password, which are, crucial for login functionality. The values entered by the user are stored in constants for further processing. Next, we print a message to the console displaying the submitted username while keeping the password hidden, of course, for security reasons. This logging step is vital for developers to debug and ensure that the correct username is being captured without exposing sensitive information. In a real application, you might follow this action with authentication logic, like validating the input against a database. Overall, this simplicity in handling user input highlights the importance of maintaining security protocols, particularly when dealing with sensitive user data, like passwords. In summary, understanding the Xcode project structure is crucial for effective iOS development. From navigating the project navigator to leveraging source control and utilizing storyboards, every aspect plays a role in streamlining the development process and enhancing your coding experience. So, as you continue your journey into iOS development, remember to periodically revisit your project structure and keep it organized. This will not only help you maintain clarity in your coding style, but it will also enable more efficient collaboration with other developers along the way. Now, in our next session, we're going to dive deeper into control flow statements, exploring conditionals, loops, and how they help in making our applications dynamic and responsive. The journey continues, and it's only getting more exciting from here.
Understanding developer mode is essential for anyone venturing into iOS development. In this segment, we will dive deep into what developer mode is, why it was introduced by Apple during the Worldwide Developers Conference in 2022, and how it helps developers install, run, and debug their apps on devices running iOS 16 or greater. So far, we learned the basics of iOS development, including setting up Xcode and creating a project, as well as understanding essential data types and collection types in Swift. We explored the importance of project organization within Xcode, particularly the role of the project navigator, source and resources folders, and the info plist file. Additionally, we discussed source control integration for version management and the use of storyboards to design user interfaces. Looking ahead, we will examine control flow statements to enhance application functionality. Now we will talk about the specifics of developer mode and its implementation in iOS app development. Developer mode is designed to bridge the gap between a developer's environment and the live operating system running on iOS devices. When activated, it allows you to access features necessary for deploying applications efficiently. Without it, developers would find themselves limited in what they can test and build on devices, which would ultimately hinder the development process. Think of it as unlocking a treasure chest of tools and functionalities that are crucial for app development. To activate developer mode, you first need to enable it on your iOS device. This is accomplished through the Settings app. Head to Privacy and Security, where you'll see an option for developer mode. By toggling this setting, you inform the device that you want to transition into a development-friendly version. This feature not only facilitates app installation, but also allows for debugging tools. The figure titled Key Concepts in Developer Mode for iOS Development displays a pie chart divided into 5 labeled segments with their relative percentages. App installation 35%, debugging 25%, performance testing 20%, version control 10%, and UI design 10%. The chart makes 2 clear patterns evident. First, the combined emphasis on app installation and debugging constitutes the majority, 60% of the chart, indicating that enabling developer mode primarily supports deploying builds to devices and troubleshooting runtime behavior. Second, performance testing is the next largest single slice at 20%, showing a substantial, though secondary, focus on profiling and optimizing apps while running on real hardware. The remaining slices, version control and UI design, are equal at 10% each, implying they are important but represent smaller, complementary concerns within the developer mode context. From this distribution, we can conclude that the practical priorities when working with developer mode are to ensure smooth installation and robust debugging capabilities, then allocate effort to performance analysis, while still maintaining version management and UI considerations. Now let's see how we can implement a check for developer mode directly in our iOS application. We start by defining a class called ViewController, which inherits from UIViewController, a fundamental building block for any iOS app's interface. Within this class, the viewDidLoad method is overridden to include our functionality. This method is called after the ViewController has loaded its view hierarchy into memory, making it the ideal place to execute setup code. In this method, we invoke a custom function, isDeveloperMode which we'll define next. The purpose of this function is to determine if developer mode is activated on the device. It achieves this by accessing user defaults, a simple key value store built into iOS where we check the value for the key developer mode. Depending on whether this key returns true or false, our app will print a corresponding message indicating whether developer mode is enabled. This approach provides a straightforward yet effective way to adapt the app's behavior based on the mode, offering developers insights on accessing advanced features or debugging information during their development process. Now let's see how we can implement a simple button action in our app, which is crucial for interactive features. We start by defining an action method for the button, indicated by that IBAction keyword. This allows Xcode to recognize that this function should be linked to a button press in the user interface. The method named buttonTapped takes a parameter of type UIButton, which gives us access to the button that triggered the action. Inside this function, we invoke performComplexCalculation, a separate function that simulates a calculation and returns an integer value. The result of this calculation is stored in the variable result. This step showcases how we can encapsulate logic in separate functions to keep our code organized and readable. Finally, we print the result using a string interpolation technique, which helps in debugging by displaying the output directly in the console. This structure not only simplifies our interaction, but also sets up a basic framework for further functionality, paving the way for more complex logic and user interactions as we advance in our development journey. In addition, developer mode allows for performance testing and gathering analytics data over time. With tools like instruments, developers can monitor various system resources, including memory usage, CPU load, and network performance. These metrics are invaluable, particularly for applications with complex functionalities or real-time requirements. Performance bottlenecks can heavily impact user experience, so it's crucial to ensure everything runs smoothly. You would invoke instruments directly from Xcode. With your app running in developer mode, you can profile it by selecting Profile in your product menu. You'll be presented with various options for performance testing, such as Time Profiler, Allocations, and more. Let's take a look at what it looks like to leverage instruments. Assume you're suspecting that a part of your app is using too much memory. You could track your app's performance with the Allocations tool in Instruments. 1. Start your app within Instruments by selecting it from Xcode. 2. Use your app normally while Instruments captures data on memory allocations. 3. Analyze the data afterwards to identify any potential leaks or high memory usage points. The good news is that Instruments is quite user-friendly, presenting analytics visually, allowing you to identify where optimizations can be made effectively. The significance of developer mode is not just theoretical, it manifests in every aspect of developing, running, and debugging an application. Developer mode creates a secure environment tailor-made for iterative development and testing, streamlining workflows and facilitating quicker releases of applications to end users. It's crucial to keep in mind, however, that using developer mode comes with its own sets of responsibilities. Make sure to keep your code clean, utilize comments for clarity, and regularly commit your changes if you're using version control. This practice ensures you have a history to revert back to in case something goes wrong. As we progress through this journey of iOS development, embracing tools like developer mode will significantly enhance your capabilities as a developer, allowing your creativity to flow freely while maintaining control over the applications you build. So wrapping up this segment, we've covered what developer mode is, how to enable it, the benefits it provides in app installation and debugging, as well as performance testing using tools like instruments. The insights gained in this lesson will form a strong foundation as we move forward into more complex topics in iOS development. Next, we'll shift our focus to control flow statements, another crucial aspect of programming that enables you to add logic and complexity to your applications. Control flow statements will allow you to dictate how your program responds to different inputs and scenarios, ultimately creating a more dynamic user experience. There's so much to look forward to, so let's keep that curiosity rolling. Managing app certificates and signing in Xcode is a pivotal aspect of iOS development that every aspiring developer must master. Today, we're going to tackle an error you might encounter. Signing for JRNL requires a development team. Understanding how to manage your app certificates and signing will not only help you resolve this error, but will enhance your development experience overall. So far, we learned the fundamentals of iOS development, including project setup in Xcode, essential Swift data types, and the importance of organization and source control. We also introduced developer mode, highlighting its role in facilitating app installation, debugging, and performance testing. Moving forward, we will cover app signing, certificates, and how to manage them effectively to avoid those pesky errors. Before diving into management techniques, it's essential to understand what app signing and certificates actually are. App signing is the process of verifying that the app's source code has not been altered after it was compiled. It's a crucial part of maintaining the security and integrity of the app, ensuring users that the app comes from a trusted source. Certificates, on the other hand, are digital documents issued by Apple that confirm your identity as a developer. Think of them as your app's passport, ensuring it can enter the iOS ecosystem. To get started, you'll need an Apple developer account. This account allows you to create and manage certificates, app IDs, and provisioning profiles necessary for signing your app. If you haven't signed up, please visit the Apple developer website and create your account. Once you have your account, we can proceed. The first step in managing your app certificates is navigating to the Apple Developer Portal. Log in to your account and find the Certificates, Identifiers, and Profiles section. Within this section, you'll have the opportunity to create a variety of certificates, development certificates for testing and distribution certificates for production apps. To create a new certificate, click on the Certificates section. Here you'll see an option to add a new certificate. You will need to select the type of certificate you require. For development purposes, you should choose iOS App Development. This certificate allows you to run your app on physical devices during the development phase. After selecting the type, you will need to create a Certificate Signing Request (CSR) on your Mac. This is where it can get a bit technical, but don't worry, I'll guide you through it. Open Keychain Access on your Mac and navigate to Keychain Access, Certificate Assistant, request a certificate from a certificate authority. Fill in the required fields with your email and common name, and make sure to select Save to Disk to save your CSR file. This file will be used to create your development certificate on the Apple Developer Portal. Once you've generated your CSR, go back to the Apple Developer Portal, upload this CSR file, and follow the prompts to create your certificate. After you've successfully created your certificate, download it and double-click on the file to add it to your keychain. Now that you have your app certificate set up, it's time to create a provisioning profile. A provisioning profile combines your app's signing identity with the devices that you want to be able to run the app on. To create a provisioning profile, head back to the Certificates, Identifiers, and Profiles section of the Apple Developer Portal. Click on Profiles and then select Add a new profile. You'll be presented with various options. Choose iOS App Development for development purposes. You need to select the app ID that corresponds to your app. If you've already created an app ID for your app, select it here. If not, you can add it quickly using the provided options. Afterward, select the certificate you just created. Next up, you'll choose the devices you want to include in this provisioning profile. Your provisioning profile will ultimately be associated with the devices on which you're going to test your app. After selecting the devices, give your profile a name that is meaningful to you and complete the process by generating the profile. Don't forget to download and install it. The figure displays a horizontal bar chart titled The Importance of Key Elements in Managing App Certificates and Signing, with 5 categories ranked by percentage. Certificate creation, 30%, provisioning profiles, 25%, debugging issues, 20%, team management, 15%, and updating certificates, 10%. From these values, we can see that the largest single focus is on certificate creation, followed closely by provisioning profiles. Together, they account for 55% of the total importance shown, indicating that initial setup tasks, creating certificates and linking them to app IDs and devices, are the primary activities when managing signing. Debugging issues occupies the next largest share at 20%, highlighting that once setup is done, diagnosing and resolving signing-related problems remains a substantial ongoing activity. Team management and updating certificates trail at 15% and 10% respectively, showing that coordination within a development team and periodic certificate renewal or rotation are important but comparatively lower effort or lower frequency tasks. The steady decline in percentages across the categories suggests a prioritization model. Invest most effort and attention in getting certificates and provisioning profiles correct, allocate significant resources to debugging when problems arise, and maintain regular but less intensive practices for team coordination and certificate updates to avoid future disruptions. Now, with your certificate and provisioning profile in place, it's time to configure Xcode to recognize them. Open Xcode and select your project from the Project Navigator. Navigate to the Signing and Capabilities tab. Here, you'll see the Signing section, where you will configure your team and your profiles. If you see the error "Signing for JRNL requires a development team," it usually points to the absence of a selected development team in your project settings. Under the Team dropdown, select your Apple developer account. If you've just set everything up, it might take a moment for Xcode to recognize your certificate and provisioning profiles. Once you select your team, Xcode will automatically manage the signing based on the provisioning profile that matches your project setup. If everything is configured correctly, you should no longer see any signing errors. Let's dive a bit deeper into the signing process and how to handle potential issues. Even with everything set up correctly, you might occasionally encounter problems like certificate expirations or conflicts in provisioning profiles. It's essential to regularly check and renew your certificates to avoid interruptions in your development workflow. For example, if you receive a message saying that your certificate has expired, return to the Apple Developer Portal and generate a new certificate following the same process as before. Once you have your new certificate, you'll also need to create a new provisioning profile associated with this updated certificate. If you try to run your app and still see a signing error, go back to the Signing and Capabilities tab in Xcode and ensure that your provisioning profile is correctly set. Sometimes Xcode doesn't refresh automatically, so forcing a change, like switching to manual signing and then back to automatic, might help trigger a refresh. Debugging signing issues can feel a bit like playing detective. You might find other errors that stem from mismatched bundle identifiers or app IDs. Each app has a unique bundle identifier that needs to be consistent across all your profiles. If they don't match, you'll see errors when trying to build or run the app. To check your bundle identifier, click on your project in Xcode and go to the General tab. Here you'll see the Identity section containing the bundle identifier field. Ensure this matches with the app ID on your provisioning profile. If there are any mismatches, resolve them to get your app building smoothly. Once everything is set, you can take your app for a spin. Try running it on a physical device to ensure that it installs correctly and that signing is functioning as expected. Remember, providing real-time testing is still essential. Nothing beats seeing your app in action. As we wrap up, managing app certificates and signing may initially seem overwhelming, but with practice, it becomes a seamless part of your development workflow. Just like cooking, you will pick up on the flows and nuances as you continue to prepare your application for iOS. So far, we have learned about the importance of app signing, the process of creating certificates and provisioning profiles, and how to troubleshoot the signing errors you might face along the way. Now, take this knowledge and apply it to your next project. Embrace the challenge and keep developing your skills as you grow into an adept iOS developer. To run your iOS app on an actual iOS device, you not only get a true representation of how your app will perform, but also get access to features that the simulator simply cannot replicate. It's an essential step to validate the functionality, performance, and hardware integrations of your app. In this session, we will explore the necessary steps to run your iOS app on a real device, discuss the advantages of testing on hardware, and provide a walkthrough on how to do it seamlessly. So far, we learned the significance of managing app certificates and signing in Xcode for iOS development, including understanding app signing and certificates as essential security measures. We covered the steps to set up an Apple developer account, create certificates and provisioning profiles, and configure Xcode for proper app signing. Additionally, we discussed troubleshooting common signing issues, including certificate expirations and bundle identifier mismatches. This foundational knowledge prepares us to effectively manage app signing throughout our development journey. Now, we will cover how to run your iOS app on a physical device, explore the setup requirements, and look at some insightful techniques that will elevate your app testing experience. First, let's begin with the essentials. Ensure that you have a compatible iOS device and a Mac running the latest version of Xcode. You'll also need to be registered in the Apple Developer Program, as this will allow you to install your app on actual devices. You might be wondering, why not just use the simulator? Well, it doesn't mimic all the hardware features. For instance, the simulator can't accurately replicate camera functionality, GPS location data, or device-specific hardware configurations such as gestures and accelerometers. Once you've confirmed that you have all the prerequisites, connect your iOS device to your Mac using a USB cable. Open Xcode and go to Window Devices and Simulators. Here, you should see your connected device listed. If you're lucky, Xcode will recognize your device automatically, but if it doesn't, make sure you unlocked your device and trusted the computer when prompted. Now let's dive into some configurations needed for your device. Click on the plus button, then choose your device from the list. Make sure that the device is registered for development under your Apple Developer account. Once your device is registered, you need to develop a provisioning profile that includes your device to allow your app to run on it. This is where the signing process comes back into play. Navigate to the Signing and Capabilities tab in your Xcode project settings. Ensure you select the correct team associated with your Apple Developer account. Under Signing, enable the Automatically Manage Signing option. Xcode will magically configure the certificates and provisioning profiles for you, making life a lot easier. In some scenarios, you may run into a signing error. Don't panic. Always check the Other section of the error message to gain valuable insight, or simply look for issues related to expired certificates or invalid provisioning profiles. It's all part of the development journey. Now that your device is connected and your project is set up correctly, we can build and run the app on your iOS device. In Xcode, select your device from the device list located at the top of the window. Once that's done, hit the Run button or use the keyboard shortcut Command plus R. Your project will start building. Keep an eye on the status bar. Once complete, Xcode will install your app onto the device. If everything goes smoothly, you should see your app icon on your device's home screen. Did I mention you might not find an app in the home screen right away? Sometimes it just takes a bit longer to appear. Be patient and give it a moment to show up. It's worth the wait. There might be cases where the app fails to install, displaying a message saying the app could not be installed. If that happens, check to ensure that you're using a device running a compatible iOS version for your app and that your device isn't full. Sometimes restarting the device can magically solve this issue as well. Now let's see how we can implement camera functionality in our app. The code begins by importing the UIKit framework, which is essential for building user interfaces in iOS applications. We define a class called CameraViewController that inherits from UIViewController and conforms to two protocols, UIImagePickerControllerDelegate and UINavigationControllerDelegate. This setup allows us to manage image picking and navigation controller functionality effectively. Within the CameraViewController class, we create a method named OpenCamera. In this method, we first check if the device has camera capabilities by using the isSourceType available method of UIImagePickerController with the camera source type. This is a crucial step to ensure that we don't attempt to use the camera hardware if it's not available, thereby avoiding potential errors. If the camera is available, we instantiate a UIImagePickerController object and set its delegate to self, which allows our class to respond to events from the image picker. We then specify the source type as the camera and present the image picker modally on the screen using the present method. This workflow ensures that users can effectively capture photos using their device's camera, enhancing the interactive experience of your app. If the camera isn't available, we provide feedback by printing a message to the console. Testing performance can also be another aspect of utilizing your device effectively. Real-world performance metrics such as responsiveness, speed, and memory usage can only be gauged on actual hardware. You can use Xcode's instruments tool to measure performance. Head over to Product Profile in Xcode or use the keyboard shortcut Command +I. This opens up several tools, but one of the most insightful is the Time Profiler, which helps track down areas in your code that may be lagging or requiring optimization. Once you've profiled your app and identified performance bottlenecks, dive into optimizing the problematic areas to ensure an ultra-smooth user experience. The figure titled Performance Evaluation of iOS App Running on a Physical Device presents a bar chart of 5 testing aspects on the horizontal axis: app launch, camera functionality, network performance, battery usage, and UI responsiveness, with a vertical scale representing performance scores out of 10. The chart shows camera functionality as the highest scoring aspect with a value of 9, indicating strong performance in hardware-dependent image capture or camera integration. App launch and UI responsiveness both score 8, revealing quick startup times and generally smooth user interface interactions. Network performance is scored at 7, placing it in a moderate position that suggests satisfactory but improvable handling of network-related tasks. Battery usage has the lowest score at 6, signaling a relative weakness where power consumption or energy efficiency may need attention. Overall, the pattern shows generally positive results, scores clustered between 6 and 9, with a clear gap between the best-performing camera feature and the weakest battery metric. This directs immediate action toward optimizing battery usage while maintaining the strong camera and UI behaviors, and treating network improvements as a secondary priority. Another crucial aspect of running your app on an iOS device involves testing the app's network capabilities. For instance, if your app relies on internet connectivity, confirm that its behavior under varied network conditions works properly. You can do this by using the Network Link Conditioner, which simulates different network conditions. The Network Link Conditioner allows you to test how your app performs under slow, very slow, 3G, or edge network conditions. To enable this, go to your device's settings and navigate to Developer Network Link Conditioner. Choose the preset condition you'd like to test. If your app crashes under certain network conditions, that could be a sign of improper error handling or unoptimized network requests. Be diligent about testing these scenarios. Your users will thank you later. Once you've thoroughly tested your application and are happy with the interactions and performance, it's time to unleash it to the world. Before submitting your app to the App Store, go through Apple's App Store review guidelines to ensure compliance. Make sure you've conducted tests on various iOS devices to confirm compatibility across screen sizes, orientations, and operating system versions. Once your app passes all sanity checks and is polished, you can package it for submission to the App Store through Xcode. Navigate to Product Archive, ensure your build is ready for distribution, and follow the prompts to upload your app to App Store Connect. Always remember, testing on an actual device gives you invaluable insights into how your application will perform once it reaches your users. Your goal is to deliver the best experience possible, and embracing real device testing boosts your chances of success exponentially. To sum up our session today, we've covered the process of running your iOS app on an actual iOS device, the importance of hardware testing, and discussed features you can validate directly on your device. We've also walked through handling common issues during installation, engaging hardware features like the camera, and performance profiling. The hands-on experience of running your app on a physical device will pave the way for crafting responsive, engaging, and high-performing applications. So next time you want to test your app, remember that the simulator has its limits, and don't miss out on the magic of real-world testing. Happy coding! Developing and trusting your iOS app certificate is a crucial part of ensuring that your applications run securely and effectively on physical devices. In this segment, we will explore what an iOS app certificate is, how to create one, and why it's vital for your app development journey. So far, we covered the importance of running your iOS app on a physical device to validate its functionality. Now, we will discuss how to develop and trust your iOS app certificate to ensure your apps work seamlessly on your devices. To begin, let's clarify what an iOS app certificate actually is. In simple terms, it's a digital certificate issued by Apple that allows you to sign your apps. This process proves your app's authenticity to both the operating system and the end user, essentially saying, hey, this app really came from me. When you develop an iOS app, Apple uses these certificates to manage app security and ensure that only apps from recognized developers can be installed on devices. Creating an iOS app certificate involves a few critical steps, which we'll go through step by step. The first one is to use the Apple Developer Portal, where you must log in with your Apple ID associated with your developer account. Once logged in, navigate to the Certificates, Identifiers, and Profiles section. Next, we will write a function that programmatically generates a certificate signing request, CSR, which simplifies the process of getting your signing certificate. The function generate_CSR takes two parameters, email and common name. These represent the email address associated with the certificate request and a name that identifies the certificate, respectively. Inside the function, we simulate the CSR creation by formatting a string that includes the common name and email. This string mimics the output you would expect from a real CSR generation process. The purpose of this simulation is to give you a conceptual understanding of how the information is structured rather than delving into the complex cryptographic details that would normally accompany a real CSR generation. We then print the generated CSR to the console, allowing you to see the outcome directly. To execute this function and visualize the result, we pass in a sample email and common name as arguments. This straightforward demonstration lays the groundwork for understanding how a CSR works in practice, providing you with a foundation to explore more advanced implementation in real scenarios. The donut chart titled Key Concepts in Developing and Trusting Your iOS App Certificate breaks the process into 5 labeled segments with proportional sizes. Certificate creation, 20%, trusting certificate, 30%, provisioning profiles, 25%, development certs, 15%, and distribution certs, 10%. The largest slice, trusting certificate at 30%, indicates that explicitly marking the certificate as trusted is the single most emphasized action in the workflow. It is a primary step to ensure the device accepts signed builds. Provisioning profiles at 25% is the next most significant piece, highlighting that linking certificates, app IDs, and devices is nearly as crucial as trust itself. Certificate creation at 20% shows that generating the CSR and obtaining the certificate remains a substantial portion of the process. Development certificates, 15%, and distribution certificates, 10%, are smaller slices, implying that while both certificate types are necessary, they occupy less immediate focus compared with establishing trust and correct provisioning. Taken together, the 3 largest segments, trusting certificate, provisioning profiles, and certificate creation, account for 75% of the chart, suggesting a priority order. Create the certificate, ensure the system trusts it, and configure provisioning profiles before concentrating on the distinctions between development and distribution certificates. This distribution underscores practical priorities immediately after you obtain the certificate file and before you proceed to installation and testing. Once you've generated and saved your CSR, the next step is to upload it to the Apple Developer Portal. After uploading, you will need to choose the type of certificate required for your project, like a development or distribution certificate. Development certificates are used for apps you're still developing, while distribution certificates are for apps you intend to submit to the App Store or distribute to users. After choosing the right type of certificate, click Continue. Apple will process your CSR and provide a certificate file for you to download. Make sure to keep track of this file, as it is crucial for signing your app. Next, you'll want to install this certificate on your Mac. Double-click the certificate file you just downloaded, and it should automatically open in Keychain Access and be installed there. If everything went well, you should see it listed under My Certificates. But don't get too comfortable just yet. We need to go a step further. You need to trust your certificate to set the trust level. 1. Open Keychain Access. 2. Locate your certificate listed under My Certificates. 3. Right-click the certificate and select Get Info. 4. Expand the Trust section and set, when using this certificate, to Always Trust. Make sure that you lock in these settings. Trusting your certificate is crucial because it ensures that any app you build and sign with this certificate is accepted by your device without throwing security warnings. Now let's dive into the provisioning profiles. Provisioning profiles are essential as they link your certificate, app ID, and device. They act as a bridge between your app and the iOS operating system, allowing your app to run on a specific device with the correct entitlements. To create a provisioning profile, go back to the Apple Developer Portal. Under the Provisioning Profiles section, click the plus button to create a new profile. You'll have to choose between development and distribution profiles based on what you're doing. Each type serves a different purpose and needs the proper settings. When creating the profile, you'll select the app ID you want to use, choose the certificate you added earlier, and specify the devices you want your app to run on for testing. Now let's take a look at how we can ensure our app is launched with the correct provisioning profile by incorporating a few essential methods in our app delegate class. In the code snippet, we start by importing UIKit and defining our app delegate, which conforms to UI application delegate. This sets up the delegate that responds to app lifecycle events. Within the application did finish launching with options method, we ensure that our application is launched correctly by checking the provisioning profile. We assign a placeholder value to profile ID for our specific provisioning profile, which you will need to replace with your actual profile ID. This method is critical because it runs when the app starts, making it an ideal spot to validate the provisioning profile early on. Next, we call the check provisioning profile ID function, which simply prints the profile ID to the console. This simulation acts as a way to demonstrate how you can validate the app signature and provisioning profile during development. By implementing this check, we can catch any discrepancies early, ensuring a smoother testing phase and a more reliable deployment later on. Through this practice, we reinforce the importance of correct provisioning in the app signing process. Trusting your iOS app certificate and properly managing your provisioning profiles are essential to creating a seamless development process. Remember, a certificate is more than just a digital file. It's the foundation of security and validation for your iOS applications. So far, we have learned about the importance of the iOS app certificate, how to create and trust it, and the role of provisioning profiles in app development. Now, we need to ensure that our certificates are maintained properly moving forward to avoid any potential issues. It's important to note that certificates and provisioning profiles have expiration dates. Be sure to keep track of these so that you can renew them or create new ones as necessary. Apple often changes security practices, so staying updated on best practices is key in this fast-paced environment of app development. Being proactive about managing your certificates can save you from last-minute headaches when you're preparing to distribute your app or submit it to the App Store. Keep your Xcode and operating system updated, and routinely check your certificates and provisioning profiles to ensure they are valid and correctly configured. In conclusion, embracing the process of developing and trusting your iOS app certificate is crucial for building robust and secure applications. As we've explored today, from generating a CSR, creating and installing your certificates, to setting up provisioning profiles, each step is a building block towards successful app deployment. As you embark on your development journey, take pride in the security protocols you've now woven into your learning. Whether you're a seasoned developer or just starting, understanding this foundational aspect will serve you well throughout your app development career. And remember, it's all part of ensuring a quality user experience, so keep coding, stay curious, and enjoy the beautiful journey of iOS development. To run your app on an iOS device, you'll need to understand the ins and outs of deployment and trusting certificates. In this lesson, we will break down the entire process into digestible steps. We'll explore how to effectively navigate iOS app deployment, ensuring a seamless experience when transferring your wonderful creations from Xcode to your actual iPhone or iPad. This journey is crucial for developers aiming to test and validate their apps on physical devices before making them available on the App Store. So far, we covered the significance of the iOS app certificate and the process of creating and trusting it for app development. We explored how to generate a certificate signing request, CSR, install the certificate, and set its trust level on your Mac. Additionally, we discuss the role of provisioning profiles in linking certificates, app IDs, and devices to ensure proper functionality on physical devices. Managing these elements is essential for securing your applications and facilitating a smooth development process. Now, we will cover how to deploy your app to an iOS device and trust its certificates. To begin with, you have your app developed in Xcode and it's time to run it on a physical device. First, ensure that your device is connected to your Mac via USB. Open Xcode and select your project in the Project Navigator. You will need to configure your app's deployment settings. Navigate to your project settings by clicking on the project file, then click on the General tab. Here, you'll find the deployment target settings, which indicate the minimum iOS version that your app will support. It's essential to select the right version that corresponds to your physical device's iOS version. Next up, let's talk about your signing and capabilities. Under the Signing and Capabilities tab, ensure that you have your developer account selected. Xcode will automatically handle the signing certificate and provisioning profile for you, but if you run into signing issues, it often helps to click the Fix Issue button provided by Xcode. This will generate a new provisioning profile that matches the app's bundle identifier and allows you to install the app on your connected device. Now let's dig deeper into provisioning profiles and signing certificates since they are the backbone of deploying your app. Provisioning profiles tie together your app ID, team ID, and device IDs. When developing, you're usually using a development provisioning profile that allows you to run the app on your registered devices. Download the correct provisioning profile from the Apple Developer Center and double-click it to install it on your machine, ensuring that it becomes available to Xcode. You can also create a new provisioning profile by logging into your Apple Developer account. Navigate to Certificates, Identifiers and Profiles, select Profiles and click the plus icon to create a new one. Choose iOS App Development as the type, then specify your app ID and select the certificates and devices you want to include in this profile. Once created, download and install it, making sure you refresh Xcode to recognize the new profile. The displayed figure titled iOS App Deployment Stages presents a bar chart that quantifies typical time allocation, duration, days, for each stage of deploying an iOS app. The x-axis lists the stages in order: initial setup 20 days, certificate creation 15 days, provisioning profiles 25 days, app deployment 30 days, trusting certificates 10 days, and gathering user feedback 5 days. The y-axis shows duration in days, and each bar has its numeric value labeled on top for precise comparison. From the chart, app deployment is the most time-consuming single stage, 30 days, followed closely by provisioning profiles, 25 days, and then initial setup, 20 days. Certificate creation takes a moderate amount of time, 15 days, while trusting certificates, 10 days, and gathering user feedback, 5 days, require the least time. The pattern indicates that configuration and deployment-related tasks, provisioning and deployment, form the primary bottlenecks in the workflow, whereas final verification and feedback collection are comparatively brief but necessary steps. Interpreting these values within the lesson, prioritize efforts and time allocation on provisioning and deployment processes to reduce overall cycle time, while still ensuring certificates are trusted and feedback is collected efficiently. With the provisioning profile in place, it's time to set your device as a testing environment. Make sure your device is added to the provisioning profile as previously mentioned. You'll find your device listed under Devices in the Apple Developer Center. Next, unlock your iPhone or iPad and ensure you've trusted your Mac. When you connect the device for the first time, a prompt will appear asking if you trust this computer. Confirm that you do. Now let's talk about the magic moment of deploying the app. In Xcode, select your device in the Scheme menu next to the Run button. Click the Run button and Xcode will build the app, install it on your iOS device, and launch it automatically. If this step fails, it's likely due to an issue with your provisioning profile or certificates. Check your logs carefully in the output console within Xcode to identify the issue. In the case where your deployment was successful, you should see your app running comfortably on your iOS device. But that's not the end of the story. If you attempt to run your application and see a message indicating that the app can't be opened, it's likely because your certificates are not trusted on the device. To trust the certificates on your iOS device, you must manually set this within the device settings. First, on your iOS device, navigate to Settings, General VPN, and Device Management. Under the Developed by Enterprise Apps section, you should find the certificate associated with your app. Tap on it and then select Trust Your Company Name. This action tells your device to allow apps signed with this particular certificate to run. What's essential here is understanding how to control those certificates. Certificates act as a digital passport for your app. They confirm that the app was signed accurately and comes from a known source, preventing malware and security risks. Once trusted, your app will run smoothly without displaying errors related to untrusted certificates. Now let's take a look at a simple code example that demonstrates how to manage and update a score in a Swift app. In this snippet, we define a variable named score, which is an integer initialized to 0. This variable represents the current score of a player or the progress of an activity in your app. Next, we introduce a function called updateScore, which accepts a parameter named points. This function is responsible for updating the score by adding the value of points to the existing score. Every time this function is called, it performs the addition operation and then prints the updated score to the console, providing immediate feedback on the current state. This functionality is valuable for tracking how a user interacts with your app, especially in gaming or scoring scenarios. Now, let's explore how we can integrate this function into our app. You can place breakpoints within the updateScore method in Xcode to pause the execution and observe how the score changes with each call, allowing you to debug effectively and ensure the scoring system works as intended. This interactive debugging process is crucial for refining your user experience and enhancing your app's performance. Now that we have your app running on an actual device, let's move on to the essence of optimizing your iOS deployment. The deployment process doesn't just stop at getting the app on your device. It's crucial to maintain version control through updates. Regularly updating your app and its dependencies will not only provide improvements and bug fixes, but also ensure compatibility with the latest iOS features. When updating your app, you must re-sign your certificates and install new provisioning profiles if changes were made to your app's configuration. Always keep a backup of your certificates and provisioning profiles to avoid any hiccups. Apple recommends using Xcode's automatic management for simpler development workflows where changes to the profiles are updated automatically. To roll out updates, ensure that you increment your app's version number and build number each time you make a release. This process is straightforward in Xcode. Under your project settings in the General tab, you can find the version and build fields. For example, if your current version is 1 and you've added significant changes, bump it up to 1.1 or even 2. The build number generally increments with each new build for the same version, such as 1.11 to 1.12. Keeping track of these versions is essential in maintaining a robust deployment cycle. Once all adjustments are made, proceed to deploy the new version just like before. Your device will receive the latest changes, ensuring your user experience is continually evolving. Finally, let's touch on beta testing before your app officially hits the market. Using TestFlight, Apple's beta testing service, you can gather vital user feedback on your app. To set up TestFlight, you'll need to archive your app in Xcode, upload it to App Store Connect, and then configure your TestFlight settings there. This process allows you to invite testers and gather insights, giving you a director's perspective before the public release. You can obtain aggregate crash reports and usage statistics to further understand how users interact with your app, allowing you to polish it before it reaches a broader audience. In your app, implement a method to capture feedback from users directly. User experience is paramount, and leveraging feedback constructs a community of users invested in the growth of your app. In the end, deploying your app isn't just about hitting that run button. It's about the entire experience, from connecting certificates and signing your app to ensuring that every user is heard during testing. It's a journey filled with learning and challenges that every developer faces. The process seems intricate at first, but with each new deployment, you'll find yourself mastering the nuances of iOS app deployment. Remember, practice makes perfect, so continue iterating on these steps as you develop new and exciting apps for iOS. To run your app on an iOS device, connecting and configuring it properly is essential. In the following segments, we will explore the necessary steps for setting up your iOS device for app development. This process is one of the vital skills needed to test your applications in a real-world environment. So far, we covered the deployment process from Xcode to a physical device, including the management of signing certificates and provisioning profiles. We also touched on trusting certificates on your device, debugging techniques using logs and breakpoints, version control, and using TestFlight for beta testing. In this lesson, we will be discussing how to connect and configure an iOS device for development effectively. The first thing you need to do is ensure that your iOS device is ready for development. To start, grab your iOS device and connect it to your computer using a USB cable. It's like when you plug in your smartphone to charge it, but in this case, you're charging your development capabilities. Once plugged in, unlock your device. You should see a prompt on your iPhone or iPad asking if you trust this computer. Go ahead and tap Trust. This step is vital as it allows your computer to interact with your device for app deployment and debugging. Once your device is connected, the next step is to open Xcode, navigate to the Window menu and select Devices and Simulators. Here, you will see the option to view all of the simulators and devices connected to your computer. If your device isn't listed, ensure that it's connected properly and that you have trusted your computer. Now that we've established a connection, let's talk about installing necessary tools and configurations. To properly set up your device for development, you will need to sign into your Apple developer account in Xcode. Go to Xcode, Preferences Accounts, and add your Apple ID. If you don't have a developer account, you can create one through the Apple developer website. This account will provide you access to provisioning profiles and the App Store when you eventually want to publish your app. We are not just signing in for fun here. This is crucial for creating signing certificates and provisioning profiles that ensure your app runs smoothly on physical devices. In the Signing and Capabilities section of your Xcode project, make sure your team is selected. This connects the app's identity to your developer account. Let's dive a bit deeper into provisioning profiles, as they might sound a bit complex but are essential for app deployment. A provisioning profile is a collection of security settings that allows a specific app to run on your iOS device. It links your Apple ID credentials with your app's bundle ID, which uniquely identifies your app in the iOS ecosystem. To create a provisioning profile, you need to navigate to the Apple Developer Portal. Here, select Certificates, IDs, and Profiles. Under Profiles, click the plus button to create a new profile. Choose the profile type based on your needs. If you're a beginner, the iOS app development option is the way to go. You will be guided through a series of steps, including selecting the app ID, your development certificates, and the devices on which you'd like to run the app. If you haven't registered your device in the developer portal yet, you can do so by clicking on Devices in the same section and following the prompts to add your device. The figure displays a bar chart titled Time spent on key steps for connecting and configuring an iOS device for development, with 6 sequential setup steps on the x-axis and the time spent in minutes on the y-axis. The labeled values on top of each bar show: Connect device 10 minutes, Trust computer 5 minutes, Open Xcode 20 minutes, Configure settings 15 minutes, Provisioning profiles 10 minutes, and Run app 5 minutes. The clear pattern is that interacting with Xcode, opening it, and configuring project settings accounts for the largest portion of setup time. Open Xcode alone is the single largest item at 20 minutes, and together with Configure settings, 15 minutes, they represent more than half of the total setup time. Trusting the computer and the final Run app step are the quickest, at 5 minutes each, while provisioning profiles and the physical act of connecting the device are moderate at 10 minutes each. From this distribution, we can conclude that preparing and configuring Xcode and project settings is where learners should focus their time and preparation, while the connection and deployment steps are relatively fast once the prior configuration is completed. Planning workshops or personal setup sessions accordingly will reduce bottlenecks during hands-on development. Now you'll want to download the newly created provisioning profile and integrate it into Xcode. Head back to Xcode and make sure to close your project before dragging the downloaded file into the Provisioning Profiles section in Xcode Preferences. Then reopen your project. Under Signing and Capabilities, you will now see your new profile ready to be selected. The next critical part is to ensure that your iOS device appears under the Valid Devices list in Xcode. When configuring your Xcode project, select your device as the target device for running the app. If everything is set up correctly, you should see your device listed as available. Now is the time to actually run your app on the iOS device. In Xcode, select your device from the list of available devices. You'll find this right next to the Run button. Don't worry, it's not going to blast into space. It's just a click of the button away from transforming your code into a reality on the physical device. Hit the Run button, the triangular play symbol, and if everything is configured correctly, your app will compile and deploy to your device. You should observe your device's screen light up, showing the app being installed. If you encounter any issues at this stage, refer back to the provisioning profiles and ensure your app ID matches any configurations made earlier. Always make sure your iOS device has a stable connection and enough storage space. Let's not forget about testing. We need to ensure your app behaves as expected. Debugging on the device is generally more insightful than using simulators because you get real-world performance data. You can view logs in Xcode while the app is running on your iOS device. Click on the Debug option in the top menu. From here, you can access the console output to monitor logs and catch any errors that may occur. Additionally, employing breakpoints helps significantly while debugging your application. Insert breakpoints by clicking on the line number in Xcode where you want the execution to pause, allowing you to inspect variables and application state at runtime, which can be immensely helpful in pinpointing issues. Once you have tested your app, you might want to share it for more extensive testing. Using TestFlight, which is integrated with Xcode, you can distribute the app to beta testers. To do this, navigate to the Product menu in Xcode, select Archive, and upload your build to App Store Connect. In TestFlight, you can manage testers and gather feedback. This stage is crucial for understanding how users interact with your app in a real-world context. It's like getting a sneak peek of how your creation performs under actual pressure, and just like that, you're one step closer to launching your app on the App Store. To wrap it all up, we meticulously walked through the steps necessary for connecting and configuring an iOS device for app development. We discussed everything from physically connecting your device, setting up your Apple developer account, and managing certificates and provisioning profiles, to deploying your app, running tests, and utilizing TestFlight for beta testing. These skills aren't just academic, they're practical tools in your development toolbox that help you bring applications to life on real devices, providing you with invaluable insights into user interactions. As you progress in your development journey, continuing to refine these processes will make you a more effective and efficient developer, ready to tackle any challenge that comes your way. So that's it. You now have the groundwork to take your exciting ideas and turn them into functioning apps on real iOS devices. Keep practicing and testing. Happy coding. Running your app on an actual iOS device is an essential part of the development process. While the simulator is a great tool for initial testing, to truly experience how your app interacts with hardware components and software APIs, you'll want to run it on a physical device. In this lesson, we'll explore the various methods of deploying your apps directly onto an iOS device, how to address common issues you might encounter, and the importance of testing on real devices. So far, we learned the essential steps for connecting and configuring an iOS device for app development, including the deployment process from Xcode to a physical device. We explored the significance of trusting the computer, signing in to an Apple developer account, and creating provisioning profiles necessary for app deployment. Additionally, we covered how to run and debug your app on a device, as well as using TestFlight for beta testing to gather user feedback. These foundational skills will help you effectively develop and test applications on real iOS devices. Now, we will delve deeper into the advantages of using a physical device, how to ensure a successful deployment, and what troubleshooting techniques can be employed if things don't go as planned. The displayed bar chart, titled Comparison of Testing Environments for iOS App Development, compares two testing environments, simulator testing and real device testing, by showing paired percentage bars for advantages and disadvantages on the y-axis %. The simulator shows 60% advantages and 40% disadvantages, whereas the real device shows 90% advantages and 10% disadvantages. These values sum to 100% for each environment, indicating a direct trade-off representation. Simulator testing retains a moderate majority of advantages, but still carries a substantial portion of limitations, while real device testing concentrates the vast majority of benefits and minimizes drawbacks. From this pattern, we can conclude that real device testing offers a significantly higher advantage to disadvantage ratio, 9:1 compared to the simulator 3:2. Reinforcing the lesson point that hardware-dependent features, accurate performance profiling, and real-world user interactions are far better validated on physical devices. Use the simulator primarily for rapid iteration and convenience, and rely on real devices for final verification and performance-sensitive scenarios. When testing your app, there's a unique experience that comes from interacting with hardware features that the iOS simulator simply cannot replicate. Think about functionalities like the camera, GPS location services, or push notifications. Not only does testing on a physical device help you catch bugs that might not show up in the simulator, but it also provides insights into the performance of your app in real-world scenarios. Imagine using your app in sunlight. How does the display react? How does it handle interruptions like phone calls or text messages? These are scenarios that you need to test directly on a device. To get started, make sure your iOS device is connected to your Mac through a USB cable. If you're using macOS Catalina or later, open Finder. For older macOS versions, you'll want to open iTunes. As a quick reminder, ensure that your device is trusted by the computer. You can do this through a prompt that appears on your device when you first connect it. Once you confirm trust on your iPhone, you'll be set to begin. Now let's take a look at how we handle camera permissions in our app. First, we import the UIKit framework to utilize iOS's visual elements. In our ViewController class, we override the viewDidLoad method, which is called after the view has been loaded into memory. Here, we check the current authorization status for video access by using the AV-Capture-Device authorization status method. If the status returns not determined, it indicates that the user has not yet granted or denied permission for camera access. In this case, we call AV-Capture-Device request access, which prompts the user for permission. The closure we provide checks if access was granted or denied. If granted, we acknowledge this with a print statement confirming access. Otherwise, we inform that access has been denied. Next, we also handle the scenario where the status is already denied, so we print a message to indicate that the user has previously denied access. This approach ensures that our app communicates clearly with users about permissions, which is crucial for maintaining a positive user experience while adhering to privacy guidelines. Now let's examine a crucial part of our app, fetching data from a remote server. We will implement a function called fetchData, which is responsible for making a network request to retrieve information. In our function, we start by creating a URL that points to the desired API endpoint. Next, we utilize URL session to initiate a data task. This task will make the request and handle the response asynchronously within a closure. Inside this closure, we first ensure there's valid data returned and check for any errors. If an error occurs, we print a message to the console indicating what went wrong. Once we've confirmed that the data is successfully retrieved without any errors, we proceed to process that data by passing it to another method called handleResponseData. This method is where you would add your logic to manipulate or display the fetched data in your application. Finally, we call taskResume to start the actual data fetch. This is a fundamental aspect of iOS networking that allows us to interact with remote APIs seamlessly, ensuring our app can retrieve and display dynamic content. Now let's take a look at a practical example of handling image loading within an iOS application. In this code snippet, we define a class called ImageProcessor, which serves the purpose of loading images from a specified URL. The class has a single property called image, which is an optional UI image. This allows it to store the image that will be fetched. Next, we implement a method named loadImageFrom, which accepts a URL parameter. Inside this method, we use the data contents of initializer to try loading the data from the specified URL. It's important to note that this operation can throw an error, which is why we use the try syntax to handle potential failures gracefully. If data is successfully retrieved, we then create a UI image from that data. However, it's crucial to highlight that this approach can lead to memory management issues, particularly when dealing with large images. Since the image is directly assigned to the image property without any optimization, it may consume significant memory, potentially affecting the app's performance. To improve this, we could implement strategies such as lazy loading or asynchronous image loading, which will help prevent blocking the main thread and enhance user experience. Now let's take a look at how to implement a logging feature for beta testing. Logging user interactions and events can provide invaluable insights during the testing phase of your app. In this code snippet, we import the OS module, which is part of the Swift programming language's capabilities for handling system-level operations and logging. Next, we define a function called logEvent that takes a string parameter called message. This function's purpose is to capture specific events that occur while users test the app. Inside the function, we create an instance of logger, which is initialized with a unique subsystem identifier and a category label to help organize the logged information. By naming the subsystem, example, my app, we ensure that our logs are easily identifiable among others. Finally, we use the logger log method to record the event, incorporating the message that was passed into the function. This structured approach not only helps in tracking user behavior during beta testing, but can also highlight areas for improvement prior to the official app launch. Thus, effective logging can lead to a more polished final product, enhancing overall user experience. Finally, don't forget about user feedback. Direct feedback from users who test your app will provide valuable insight that may not be captured through analytics and crash reports alone. Encourage users to report issues or suggestions. You can include a feedback button in your app that directs users to a form, or alternatively, use services like Firebase Crashlytics to capture error reports automatically. As you refine your app based on provided feedback, you'll not only enhance the user experience but also raise the overall quality and reliability of your application. Through this process of deploying, testing, and iteratively improving your app on real devices, you'll build an understanding of user interactions and hardware capabilities that the simulator cannot offer. Taking the time to run your applications in real-world scenarios is absolutely crucial to your success as an iOS developer. In summary, running your app on an actual iOS device opens up a world of testing opportunities that improve app performance and user experience. We've discussed how to set up your device for deployment, the importance of permissions, effective debugging, performance testing, and gathering user feedback. So get out there and make the most of these tools at your disposal. Happy coding. The world of iOS app development is just a tap away. Creating your first iOS app and running it in the simulator is an exhilarating milestone in your development journey. Today, we'll explore the various steps and techniques to ensure your app runs smoothly and efficiently within the simulator environment. So far, we learned about the critical importance of testing your app on physical iOS devices to assess its interaction with hardware features and real-world performance. We covered essential steps for app deployment, device trust settings, and provisioning profiles, alongside debugging techniques and performance testing with tools like instruments. The significance of managing app permissions and gathering user feedback through beta testing, such as test flight, was also emphasized. These foundational skills ensure you develop high-quality iOS applications. Now we'll talk about creating your first app, ensuring you know how to run it smoothly in the iOS simulator, and setting yourself up for success as you bring your ideas to life on the screen. To kick things off, let's make sure your development environment is ready. Ensure you have Xcode installed on your Mac. This is the integrated development environment for macOS that bundles everything you need to create apps for iOS. Head over to the App Store, search for Xcode, and download it. Once installed, open Xcode and let's create our first project. When you launch Xcode, you'll be greeted by the welcome screen. Click on Create a new Xcode project. This opens a template selection window where you can choose from various app types. For our purposes, we'll select App under the iOS tab. Click Next. At this point, you'll need to fill in some basic information for your project. Name your app something fun. For now, let's call it My First App. You also need to provide your organization identifier. This can be something that resembles a reverse domain name format like .com/yourname. Next, make sure interface is set to SwiftUI and lifecycle is set to SwiftUI app. Choose Swift as your language. Set your project's options accordingly and click Next. Select a location to save your project on your computer, and Xcode will create a new project workspace for you. Once the project setup is complete, let's dive into the code. Open the file named Content View Swift. Here, you will find a basic structure provided by SwiftUI. You should see a struct content view that conforms to the view protocol. The figure titled Steps in Preparing Breakfast Using Swift Concurrency displays a simple bar chart with 4 labeled steps on the x-axis, step 1 through step 4, and time in seconds on the y-axis. Visually, the chart contains 2 non-zero bars followed by 2 zero-height bars. Step 1 shows a value of 2 seconds and Step 2 shows a value of 7 seconds, while Step 3 and Step 4 are recorded as 0 seconds. Each bar has its numeric value annotated on top, and the plot includes horizontal dashed grid lines to help read the time values. From the data shown, the dominant time cost is concentrated in Step 2, 7 seconds, with Step 1 representing a much smaller portion of the total time, 2 seconds, and no additional time recorded for Steps 3 and 4. The clear pattern, 2 active steps followed by 2 zeros, indicates that the measurable work in this sequence is confined to the first 2 steps. A practical takeaway is to target optimization or concurrency efforts on the step that consumes most time, step 2, to reduce overall elapsed time when applying Swift concurrency patterns. Now let's see how we can implement a basic view in SwiftUI to display a simple message. In this code snippet, we define a structure named Content View that conforms to the View protocol, establishing it as a reusable component of our app's user interface. The body property is critical in SwiftUI, acting as a container where we define what our view will show. Within this property, we utilize the text view to present the string "Hello, World" on the screen. This is a fundamental starting point for understanding how to display text in a SwiftUI app. To enhance the visual presentation, we apply the padding modifier to the text view. This modifier adds whitespace around our text, ensuring it stands out and is easily readable. As we move forward, you'll find it beneficial to run the app in the simulator to see your changes live. This experience reinforces the interactive nature of your code, allowing you to witness the straightforward yet powerful declarative syntax of SwiftUI in action. So let's run our app and observe how the interface reacts. Now that you have selected your device, hit the play button. Xcode will compile your app, which may take a few moments. Once the build completes successfully, your simulator should launch automatically, displaying your app. Voila, you've just created a simple app. If you look closely within the simulator, you can see the "Hello, World" message. Take a moment to relish this accomplishment. You just made your first iOS app, but hold on to your excitement because there's more to explore. Next up, let's add some interactive features to your app. One exciting way to do this is by incorporating buttons. Modify your Content View Swift to include a button that modifies the text displayed when tapped. To do this, we first need a state variable to hold our text and a function to update it. Next, we will write a state property that will manage the text displayed in our app. The @state keyword is crucial here, as it allows SwiftUI to automatically update the user interface whenever the state changes, ensuring a dynamic presentation of text. We initialize this state variable named displayText with the string "Hello, World," so that upon first launch, the user sees this friendly greeting. Now let's implement the body of the view, where we will set up a vertical stack using VStack. This layout will help us arrange our text and button components vertically on the screen. The text view will display the current value of displayText, and we apply padding to enhance its visibility. Below the text, we introduce a button, which plays a pivotal role in our interactive design. This button has an action block that updates displayText to "You tap the button" when tapped. For visual appeal, we style the button with padding, a blue background, white text color, and rounded corners, making it inviting for users. This integration of state management, UI elements, and styling helps create an engaging interactive experience. Now that we've incorporated interactive elements in our app, let's see how we can implement a button that modifies the text displayed when tapped. We start by defining a button within our user interface. This button has an associated action, which is executed when the user taps it. In this case, we'll change the existing variable displayText to display a new message: "You tap the button." To do this, we will create a button with an action closure. Inside this closure, instead of updating the displayText variable correctly, we will introduce an incorrect variable name, displayTextWrong, which will purposely trigger a compile time error. When you run the code with this mistake, Xcode's issue navigator will highlight the problem and provide an informative error message indicating that displayTextWrong cannot be found. As a result, it teaches us how to identify and rectify common coding issues. After observing the error, simply revert the variable name back to displayText, and you'll be back on track, ensuring that users see the updated message when the button is pressed. This exercise illustrates the importance of careful attention to detail in coding and familiarizes us with the debugging tools available in Xcode. Next, let's put into practice what we learned so far about app permissions, as these are vital when you're dealing with real-world scenarios. While your current app doesn't handle any permissions, let's consider an app that requires camera access. You'll learn how to configure this. In your app's info plist file, you will need to add a key for camera usage. Open the info plist file in Xcode, right-click and go to Add Row. Select Privacy Camera Usage Description from the drop-down menu. Now add a string that explains to users why your app needs access to their camera. For examples, this app requires camera access for taking photos. Accessing device features such as the camera requires thorough user explanation, a golden rule in app development. With our permissions configured, let's now tiptoe into the realm of running tests. Testing is essential, and the simulator is an excellent tool for this, mimicking various devices and scenarios. You can run your app in different configurations to see how it behaves in various screen sizes and orientations. For example, if you want to test your app in landscape orientation, with the simulator running, click on the simulator window and press Command plus left arrow to rotate your app. Notice how your layout adjusts or doesn't adjust. This is an opportunity to build responsive layouts. To provide a better experience, consider using adaptive layout constructs like Geometry Reader, which allows views to adapt based on their environment and container size. Now let's take a look at how we can create a responsive user interface using Geometry Reader. In the body of our structure, we begin by declaring a Geometry Reader, which gives us access to the container's dimensions. By doing this, we can design our views to adapt dynamically to different screen sizes rather than having fixed dimensions. Inside the Geometry Reader, we place a VStack, which allows us to stack views vertically. First, we add a text view that displays the current value of display text. By setting its width to 80% of the parent's width and height to 10% of its height, we ensure that it remains proportionate regardless of the device it's displayed on. Following this, we define a button. When tapped, this button updates display text to indicate the button has been pressed. The button's design is also adaptive. Its width takes up 50% of the parent's width, and the styling includes a blue background and rounded corners to enhance its appearance. This approach shows the power of using Geometry Reader to utilize the available space effectively, leading to a flexible, adaptive design that responds to various screen sizes. Finally, let's wrap things up with a discussion on running your app on a real device as your next big step. Testing on a physical device allows you to assess performance metrics such as load times and resource usage, which cannot be accurately simulated by virtual environments. Connect your iPhone via USB, select your device in Xcode, and build the project as you did with the simulator. Make sure to trust your development certificate on your device. Navigate to Settings, right arrow General, right arrow Device Management, and trust the developer app. Once this is done, you can test your app just like you did in the simulator, but this time it's on your iPhone, interacting with real hardware. Congratulations, you have successfully run your app on an actual iOS device. You've learned critical steps, interactive UI elements, app permissions, and debugging techniques. With the solid foundation and hands-on experience you've gained, you are well on your way to becoming proficient in iOS app development. Retain the excitement, practice continually, and you will master the art of crafting amazing applications. As you dive deeper into the world of iOS development, don't forget to keep your skills sharp and your curiosity alive. Happy coding! Congratulations, you have successfully run your app on an actual iOS device. What an amazing achievement. This moment is truly exciting, and it opens that door to endless possibilities in app development. Today, we're going to dive deep into taking your first steps in building and running your iOS application, focusing on how to turn your ideas into reality on a device that fits in your pocket. So far, we have learned about the creation and testing of your first iOS app using Xcode and the simulator, and we've touched upon the importance of app performance on physical devices. We covered project setup, coding basics with SwiftUI, integrating interactive elements along with error handling in Xcode, and the significance of app permissions and adaptive layouts using Geometry Reader. With these foundational skills under your belt, you're well equipped to successfully develop and optimize iOS applications. Now, let's explore how to take this knowledge further and truly make your app shine on physical devices. Now let's take a look at how to build the main view of our application using SwiftUI. In the content view structure, we define a body property that constructs the user interface. The primary component here is a vertical stack, or VStack, which arranges its children vertically. First, we add a text element that displays a welcoming message to the user, styled with a large title font and padding for better spacing. Next, we implement a button that triggers an action when pressed. This button, labeled Press Me, employs a closure for its action where we print a message to the console. The button is further enhanced with padding, a blue background color, white text color, and rounded corners, making it visually appealing and user-friendly. This simple layout serves as a foundation for interaction in your app. Upon running this code on an actual device, the button becomes interactive, allowing users to engage with the interface and observe the printed message in the Xcode debugger, thereby enhancing your understanding of user interactions in SwiftUI. Now let's see how we can implement a dynamic greeting feature in our app. First, we introduce a @state variable named greeting, which allows the text on the screen to change based on user interaction. This variable is initially set to Hello, iOS developer, and will be updated whenever the button is pressed. In the body of our content view, we utilize a VStack to organize our views vertically. Inside the stack, we place a text view that displays the current value of our greeting variable in a large font and with padding for better visual appeal. Next, we need to make our button interactive. The button view is set up with an action that toggles the greeting text between two different messages. When the button is tapped, it checks if the current greeting matches the initial message. If it does, it changes to Welcome to SwiftUI, and vice versa. This simple toggle not only enhances user engagement, but also exemplifies the principles of state management in SwiftUI. Finally, we ensure our new layout is displayed in the app preview, allowing for real-time updates when the button is pressed. The figure titled Key Concepts in iOS App Development presents a horizontal bar chart that quantifies emphasis across 5 focus areas: running app on device 45%, interactive elements 30%, error handling 15%, app permissions 5%, and performance assessment 5%. The most prominent pattern is a steep concentration of focus on running the app on an actual device, nearly half of the total, followed by a strong secondary emphasis on interactive elements, which together account for 75% of the distribution. Error handling occupies a moderate but noticeably smaller slice at 15%, while app permissions and performance assessment are shown as minimal focus areas at only 5% each. From these percentages, we can conclude that practical device testing and crafting interactive UI receive the bulk of attention in this dataset. Error handling is recognized but less prioritized, and permissions performance are comparatively underemphasized, an important signal to balance priorities when planning development and testing efforts. Now let's implement the Shake Motion class to handle shake gestures. This class inherits from UIViewController and features a closure property called onShake, which will be triggered when a shake motion is detected. Inside the motion-ended method, we check if the motion corresponds to a shake event. If it does, we call the onShake closure, allowing us to define custom behavior when the device is shaken, such as triggering color changes in our app. Next, we'll look at how to integrate this functionality into our main content view. In the content view struct, we introduce a @state variable, color, initialized to white. The body of the view contains a VStack with a full-screen rectangle that fills with the current color and a text view prompting the user to shake the device. Using the onAppear modifier, we instantiate shake motion and assign an action to onShake that updates the color state to a random value, leveraging the colorRandom function. This dynamic interaction showcases how we can respond to physical movements, enhancing user engagement. Finally, we need to create the color extension. Here, we provide a static method called random that returns a color with randomized RGB values. This method allows our app to generate vibrant colors every time the device is shaken, delivering an interactive experience that emphasizes the use of device sensors within our SwiftUI application. Now let's implement error handling in our app to ensure users receive appropriate feedback if something goes wrong during data fetching. We begin by creating a function named fetchData. This function starts by ensuring we have a valid URL to work with. If not, it gracefully exits without executing further. Next, we utilize URL session to create a data task that performs the actual network request. In the closure of this data task, we check for errors in the response. If an error occurs, we switch to the main thread using dispatch_queueMainAsync, which is necessary when updating the UI. We then print a descriptive error message to the console and create a friendly alert to inform the user of the issue, ensuring they understand what went wrong. Lastly, if there are no errors, our application would proceed to process the received data. To show the error alert, we can introduce a helper function, showAlert, where we'll harness SwiftUI's capabilities to present alerts by binding the message to a state variable. This robust error handling approach not only prevents crashes, but actively engages users in a meaningful way, enriching their overall experience with your application. Now let's implement the following function to request camera access from the user. This code utilizes the AV Foundation framework, which provides access to media capture and playback functionalities. The request camera access function calls AV capture device request access for video, initiating a prompt to the user asking for permission to access the camera. Within this closure, we handle the response in a completion handler that receives a Boolean value, granted, indicating whether access was granted or denied. If the user accepts, we can print a message stating that camera access was granted, signaling that we can proceed with functionalities that require camera usage. On the other hand, if permission is denied, we print a message stating that access was denied, allowing us to manage the app's behavior accordingly, such as providing alternate options or informing the user of the limitation. This approach not only ensures compliance with Apple's guidelines, but also highlights the importance of user privacy and transparency in an application's functionality. Always remember to clearly communicate to users why your app needs such permissions to foster trust and a positive user experience. Finally, let's wrap up the lesson with a quick review of what we have covered today. We started by running our app on an actual iOS device, stressing the importance of real-world testing. We then enhanced user interactivity by allowing greeting changes and utilizing device motion for color changes. Following that, we implemented error handling for network requests and discussed the importance of app permissions. So what's next? Take these concepts and expand upon them. Experiment with more features, libraries, and frameworks that interest you. Don't hesitate to explore the vast iOS development ecosystem. You now have a solid foundation to grow from, and I can't wait to see what you create next. Keep coding, keep testing, and most importantly, keep having fun. Happy coding. To effectively develop and debug applications on iOS devices running iOS 16 or greater, you must familiarize yourself with developer mode. This feature was introduced by Apple during the Worldwide Developers Conference in 2022. It allows developers to install, run, and debug their apps on physical devices, giving a true representation of app performance and behavior outside the confines of an emulator. So far, we've learned about the importance of running your app on a physical iOS device, which allows for real-world testing and performance assessment. We explored creating interactive elements, such as dynamic greetings and color changes using device motion, along with implementing error handling in network requests. Additionally, we discussed the importance of app permissions when accessing hardware features like the camera. With these skills, you are well prepared to further develop and enhance your iOS applications. Now, we will cover how to enable developer mode, explore the benefits it offers, and dive into the steps for running apps on an iOS device. Enabling developer mode on your iOS device marks the beginning of a more profound journey into app development. To enable this mode, you'll need to access the device settings. It's a straightforward process. Start by opening the *** settings ** app on your iOS device. Scroll down and tap on Privacy and Security ***. Here, you will find the option for * developer mode ***. When you tap on it, you'll see a toggle switch. Activate this switch and you will be prompted to restart your device. After the restart, you'll need to confirm your choice to enable developer mode. While this may sound simple, it's a crucial step because developer mode allows your device to trust the applications you install from Xcode. In other words, it opens the gates for running your projects directly on the device, bypassing certain restrictions that would have otherwise blocked apps built outside the App Store. Now let's implement the following code to set up our application's lifecycle and customize the launch behavior. This AppDelegate class is crucial as it acts as the central point for app-level configuration. It extends UI Responder and conforms to the UI Application Delegate protocol, enabling it to respond to app lifecycle events. Within the class, we declare a variable window, which serves as the main interface for the app. The application did finish launching with options. Method is where we can execute custom code after the app has launched. This method is automatically called by the system when the app has completed its launch process. Here, we override the default behavior to insert our own functionality. In this example, we print a message indicating that the app has launched, which can be very helpful for debugging purposes and understanding how the application flows during its startup. This simple setup allows developers to build upon the foundation, enabling further configurations as necessary, and ensures that we are ready to debug and enhance our application as we proceed with development. The displayed figure is a bar chart titled Key Concepts in iOS Development that quantifies the relative importance of 5 topics: developer mode 30%, real device testing 25%, error handling 20%, UI testing 15%, and app performance 10%. The chart shows developer mode as the single largest bar at 30%, indicating it is the highest priority concept in this context, closely followed by real device testing at 25%. Together, these two account for 55% of the total emphasis and signal that enabling developer mode and validating on physical devices should be primary activities. Error handling at 20% sits in the middle, highlighting that robust network and runtime error management is a core concern that demands substantial attention. UI testing, 15%, and app performance, 10%, are smaller but still meaningful parts of the distribution, suggesting that visual correctness and performance tuning are important once the app reliably runs on devices and handles errors. From these proportions, we can conclude a recommended workflow. First, ensure developer mode is active and perform real device validation, then prioritize implementing thorough error handling, and finally iterate on UI testing and performance optimizations as subsequent phases of development. Now let's see how we can implement a function to perform network requests in our application. We begin by defining a function called fetchData, which takes a URL string as an argument. The first thing we do is validate the URL. If it's not valid, the function simply returns without proceeding further. This is crucial to prevent the app from attempting to make a request to an invalid address. Next, we create a data task using URL session, shared data task, designed to perform a GET request to the specified URL. Upon executing the request, we handle 3 possible outcomes. If an error occurs, we log the error description to the console, which is essential for troubleshooting and debugging. If data is received, we then try to parse it into a JSON object. If this parsing fails, we catch the error and log it as well, ensuring we maintain robust error handling. Finally, we call taskResume to start the data task. This function encapsulates the essence of making asynchronous network calls in iOS, allowing your app to retrieve data efficiently while handling errors gracefully. This approach not only demonstrates effective network interaction, but is also fundamental when developing dynamic, data-driven applications. Now let's see how we can implement a simple SwiftUI view that enhances user interaction. In this code, we define a content view struct that conforms to the view protocol, which is essential for any SwiftUI design. Within the body property, we create a vertical stack using vstack to neatly lay out our interface components. At the top of the stack, we place a welcoming text element that greets users with the message, "Welcome to my app," styled with a large title font and some padding for visual comfort. Beneath this greeting, we introduce an interactive component, a button that users can tap to fetch data. The button's action triggers the fetchData function, where we specify the URL from which to retrieve data. The button's design includes padding, a blue background, and rounded corners, making it visually appealing and easy to interact with. This arrangement not only encourages user engagement, but also allows for real-time data interaction, providing a dynamic app experience. After setting this view as the root in your app's main structure, you will see how seamlessly user actions translate into network requests, embodying the core principles of app interactivity in SwiftUI. Now let's implement additional error handling into our earlier fetchData function to better manage potential network issues. In this version, we start by ensuring that the provided URL string is valid, or the function will simply return if it isn't. Once we confirm a valid URL, we create a data task with URL session, which is designed to make network requests. Next, we wrap our network completion handler code inside a dispatch queue main async block. This is crucial since UI updates must always be performed on the main thread. Inside this block, we first check if there's an error returned from the network request. If an error exists, we log a descriptive message, which is helpful for debugging, and perhaps you would want to update the UI or inform the user with an alert here. If the request is successful and no errors occur, you would typically handle the received data. This structured approach ensures that your application remains robust even when facing network failures, giving you the ability to address issues gracefully rather than allowing them to disrupt the user experience. Now let's implement the necessary permissions to access the camera in our app. To do this, we need to modify the info.plist file, which is essential for defining the privacy settings of our application. Specifically, we will add a key called NS-Camera Usage Description, followed by a user-facing message that explains why the app requires camera access. This is crucial because iOS will display this message when prompting the user for permission, ensuring they are informed about the app's request. Next, we will create a class that handles the camera functionality, utilizing UI Image Picker Controller. Within this class, we implement the present camera method, where we first check if the device has a camera available using isSourceTypeAvailable. If the camera is accessible, we instantiate UI Image Picker Controller, set the view controller as the delegate, and specify that the source type is the camera. Finally, we present the image picker modally, allowing the user to capture photos directly from the app. This seamless integration facilitates live interactions with the camera feature and enhances overall user experience during testing. In conclusion, developer mode is an indispensable tool for iOS developers looking to test and debug applications effectively on physical devices. The hands-on experience allows you to understand how your app behaves in the wild, reveals performance bottlenecks, and offers insights that emulators cannot. So far, we've learned how to enable developer mode, the steps for running apps directly on devices, implementing network requests, building UI components using SwiftUI, and handling permissions for device functionalities such as the camera. As you become more comfortable with utilizing developer mode, you will find that it significantly enhances your development workflow. Remember, effective debugging and testing lead to robust applications that provide a great user experience. Now get out there, enable developer mode, and start testing those applications on your iOS devices. Happy coding! Understanding developer mode in Xcode is crucial for anyone involved in iOS app development, especially with the recent updates from Apple. Developer mode, introduced during WWDC 2022, is a game changer for developing apps on devices running iOS 16 or greater. It allows developers to install, run, and debug their applications seamlessly on real devices, which enhances both app performance testing and user experience optimization. So far, we've learned about the significance of developer mode in iOS app development, which enables testing and debugging on physical devices. We explored how to enable developer mode and the steps necessary to run apps directly on iOS devices using Xcode. Additionally, we discussed implementing network requests, creating interactive UI components with SwiftUI, and handling permissions for hardware features like the camera. As we continue, we will delve into more advanced functionalities and best practices for optimizing app performance and user experience. To kick things off, let's recap what developer mode really entails. When you enable developer mode on your device, it unlocks a plethora of potential for app testing. It's not just an option but a necessity for developers looking to ensure that their applications will perform well in real-world scenarios. Imagine being able to tweak your app, modify some UI components while it's running, and see the results instantaneously. Pretty slick, right? One of the first things we need to address is how to activate developer mode. On your iOS device, you need to head to Settings, navigate to Privacy and Security, and from there, enable developer mode. After you confirm with a restart, your device is all set to connect with Xcode. Your MacBook or whatever development machine you're using will recognize that the device is now in developer mode, allowing you to run apps directly on it. It's like laying down the red carpet for your app. No more awkward testing errors when deploying to the device. Now let's implement a simple SwiftUI view that fetches random jokes from an API. We start by defining a content view struct that conforms to the view protocol, introducing a state variable to store our joke. This state variable, initialized with a prompt text, is crucial as it allows the UI to reactively update whenever the joke is fetched. Next, we lay out our user interface using a vertical stack, featuring a text view to display the joke and a button that triggers the fetching process. When the button is tapped, the fetchJoke function is called. This function constructs a URL to a public API that serves random jokes. By leveraging URL session, we initiate a data task that asynchronously retrieves data from the API. Upon receiving data, we parse it using Swift's JSON decoder to extract the joke. Importantly, we ensure any UI updates occur on the main thread with dispatch queue main async, which maintains a seamless user experience by preventing potential UI freezes. Lastly, we define a custom codable struct, jokeResponse, to map the JSON structure into our Swift model, enabling easier data handling and manipulation. Now let's implement the following function that will enhance our app by effectively fetching a random joke while accounting for potential network delays. This method, fetch joke conditionally, initiates a network request to retrieve a joke from the Chuck Norris API. The first thing we do is create a URL object pointing to the API endpoint. We then set up a URL request and specify a timeout interval of 5 seconds. This timeout ensures that if the request stalls or the network is slow, it won't keep the user waiting indefinitely. Inside the URL session data task, we handle the response with a closure that checks for errors first. If an error occurs, we utilize the main dispatch queue to update our joke variable with an appropriate error message, communicating this back to the user. If data is received and can be decoded into our joke response object, we extract the joke and again, update the joke variable on the main thread. This structure allows our app not only to fetch data, but also to provide user feedback, maintaining a smooth user experience even under potential connectivity issues. Next, we will implement the necessary settings in the info.plist file to request access to the camera. This file is crucial for defining permissions in iOS apps, and for our joke app, we need to specify why camera access is necessary. By adding a key for the camera usage description, we inform users about the purpose for which the app requires their camera, such as capturing funny moments. This transparency is vital for user trust, as it clarifies the app's intentions and helps manage user expectations. Now let's take a look at how we can check and request camera permissions programmatically. We start by importing the AV Foundation framework, which is essential for working with hardware like the camera. Within a function, we check the current authorization status for video devices. If access is authorized, the app will proceed without any interruptions. If the status is not determined, we call for permission, prompting the user to grant access. We handle the cases of denial or restriction properly to ensure we address user feedback. This structured approach not only enhances usability, but also prevents app crashes due to unauthorized access. Now let's implement a simple image caching mechanism. The code defines a singleton class called ImageCache, which utilizes NSCache to store images in memory efficiently. This design pattern ensures that there is only one instance of the cache throughout the application, making it easily accessible. Next, we have two main functions in this class. The cached image for key method allows us to retrieve an image from the cache using a unique key. If the image exists in the cache, it returns that image for quick access. Otherwise, it returns nil, indicating that the image isn't available. This feature is particularly useful for minimizing network calls, as it allows previously fetched images to be displayed without re-downloading them. The store image for key function serves the purpose of saving an image to the cache with a corresponding key. By storing the image in memory, this approach conserves bandwidth and enhances the performance of our app, especially when dealing with frequently displayed images. Overall, implementing this caching strategy will improve the user experience by ensuring that images are loaded quickly and efficiently. Next, we will write a unit test using Swift's XCTest framework to validate the functionality of our joke fetching feature. This unit test is designed to ensure that when we make a network request to the joke API, it completes successfully without any errors and that we receive valid data in return. The test begins by creating an expectation that will help us synchronize our asynchronous network call. We then specify the URL of the joke API endpoint and initiate a data task using URL session, shared data task. Inside the closure, we assert that there should be no error returned from the request by utilizing XCT assert nil. This step is crucial because it confirms that the network call executed smoothly. We also check that the data received is not nil, indicating that we successfully fetched something from the URL. Finally, we call expectation fulfill to signal that our expectation has been met, and then we wait for the expectation to be fulfilled with a timeout of 5 seconds, allowing us to manage the response time effectively. This testing approach helps ensure that our app remains reliable, catching potential issues before they reach users. As we wrap this up, I hope you can see the undeniable value developer mode brings to your app development process. From testing and debugging on physical devices to managing permissions and optimizing performance, the tools and practices we covered empower you as a developer. Remember, iterative development along with rigorous testing will lead to a smoother user experience and ultimately, a successful app. Keep your devices up to date, enjoy the perks of developer mode, and happy coding. The Swift programming language is a powerful tool for developing iOS applications, and one of the best ways to learn it is through a hands-on approach using Swift playgrounds. In this session, we'll dive into the fundamentals of Swift, focusing on simple values and types, and exploring how they are implemented in the language. So far, we learned about the importance of developer mode in iOS app development, enabling testing and debugging on physical devices. We discussed how to activate developer mode, run apps, and manage network requests while simulating various network conditions. Additionally, we covered permission handling for hardware features and best practices like continuous testing and writing unit tests to enhance app reliability. Now we will talk about the core aspects of Swift and how we can leverage Swift playgrounds to make learning interactive and fun. Let's get started by opening Swift Playgrounds. If you haven't downloaded it yet, it's available on the App Store for iPad and Mac. Once you have it installed, launch it and prepare to enter a vibrant world where learning Swift becomes a visual adventure. Swift Playgrounds offers a unique way to experience programming with immediate feedback as we write our code. Now let's explore how to declare and use integer variables in Swift. First, we can explicitly specify the type of the variable by using the syntax var age int equals 25. Here, we've declared a variable named age, assigned it the type int, and initialized it to 25. This approach not only clarifies our intent, but also ensures type safety. However, Swift's type inference feature allows us to skip type declaration by simply writing var age equals 25, and Swift will automatically determine that age is of type int. This succinctness is one of the beautiful aspects of the language. Next, let's see how we can print the value stored in age. We use string interpolation along with the print function to achieve this. By writing print myAge is \age, the value of age is seamlessly inserted into the string, making it readable and easy to follow. When running this code in Swift Playgrounds, you'll immediately see the output, which exemplifies how Swift provides instant feedback, enhancing the learning experience while you work with basic data types. Next, we will write the following code to explore how to declare and use floating point numbers in Swift. We start by defining a variable named pi of type double, which allows us to represent the mathematical constant with greater precision due to its 64-bit structure. We initialize pi with the value of 3.14159, a commonly used approximation of pi, which is essential for calculations involving circles and mathematics in general. Additionally, we introduce a variable called temperature of type float, initialized to 36.6. This variable represents body temperature in degrees Celsius. The choice of float here is appropriate considering that this value does not require the higher precision of a double. To display these values, we use the print function. We format our output using string interpolation, which allows us to seamlessly embed the values of pi and temperature within a string. The output will clearly communicate these numerical values to us in a readable format, demonstrating the practical application of floating point numbers in Swift. This simple exercise emphasizes how we can work with different numeric types and showcases the flexibility of Swift for handling various data formats. Now let's declare our string variables. In Swift, strings are fundamental data types that allow you to work with sequences of characters. Here we create two variables, greeting, which holds the value hello, and name, which contains world. These variables will help us understand how to manipulate and combine strings effectively. Next, we will combine these strings using the plus operator to form a complete message. By concatenating greeting, a comma and space, and name, followed by an exclamation mark, we create a new variable called combine message. This showcases the simplicity of string concatenation in Swift, producing the output hello world when we print the combine message. Now let's explore multi-line strings, which are particularly useful for longer text blocks or formatted content. We create a variable multi-line string using triple quotation marks, allowing us to span the string across multiple lines effortlessly. When we print this variable, Swift will display the entire content as intended, preserving the line breaks. This feature is incredibly handy for managing longer strings and improves code readability. Now let's see how we can implement a Boolean to check if today is a weekday. In Swift, we can declare a Boolean variable called isWeekday, which can hold a value of either true or false. In this case, we initialize isWeekday to true, indicating that it is a weekday. Next, we use an if statement to evaluate the value of isWeekday. If the condition is true, the program executes the first block of code, which prints time to work, to the console, signaling that it is time for work or responsibilities. Conversely, if isWeekday is false, the else block will run, printing it's the weekend instead. This simple Boolean structure illustrates how conditional statements in Swift can help us control the flow of our applications based on specific criteria. To deepen your understanding, try toggling the value of isWeekday and observe how the output changes, showcasing the dynamic nature of Boolean logic in programming. Next, we will write an array of integers to illustrate how we can store multiple values in an ordered format. In Swift, we denote an array by using square brackets, and in this example, we create an array named numbers that holds the integers from 1 to 5. This structure allows us to keep track of collections of numbers efficiently. Now let's see how we can append a new number to this array. We use the append method to add the integer 6 to our numbers array. This method is convenient as it dynamically increases the size of the array to accommodate new values. After adding the number, we print the entire array to see the updated list of integers, which now includes 6 as the last element. Next, we will explore dictionaries, another vital collection type in Swift. We will create a dictionary called person, which stores related data as key-value pairs. In this case, the keys are name and age, and they correspond to the values John and 30, respectively. This structure allows easy retrieval of values by their associated keys, promoting organized data management. We will demonstrate this by printing out the person's name and age, showcasing how to access these values from our dictionary. The displayed pie chart titled Key Concepts in Swift Programming Language allocates relative emphasis across 6 core concepts: integers, doubles, strings, booleans, arrays, and dictionaries. Quantitatively, integers dominate the chart, accounting for roughly 2/3 of the total, 67.3%, indicating a strong emphasis on whole number operations and integer-based examples in this lesson. Arrays form the next largest segment at about 13.5%, highlighting that ordered collections are a primary data structuring focus after numeric types. Doubles, floating point numbers, contribute around 8.4%, showing moderate attention to numeric precision in decimal values. Dictionaries represent approximately 5.4% of the chart, which signals that keyed, unordered collections are covered but with less emphasis than arrays. Finally, strings and booleans each occupy small but visible slices, 7% each, reflecting their essential role in handling textual data and conditional logic despite being smaller topics in proportion. From this distribution, we can conclude that the lesson centers on numeric types, especially integers, and collection handling arrays, while still including critical support topics, floating point math, dictionaries, strings, and Boolean logic that complete a practical foundation for Swift programming. Now let's take a look at optionals in Swift, a powerful feature that allows us to work safely with variables that may or may not contain a value. In our first line, we declare an optional string variable named optional value and initialize it with the value hello optional. Notice the appended to the type string, indicating that optional value can be nil, which enhances the safety of our code by preventing unexpected crashes. Next, we will write the following code that demonstrates how to safely unwrap this optional using optional binding. Here, we use an if-let statement to check if optional value has a value. If it does, we assign that value to a new variable called unwrapValue and print it out. This approach allows our program to gracefully handle scenarios where data might be missing, showcasing the flexibility of Swift when managing optional values. If optional value is nil, the else clause executes, printing no value found. This ensures our program remains reliable, even in cases where values aren't present. Now let's see how we can implement control flow statements in Swift, which are essential for determining how our programs respond to various situations. First, we have a for loop that iterates through each element in the numbers array. Within the loop, we print the current number being processed, utilizing string interpolation to seamlessly embed the variable's value into the printed string. This allows you to see how each number is handled dynamically during execution. Next, we'll implement a while loop to achieve a similar effect but in a different manner. Here, we maintain a count variable that starts at 0 and continues to increment until it reaches 5. Within the loop, we print the current count, showcasing how to manage repetition using a condition that determines when the loop should stop. Both of these control flow statements enable us to automate tasks efficiently, making our code more versatile and responsive to different conditions, which is fundamental for creating interactive applications. Finally, as we conclude this session, keep in mind that mastering values and types in Swift is an essential foundation for building applications. Swift Playgrounds is a fantastic way to learn these concepts in an interactive environment, enhancing your coding skills with immediate results. Now that you've learned about basic values, types, optionals, and control flow statements, you have the tools needed to begin writing more complex Swift code, setting the stage for your next adventures in iOS development. As you move forward, explore these concepts further on your own or continue to challenge yourself with new projects. Happy coding! Congratulations, you have successfully run your app on an actual iOS device. This milestone is significant in your journey as an iOS developer. Today, we will explore how to take your Swift applications from the simulator to a real device, unlocking a whole new level of development experience. We'll also touch upon some important configurations and debugging techniques to ensure your app runs smoothly. So far, we learned that the Swift programming language is essential for iOS app development, and hands-on engagement through Swift Playgrounds facilitates learning its core concepts, including values and types. We explored how to declare and use integers, floating-point numbers, strings, booleans, and collections like arrays and dictionaries, all while emphasizing type safety. The importance of optionals for safe value handling and control flow statements for dynamic program behavior was also highlighted. This foundational knowledge equips you to write more complex Swift code and enhances your iOS development skills. Now, we will talk about how to set up your device for development and what steps to follow to run your app on your real iOS device. To get started with running applications on an actual iOS device, there are a few prerequisites and steps you'll need to complete. First, ensure that you have a valid Apple developer account. While you can run apps on a device with a free Apple ID, having a paid developer account grants you access to a wider range of features, including app distribution and access to beta software. If you don't have a developer account yet, you can easily sign up on the Apple developer website. Once you have your developer account, the next step is to set up your iOS device for development. Connect your iPhone or iPad to your Mac using a USB cable. You should see a prompt on your device asking if you trust this computer. Make sure to select Trust. After that, launch Xcode on your Mac and navigate to the Window menu. From there, choose Devices and Simulators. You should see your connected device listed. Select your device from the list and make sure that you have enabled the development mode. If prompted, follow the on-screen instructions to complete the setup. Once your device is configured for development, you will now be able to run your iOS apps directly on it. Now let's implement the following code to create a simple Hello World application using SwiftUI. This code begins by importing the SwiftUI framework, which provides tools to build user interfaces in a declarative style. Inside the content view struct, we define the main body of our app with a computed property, body, that returns a view. Within this body, we create a text view that displays the string Hello World, styled with a large font using the font large title modifier, ensuring it's visually prominent on the screen. To enhance the appearance, we add some padding around the text using the padding modifier, which improves spacing and visual readability. The structure also includes a content view preview struct, allowing us to preview the view in Xcode's design canvas. This helps in visualizing UI changes without running the app on a device. By writing this simple code, we lay the foundation for demonstrating how to build and deploy an app, showcasing essential SwiftUI features while engaging with user interface elements easily. The figure titled Stages of iOS App Development is a bar chart that maps 4 sequential stages: concept, development, debugging, and deployment, against their respective completion percentages: 20%, 60%, 80%, and 100%. The chart shows a clear, monotonic upward progression. The concept stage sits at a relatively low 20% completion, indicating early stage planning and definition. Development jumps substantially to 60%, identifying it as the phase where the majority of implementation work occurs, a 40 percentage point increase from concept. Debugging then rises to 80%, signaling that a significant portion of effort is devoted to fixing issues and refining behavior after core features are implemented. Finally, deployment reaches 100%, representing the finalization and release of the product. From these values, we can conclude that effort and progress accelerate after concept, with development being the most intensive phase, followed by an important but smaller incremental investment in debugging before reaching full completion at deployment. This pattern highlights two practical lessons for the workflow described in this chapter. Allocate substantial time and resources to the development phase, where most features are built, and plan for a meaningful debugging phase on real devices, where issues that do not appear in the simulator are often uncovered before targeting deployment as the final 100% milestone. Upon running the app, you may need to select your device in the target drop-down menu to ensure the app runs on the actual iOS device rather than the simulator. If everything is set up correctly, Xcode will build the app and install it on your device. You'll see an alert on your device that requests permission to run an app from an unverified developer. Since this is a development app, you can go to your device's settings, navigate to General, then Device Management, and select your Apple ID. From there, tap Trust to allow your app to run. After granting permission, you will be able to find the Hello World app on your home screen. Tap on it and there you go. You've just run your first iOS application on an actual device. It's amazing how quickly you can shift from code to functionality in your hands. Now let's implement a feature that allows users to enter their names, enhancing user interaction in our app. We will begin by introducing a text field, which provides a space for users to input text. This text field will be bound to a @state property named userInput, ensuring that any text entered is stored effectively and can be updated dynamically. As users type in their names, the entered value is automatically reflected in the userInput variable. To trigger an action when the user clicks the Say Hello button, we will define a button action that prints a personalized greeting to the console. When the button is clicked, it will access the current value of user input and display Hello name in the console. This demonstrates not only how to capture user input, but also how to respond to user actions in real time. By structuring our UI with a vertical stack, VStack, we ensure that the text field and button are neatly arranged. With proper padding applied for spacing, the user experience is made more pleasant. Remember, after implementing this code, it's important to run the app again on your device to see these changes in action. As you continue your journey with iOS app development, debugging becomes an essential skill. Debugging allows you to pinpoint issues within your code and optimize performance. Xcode provides powerful tools for this purpose. Let's briefly explore how to debug your app while it runs on your actual device. When you run your app, Xcode will automatically attach a debugger. If your app encounters an issue, it will stop execution at the point of failure, enabling you to investigate. You can set breakpoints in your code by clicking the line number in the editor pane where you suspect an issue might occur. When the breakpoint is hit, Xcode will pause execution, allowing you to inspect variable values, review the call stack, and examine the console output. For example, if you wanted to see the value of user input while the app is running, you could set a breakpoint inside the button action. Clicking the button would pause execution at that breakpoint, and you could then check the value in the debug area. This debugging method is incredibly valuable for troubleshooting issues that arise when running apps on a real device, where behavior might differ from the simulator due to hardware differences or real-world conditions. To conclude, running your first iOS app on an actual device is a rewarding experience that grants you insights into how your app interacts with the real world. You've learned essential steps to configure your device, create a simple app, and implement user input. You also have seen how debugging tools in Xcode can help you troubleshoot and optimize your applications. In essence, you've taken an essential leap into iOS development. As you build upon this experience, remember to explore new features, integrate functionalities, and keep expanding your knowledge of Swift and iOS frameworks. With continued practice and exploration, you will create amazing applications that can make a difference in users' lives. So there you have it, you've successfully transitioned from coding in Swift to deploying apps on your actual iOS device, embodying the core essence of what it means to be an iOS developer. Keep experimenting, keep learning, and embrace the journey ahead. Running your app on an actual iOS device is an exciting and crucial step in your journey as an iOS developer. Today, we will explore the importance of deploying applications to real devices, discussing not only how to run your app on an actual iPhone or iPad, but also the benefits that come with it. So far, we learned that successfully running an iOS app on a real device is a key achievement in your development journey. We covered the necessary steps to set up your device for development with a valid Apple developer account and how to build and run a simple Swift application. Additionally, we discuss the importance of debugging techniques to identify and resolve issues that may arise during development. This foundational experience prepares you for further exploration and enhancement of your iOS development skills. First, let's dive into the advantages of testing on a real device as opposed to using the iOS simulator. The simulator is great for initial tests and debugging, but it's important to remember that it can't replicate all the features of real hardware. For example, consider the camera functionality. If your app utilizes the camera for taking pictures or scanning QR codes, the simulator won't help you with that test. Similarly, any features related to hardware sensors, GPS location, or the gyroscope will not perform accurately in the simulator environment. By testing on real devices, you can capture the nuances in behavior, performance, and presentation that the simulator simply cannot offer. The displayed chart titled Advantages of Running iOS Apps on Real Devices versus Simulator presents two labeled segments: real device testing at 80% and iOS simulator testing at 20%. The dominant pattern is a 4-to-1 preference for real device testing over the simulator, indicating that the majority of advantage or preference, as represented, clearly favors using actual hardware. From this distribution, we can draw several conclusions that tie directly into the lesson. Real devices are the primary source for validating hardware-dependent features, camera, sensors, GPS, gyroscope, for measuring true performance and battery impact, and for observing authentic gesture interactions. The simulator, while useful, accounts for a smaller but meaningful portion of testing suited to rapid iteration and early-stage debugging. Practically, the chart suggests that most testing resources and time should be allocated to real devices, especially for final acceptance testing and performance profiling, while the simulator remains valuable for quick checks and initial development cycles. Preparation is key. Make sure your physical device is configured properly for development. It's essential to have the latest version of iOS installed, enabling you to test your app against the most current features and functionalities. Remember, you need a valid Apple developer account to build and deploy apps to a real device. If you don't have one, you can sign up on the Apple developer website, where you will need to register and obtain a development certificate. Now let's talk about connecting your iOS device to your development environment. With your iPhone or iPad in hand, connect it to your computer via USB. Open Xcode and head to the Xcode menu to navigate to Window and select Devices and Simulators. Your device should appear in the list, confirming that your connection is successful. You may need to unlock your device and choose Trust this computer to establish the connection. Once you trust the computer, Xcode should recognize your device and allow you to build and run your app directly onto the device. Now let's see how we can implement our Hello World functionality in the View controller. We start by creating a new class, View Controller, which inherits from UI View Controller, the foundational class for view management in iOS applications. Within this class, we override the ViewDidLoad method. This method is called after the View Controller has loaded its view hierarchy into memory, making it the perfect place to set up our user interface. First, we set the view's background color to white, ensuring our label will stand out clearly. Now let's take a look at how we create the label. We instantiate a UI label and set its text property to Hello World, centering the text and choosing a font size of 24 for visibility. Importantly, we disable the Translates Auto-resizing mask into Constraints property to use Auto Layout for positioning. Next, we add the label as a subview to the main view. To center the label in the view, we create constraints using NSLayout constraint activate, aligning it both horizontally and vertically. This approach ensures our label always remains centrally positioned on the screen, adapting to different device sizes and orientations, crucial for providing a consistent user experience. Now let's implement the following enhancements to our Hello World app by incorporating user interaction through gestures. We begin by overriding the ViewDidLoad method, where we initially set up our label. The label is created and configured to display Hello World at the center of the screen with a larger font size for visibility. To enable user interaction with the label, we introduce a UI Tap Gesture Recognizer. This gesture recognizer is initialized with a target action mechanism which points to the label tap function that we will define. By setting Label as User Interaction Enabled to True, we allow the label to respond to touch events. With the gesture recognizer added to the label, the app can now respond to tap gestures. When a user taps the label tap function is invoked, triggering a print statement that provides immediate feedback in the console. This interaction illustrates how developers can refine app usability on physical devices, ensuring that the app feels intuitive and responsive. This direct user engagement is vital for creating a smooth and enjoyable experience. Now let's take a look at how we can implement a tap gesture to respond to user interactions within our app. In the provided code, we define a function called label_tapped, which will be invoked when the user taps on a label. This function calls potentially risky operation that performs an operation which could potentially lead to a runtime crash if the return value is not handled properly. By implementing this function, we allow ourselves to investigate the outcome of the risky operation to ensure stability in our app. We then print a message to the console indicating that the label was tapped, along with the value returned from the operation. It's important to understand that wrapping such risky operations within an interactive user gesture highlights the necessity of careful error handling. Next, we will explore how to utilize debugging tools in Xcode to set breakpoints effectively in this function. By placing a breakpoint on the line where potentially risky operation is called, we can pause execution and inspect values in real time, allowing us to finely tune our approach to ensure a stable user experience. This technique is a fundamental aspect of debugging while developing on a real device, as it provides crucial insights into the app's behavior during execution. Let's not forget about the important aspect of app performance. Running your app on a real device allows you to evaluate performance metrics accurately. Are there any noticeable lags when running animations or loading resources? How is the battery impact when your app is executing heavy tasks? The simulator won't provide you with an accurate representation of these critical aspects. Consider using instruments to profile your app's performance metrics. With instruments, you can monitor everything from CPU usage to memory leaks, providing essential feedback on your app's performance benchmark. To use instruments once connected to your iOS device, you can select your app in Xcode and navigate to Product Profile. From there, it opens up various templates such as Time Profiler, Core Animation, and Memory Allocations. Feel free to dive deep into whichever template aligns with your current needs. For instance, using the Time Profiler can help identify functions in your code that are taking too long to execute, giving you actionable insights to optimize your app. Now let's see how we can implement responsive layouts based on device types using the size classes in Swift. In the provided code snippet, we start by checking the device's horizontal size class. If the size class is identified as compact, which typically corresponds to smaller devices like iPhones, we call the setUpCompactLayout function. This function would contain the necessary adjustments to ensure the user interface is optimized for a compact screen. On the other hand, if the size class is not compact, it indicates that the device has a regular width, such as an iPad, leading us to invoke the setUpRegularLayout function. This modular approach allows us to define distinct layouts tailored to different screen sizes, ensuring that the app's appearance and usability remain consistent across various devices. Utilizing size classes not only makes your app more adaptable, but also enriches the user experience by displaying the interface in a way that feels native to the device being used. This strategy is crucial for accommodating the diverse array of iOS devices available today. Overall, running your app on an actual iOS device is an essential step in your development process. It provides crucial insights, accurate user interactions, expanded testing opportunities, and performance metrics that the simulator cannot match. As you embark on this journey, remember to leverage the power of real hardware, utilize debugging tools, and continue fine-tuning your app to provide the best experience for your users. In conclusion, so far we've covered the foundational knowledge needed to successfully run your app on a real device, from setting up your device for development to hands-on testing, debugging, and optimizing your app for different screen sizes. Next, we'll be exploring advanced development techniques, diving deeper into integration with APIs, and examining how to leverage external services to take your app to the next level. Keep those development dreams alive, and let's get coding. Now let's take a look at how we can create our first variable in Swift. In this example, we declare a variable called greeting and assign it the string value hello Swift Playgrounds. The keyword var indicates that this variable is mutable, meaning we can change its value later if needed. Once we have our variable set up, we use the print function to output its value to the console. This allows us to see the result of our code immediately, showcasing one of the key features of Swift Playgrounds, real-time feedback on our coding efforts. When we run this snippet, the message hello Swift Playgrounds appears right away, reinforcing how Swift's interactive environment enhances learning by providing immediate results and encouraging experimentation. By working with variables in this way, we begin to understand the foundational concept of storing and manipulating data in our programs. As we progress further, we will explore more complex types and operations to deepen our understanding of Swift programming. Now let's see how we can implement constants in Swift. To declare a constant that won't change throughout the program, we use the let keyword. In our example, we declare pi and assign it the value of 3.14159. By using let, we specify that this value is immutable, meaning if we attempt to modify pi later in our program, it will result in a compilation error. This characteristic of constants is particularly beneficial when working with values that are meant to remain fixed, such as mathematical constants. Following this declaration, we utilize the print function to output the value of pi. When executing this line of code in Swift Playgrounds, you will see the number displayed immediately. This not only reinforces the concept of constants, but also showcases the ease and clarity Swift offers in handling fixed values, promoting good coding practices by discouraging unintended modifications. Using constants like pi helps maintain the integrity of important data throughout your program's execution. Next, we will write the following code to declare an integer variable and demonstrate how to use it effectively. Here, we define a variable called age with the type int, initializing it with the value 30. By specifying the type, we ensure that our variable can only hold integer values, reinforcing Swift's strong type safety. After defining age, we utilize string interpolation to create a dynamic message when printing. The print function outputs the string, "I am 30 years old," seamlessly incorporating the value of age into the message. This feature is particularly powerful in Swift as it allows for more readable and maintainable code when incorporating variable content into strings. Now let's see how we can implement a similar approach for floating point numbers using the double type. In this case, we declare a variable called height and assign it a decimal value of 5.9. By using double, we can accurately represent measurements with decimal points. As before, we perform string interpolation in the print statement to output the message, "My height is 5.9 feet." This demonstrates how Swift effectively handles both integers and floating point numbers, serving various needs in programming while maintaining clarity in code execution. Now let's see how we can combine strings using variables to create meaningful text. In this example, we declare two string variables. First name, assign the value John, and last name, assigned Doe. By combining these two variables, we create a new variable called full name that concatenates the first name, a space, and the last name together. This showcases string manipulation in Swift, which is a fundamental skill for creating more complex outputs. After forming the full name, we utilize string interpolation within the print statement to dynamically include the value of full name in the output message. When we execute this code, it will display full name, John Doe, demonstrating not only how to concatenate strings, but also how to effectively use print statements to convey information. Next, let's take a look at another practical use of strings, where we can implement string interpolation to present dynamic content. In a new example, we create a variable favorite color to store the value blue. This time, we print a statement that includes this variable, resulting in the output, "My favorite color is blue." This approach highlights the power of string interpolation, allowing us to create user-friendly messages that incorporate variable values seamlessly. Now let's take a look at how Booleans function in Swift, as they play a crucial role in controlling the flow of our code. We begin by declaring a variable named isLearningSwift, which we set to true. This variable represents a condition we can check in our program. The following if statement evaluates this Boolean value. If it is true, the program executes the code within the first block, printing an encouraging message to keep up the good work. Conversely, if the variable were false, the else block would trigger, suggesting that it might be time to start learning Swift. This simple yet powerful structure illustrates how decisions are made in programming based on Boolean conditions. Understanding how to use Booleans effectively allows you to implement logic that can adapt to different scenarios, making your applications interactive and responsive to user needs. As you practice using Booleans in your projects, you'll become more adept at controlling your code's behavior, enhancing the overall functionality of your programs. Now let's see how we can implement a personalized greeting program using variables in Swift. In this code, we first import the UI Kit framework, which is essential for iOS applications, although it may not be strictly necessary in this simple playground example. Next, we declare a constant called username and assign it the string value Alice. This showcases how to use the let keyword to define a constant, indicating that this value won't change during the program's execution. We then declare another constant, userAge, of type int and set it to 25. This highlights the importance of defining types in Swift, ensuring clarity and type safety. Following that, we create a variable named greeting that utilizes string interpolation to weave together the username and userAge into a friendly message. This demonstrates how powerful and flexible string interpolation can be in Swift, allowing us to seamlessly insert variable values into strings for dynamic text generation. Finally, we print the greeting to the console, allowing the user to see their personalized message, reinforcing the concept of user interaction in Swift applications. Now let's explore how Swift enforces type safety, a crucial feature that helps to maintain the integrity of our code. In the following example, we declare a variable named score and specify its type as int, which means it can only store integer values. Swift's strong typing requires us to be explicit about the data type we intend to use, thereby reducing the chances of errors during runtime. Next, we attempt to assign a string value, 90, to the score variable. However, this will result in a compile time error since the string type is incompatible with the integer type of score. This strict enforcement of type rules not only catches mistakes early, but also ensures that our program behaves predictably. By utilizing this type safety feature, we can foster more reliable and robust code, effectively minimizing logical errors as we develop our applications. It's a fundamental part of what makes Swift a powerful language for developers, encouraging best practices right from the start. Now let's explore the concept of optionals in Swift, which allows variables to hold a value or represent the absence of a value, indicated by nil. We begin by declaring an optional string variable, user nickname, and initialize it to nil. When we print user nickname, Swift gracefully handles the absence of a value, displaying nil. This illustrates how optionals promote safety by ensuring we consciously account for the possibility of missing data. Next, let's see how we can assign a value to user nickname. Here, we give it the string ace and proceed to print it. Notice the use of the exclamation mark when printing user nickname. This syntax, known as unwrapping, is a way of telling Swift that we're confident this optional contains a value. However, using on a nil optional would lead to a runtime error. Thus, it's crucial to handle optionals cautiously to avoid unexpected crashes in your programs. Through this example, we've highlighted how Swift encourages careful programming practices around handling potentially absent values. Now let's take a look at how we can work with implicitly unwrapped optionals in Swift. Implicitly unwrapped optionals are particularly useful when you can guarantee that a variable will have a value after it has been initialized. In the code snippet, we declare a variable called userAge of type int, initialized with a value of nil. At this point, userAge is an optional that we expect to have a value later. Next, we assign 30 to userAge, which signals that it is now safe to use without additional checks. After the assignment, we employ string interpolation to print a message that includes userAge. The beauty of implicitly unwrapped optionals lies in their fluidity. Although initially declared as optional, once they hold a value, they can seamlessly be used as if they were non-optional throughout the code. This approach simplifies handling of optionals, provided you ensure a value is assigned before any operation that relies on it. However, it's important to use them cautiously to preserve the integrity of your code and avoid potential runtime errors. Now let's take a look at how we can work with arrays in Swift to manage collections of data. In this example, we start by declaring an array named fruits, which is specifically designed to hold strings representing different types of fruits. The syntax string indicates that this array will only contain string values, showcasing Swift's type safety. Next, we initialize our fruits array with 3 elements: apple, banana, and cherry. This sets the foundation for our collection to grow. Now let's implement the append method, which allows us to add new elements to our array dynamically. Here we append orange to the existing array. This flexibility demonstrates one of the key features of collections in Swift. Arrays can easily expand as needed. Finally, we use the print function to output the contents of the fruits array. After executing this code, you will see that the array now includes the newly added fruit, resulting in the output: apple, banana, cherry, orange. This shows how effortlessly we can manage lists of related data using Swift's powerful array capabilities. The bar chart titled Key Concepts of Swift Programming displays 5 vertical bars labeled along the x-axis as variables, constants, data types, optionals, and collections, with the y-axis labeled importance %. Each bar has a numeric label above it showing its percentage. Variables at 35%, constants at 25%, data types at 20%, optionals at 10%, and collections at 10%. From these values, we can draw clear conclusions about emphasis. Variables are shown as the single most emphasized concept at 35%, and when combined with constants, 25%, they constitute 60% of the chart's indicated importance, underscoring the central role of understanding mutability and immutability early on. Data types at 20% remain a substantial portion, signaling that mastering types int, double, string, bool, etc. is the next priority. Optionals and collections, each at 10%, are represented as important but secondary topics relative to variables, constants, and basic types. This suggests a recommended learning order where one becomes comfortable with variables, constants, and data types before diving deeper into optionals and collection manipulation. The presence of explicit percentage labels above each bar also makes it easy to compare values precisely and see the relative gaps between concepts. Now let's take a look at how to iterate through the elements of an array using a for loop. The provided loop goes through each fruit in our fruits array, enabling us to perform actions with each element individually. As we go through the loop, we use string interpolation to construct a message that includes the current fruit's name, preceded by I like. This approach not only demonstrates the syntax for a for loop in Swift, but also highlights the usefulness of collections, showing how we can easily operate on each item within an array. By executing this loop, you'll generate personalized statements like I like apple, I like banana, and so on for each fruit in the array. This makes it clear how straightforward it is to interact with collections, allowing programmers to process multiple items efficiently. Utilizing such loops is fundamental when working with data in Swift, providing a solid foundation for more complex programming tasks. With this understanding, you're better equipped to manipulate arrays and implement similar logic in your own projects. Now let's take a look at dictionaries, which are an essential collection type in Swift used for storing key-value pairs. In this example, we declare a variable called capitals, specifying that it will be a dictionary with both keys and values of type string. We initialize this dictionary with 3 entries, the capital cities of the USA, France, and Japan. Next, we use the print function to display a formatted message that incorporates a value from the capitals dictionary. By referencing the key, France, we are able to retrieve the corresponding value, which is Paris. The syntax capitals France accesses this value, where the exclamation mark signifies that we are forcefully unwrapping the optional result. This means we're asserting that there is a valid value for the key, France, crucial in ensuring our code doesn't run into issues if the key were absent. This straightforward lookup illustrates how dictionaries in Swift provide a powerful way to manage and retrieve complex data efficiently, while maintaining a clear relationship between each key and its respective value. In conclusion, today we ventured into the fundamental concepts of the Swift programming language using Swift playgrounds. We explored how to use variables and constants, understood data types like integers, strings, and booleans, and delved into the powerful concepts of optionals and collections. By engaged in small examples, we've not only learned the syntax, but also how to apply these concepts practically in your coding journey. As you continue to explore Swift, remember that practice is key. With time, you'll start to feel more comfortable and confident in your coding abilities. So keep experimenting and don't hesitate to dive deeper into the features Swift has to offer. Happy coding! Today we're diving into the exciting world of Xcode and iOS development. Xcode is Apple's integrated development environment, IDE, that simplifies the process of building apps for iOS, macOS, watchOS, and tvOS. We'll explore how to set it up, its key features, and how it interacts with Swift, bringing your app ideas to life. So far, we learned that Swift programming, particularly in Swift playgrounds, allows for an interactive and enjoyable learning experience. We've discussed key concepts such as variables, constants, data types, optionals, and collections, and how they contribute to building robust applications. Additionally, we emphasized the importance of type safety and the syntax differences between mutable and immutable values. Continue practicing these fundamentals to strengthen your coding skills and confidence in Swift. Now, we will talk about how to download and install Xcode and what features it provides to enhance your development workflow. The displayed bar chart titled Comprehensive Overview of Xcode and iOS Development presents importance ratings on a 1-10 scale for 8 core topics. Variables 8, constants 7, data types 9, optionals 6, collections 8, type safety 9, debugging 5, and testing 7. Key patterns visible are data types and type safety receive the highest ratings, both 9, indicating they are perceived as the most critical concepts. Variables and collections are rated strongly 8, showing their role as foundational constructs. Constants and testing share mid-level importance 7, reflecting steady emphasis on immutability and verification. Optionals are slightly lower 6, highlighting a moderate learning priority. And debugging scores lowest 5, suggesting it is considered less central in initial learning though still necessary. From these values, one can conclude that the lesson should prioritize deep understanding of type-related concepts, data types and type safety, reinforce core structures, variables, and collections, and ensure learners allocate time for testing practices and optional handling, while incorporating debugging techniques as supportive skills to resolve issues that arise during development. First, let's get started with downloading and installing Xcode. Xcode can be obtained from the Mac App Store or downloaded directly from the Apple developer website. Installing it from the App Store ensures you get the latest stable version, which includes all the necessary tools to kickstart your iOS development journey. To download Xcode from the App Store, simply open the App Store application on your Mac, search for Xcode, and click the Get or Install button. Depending on your internet speed, this may take a bit of time, as Xcode is quite large. After installation, launch Xcode, and you'll be greeted with a welcome screen where you can create a new project or explore existing ones. The first project you may want to build is a simple application. Let's create a basic Hello World app to familiarize ourselves with the interface. After launching Xcode, select Create a new Xcode project. In the template selection, choose App under the iOS tab and click Next. Fill in your product name, team, organization name, and organization identifier. Be sure to select Swift as your programming language. Now click Next, choose a location to save your project, and hit Create. Now let's see how we can implement our user interface using SwiftUI. The first line imports the SwiftUI framework, which is essential for building modern user interfaces in iOS apps. We define a structure called Content View that conforms to the View protocol. This is necessary for any SwiftUI view. Inside this structure, we declare a computed property named Body, which must return some kind of view. Within the body, we utilize a text view to display the message Hello World. This gives our app a basic label on the screen. To enhance the visual appeal, we add modifiers such as padding to create space around the text, applying a font, large title, modifier to make the text larger and more prominent, and setting the text color to blue using foreground color, blue. Furthermore, we have a structured preview provider named Content View Previews, which allows us to visualize our user interface in the canvas or preview section of Xcode. This live preview helps us see the changes without needing to run the app constantly, streamlining the design process as we develop our interface further. Now let's implement a simple app that changes text when a button is clicked using SwiftUI. In the content view, we begin by defining a state variable, message, initialized with the text Hello World. This variable will hold and update the text displayed on the screen, allowing the app to respond to user interaction. Next, we structure the user interface within the body property, which returns a vertical stack or VStack. This layout arranges elements vertically. Inside the VStack, we add a text view that displays the content of the message variable, complete with padding and styling for enhanced appearance. Now let's write a button that triggers an action when tapped. The button is created with an action that updates the message variable to button clicked each time it is pressed. This dynamic interaction is crucial for making your app responsive. Finally, the button itself includes a text label and is styled with padding and color, creating an inviting interface. With this, we have successfully connected UI elements and states, making the app interactive. Now let's see how we can enhance our button's functionality in the application. We'll modify the button's action to include a statement that updates the message variable with the text button clicked whenever the button is pressed. This dynamic change enables the user to see immediate feedback, enhancing interaction within the app. Along with updating the message, we will also incorporate a print statement directly after this assignment. This allows us to output the current value of message to the console, which is a useful debugging tool. By inspecting the console, we can confirm that the button action is correctly linked and that the expected message is printed every time the button is clicked. In this way, the combination of updating the state and printing to the console allows for a more robust interaction model within our app. By observing the console output, we gain insights into the program's behavior, making it easier to identify any issues that may arise during development. This practice of utilizing both state changes and console output is a valuable technique for debugging in SwiftUI applications. Now let's implement a simple test case to verify the initial state of our application. We start by importing the Xcode framework, which provides the necessary tools to write unit tests, along with our apps module to access its components. In the test class, which inherits from Xcode case, we define a function named testMessageDefault. This function will be responsible for creating an instance of our content view and checking whether the message property is correctly initialized. We use the XCT_assert function to assert that content_viewMessage matches the expected string, hello world. If the assertion holds true, it confirms that our app's default message is set appropriately when the view is initialized. Testing is crucial to ensure that our application behaves as expected, especially as we continue to add features and functionalities. Once you have written the test, you can run it from the Xcode menu to validate your code. If all the tests pass, it indicates that our message initialization works properly, giving us confidence as we build upon this foundation. Finally, let's discuss deploying your app. Once you've built and tested your application, you can distribute it through the App Store or for development purposes, test it on a physical device. To run your app on an iPhone, connect the device to your Mac. Ensure that your iPhone is selected in the device drop-down menu in Xcode. Before deploying to the App Store, you'll need an Apple developer account. Sign up and enroll for the program to access App Store Connect. This platform handles app submissions, analytics, and revenue reports, among many others. Before submission, you will also need to configure your app's metadata and take care of any App Store requirements like screenshots and a compelling description. This is where your creativity should flow. In summary, you've now grasped how to download and install Xcode, create your first iOS application, utilize SwiftUI for your user interface, debug, test, and finally prepare your app for deployment. The world of iOS development is vast, filled with opportunities to explore and create. Keep practicing these concepts, play around with more features in Xcode, and don't hesitate to try building more complex applications as your confidence grows. The skills you've built so far in Swift will serve as a strong foundation as you delve deeper into the intricacies of iOS development. Good luck and happy coding. Understanding developer mode and trusting your iOS app certificate is crucial for embarking on your journey into iOS development. With the rapid advancements in technology, Apple introduced developer mode during the Worldwide Developers Conference in 2022, making it essential for developers working with iOS 16 or newer devices to ensure seamless installation, running, and debugging of their applications. So far, we learned about the importance of Xcode in developing iOS applications, where we created our first project, designed a Hello World app with SwiftUI, and enhanced it with interactive features using buttons and state management. Additionally, we dived into debugging techniques, highlighting the significance of thorough testing to maintain code reliability. Now we will cover developer mode, its significance, how to trust your iOS app certificate, and how it can impact your development process. Developer mode is a feature that enables developers to install and test apps directly onto their devices from Xcode without needing to go through the usual App Store submission processes. When you want to run an app on your iOS device, your device must trust the app certificate. This security measure prevents unauthorized apps from being installed, thereby safeguarding user data and device integrity. Engaging with developer mode is the gateway to realizing the full potential of your development capabilities, as it allows you to test your apps in real-world conditions. Setting it up is simple. To enable developer mode on your device, you first need to connect your iPhone or iPad to your computer via USB cable. After launching Xcode, you must navigate to the Preferences menu and select the Devices and Simulators tab. You'll notice that your connected device appears on the list. Click on the Use for Development button. Voila, your device is ready to go. The figure titled Impact of Developer Mode and Certificate Trust on iOS Development presents a pie chart divided into 4 labeled slices with percentages. Enabled Developer Mode 25%, Trusted Certificate 40%, Apps Running Smoothly 20%, and Debugged Issues 15%. The largest portion is the Trusted Certificate slice at 40%, indicating that among the factors shown, establishing trust in the app signing certificate is the single most significant contributor to successful development and deployment workflows. Enabled Developer Mode accounts for a substantial 25%, showing that having developer mode active is a necessary foundation but not sufficient by itself. Together, these two prerequisites, developer mode and trusted certificate, comprise 65% of the chart, which supports the practical conclusion that enabling developer mode and ensuring certificate trust are the primary enablers for getting apps onto devices and running them. The remaining slices, apps running smoothly at 20% and debugged issues at 15%, represent runtime outcomes. Once the initial setup and trust are established, a notable portion of effort still goes into ensuring smooth operation and resolving bugs. From this distribution, you can infer priorities for onboarding devices and organizing development efforts. First, confirm developer mode and certificate trust, then focus resources on stabilizing app behavior and resolving issues that remain after deployment. Once developer mode is enabled, you may encounter a common scenario. Your device doesn't automatically trust the apps you are trying to run. This typically happens if you are using a self-signed developer certificate. To resolve this issue, you need to configure your device to trust these apps manually. To do so, head over to the Settings app on your iOS device. Tap on General and navigate to VPN and Device Management. You should see your developer certificate listed here. Simply tap on the certificate and then select Trust your developer name. This confirms that your device trusts apps signed with that certificate. Once done, you should be free to run your application without hurdles. Understanding the importance of trusting your app certificate cannot be understated. Certificates ensure that the code being run on your device is from a known source and hasn't been tampered with. If a certificate isn't trusted, iOS will halt the app from executing, making the debugging process tedious. For example, if you have an app built and ready to run, but you face the dreaded untrusted developer prompt, don't panic. Simply navigate back to the settings like we did before, and remember that trusting your developer certificate is a one-time setup step. After you're through with it, you can run your app as many times as you'd like. Now let's take a look at a simple SwiftUI application that prints a welcoming message on the screen. This code begins by importing the SwiftUI framework, which provides the necessary tools to build user interfaces in a declarative way. Next, we define a structure named Content View that conforms to the View protocol, which is essential in SwiftUI for creating user interface components. Within this structure, we implement the body property, which describes the view's content. Here, we utilize the text type to display the string Hello Developer Mode on the screen. By chaining modifiers such as font, large title, and padding, we enhance the appearance of the text, making it larger and adding some space around it for better readability. Following the content view, we define the main entry point of our app with the developer mode app structure, also conforming to the app protocol. Inside this structure, we once again define a body property that outlines the app's primary scene, which contains a window group. This window group houses our content view, ensuring that when the app is launched, the user sees our greeting message prominently displayed. This foundational setup highlights the strength and simplicity of SwiftUI, enabling developers to quickly create intuitive user interfaces. Now let's talk about certificates themselves. Xcode generates a signing certificate that uniquely identifies you as a developer. This certificate plays a pivotal role in code signing your app. Every time you build your project and run it on your device, Xcode will sign your application with this certificate, ensuring that the code integrity is maintained and that no malicious code is being executed. Certificates are managed through Apple's developer portal, where you create and maintain your distribution profiles. Go through your developer account and you'll see an option for certificates, identifiers, and profiles. It's here that you can manage existing certificates, generate new ones, and link your app build to the appropriate provisioning profile. Now let's implement a simple function to check if our app is correctly provisioned. The function, named isProvisioned, begins by obtaining the bundle identifier of the app through bundle main bundle identifier. This string is crucial as it uniquely identifies your application. If the bundle identifier is nil or empty, the function will return false, indicating that the app cannot be properly provisioned. Next, the function checks if the bundle identifier is not empty. This is a straightforward yet effective mechanism to ensure that a valid provisioning profile is associated with your application. A non-empty identifier signifies that the app has been correctly configured to run on designated devices. This function is particularly beneficial during the early stages of development, as implementing such checks can prevent potential deployment issues later on. By ensuring that your application is properly provisioned right from the start, you can streamline your development process and avoid hiccups when it comes time to run your application on an actual device. Let's not forget that, as developers, staying updated with Apple's requirements and guidelines is paramount. Whenever Apple releases new operating systems or updates, it's essential to reassess your apps. This includes revisiting developer certificates and provisioning profiles, as they can change with updates to iOS, Xcode, or even new security protocols introduced by Apple. Periodically check the developer documentation for any changes in these statuses. It will save you from facing unexpected runtime issues. Keeping your development environment and devices updated ensures that you can leverage the latest features and make the most of developer mode. Now let's implement a logging feature to keep track of user inputs in real time. In this example, we define a logger struct with a static method called logEvent that takes a string parameter and prints it to the console, allowing us to monitor significant events easily. Next, we create a content view struct that conforms to the SwiftUI view protocol. Within this structure, we declare a state variable, userInput, which holds the text entered by the user. This state is essential as it allows SwiftUI to manage the view's updates dynamically based on user interactions. In the body of the view, we set up a vertical stack containing a text field and a text that displays the user's current input. The text field is initialized with a placeholder text, prompting the user to enter your message. We also attach an onChange modifier to the text field, which triggers every time the text changes. This modifier calls the logEvent method from the logger with the updated input, effectively logging each user entry. Lastly, we showcase the live input beneath the text field, allowing users to see their input in real time, creating an interactive and engaging experience. In summary, the transition to developer mode and effectively trusting your iOS app certificate is instrumental in establishing a solid foundation for your development process. By enabling developer mode, setting up your environment, and understanding the mechanisms for trusting certificates, you can test your apps effectively to provide the best user experience possible. To recap, we covered how to enable developer mode, trust your app certificate, role of certificates in code signing, and practical code examples demonstrating how to manage and log events in your Swift application. Next time you embark on a new project, remember these principles and watch your productivity soar as you confidently navigate the iOS development landscape. Congratulations, you have successfully run your app on an actual iOS device. This moment is a significant milestone in your journey as an iOS developer. Today we'll dive deeper into the essentials of running and optimizing your first app, ensuring it not only functions well but also shines in the user's hands. So far, we've learned about the significance of developer mode, trusted app certificates, and enhanced testing practices, and now we will cover optimizing the app development process. Now let's take a look at a common scenario in which two classes, person and pet, establish a relationship. In the initial code, we see a simple structure where the person class has a property called pet, which references an instance of the pet class. Similarly, the pet class holds a reference back to its owner of type person. This setup works well for establishing the relationship, but can lead to a significant issue known as a retain cycle. When instances of person and pet hold strong references to one another, they cannot be deallocated, which can lead to memory leaks in our application. To address this issue, we need to modify the code by making the pet property in the person class a weak reference. Now let's see how we can implement this change. By declaring pet as a weak variable, we allow the person instance to relinquish its ownership of the pet. This adjustment means that if there are no other strong references to the pet, it can be properly deallocated, thus breaking the retain cycle and ensuring that our application's memory is managed efficiently. This understanding of memory management is crucial for maintaining a responsive user experience. Now let's take a look at how we can efficiently filter an array of integers to retrieve even numbers. In the first code snippet, we initialize an array containing 1 million integers, ranging from 1 to 1 million. We then utilize the filter method to create a new array called filtered array, which consists of only the even numbers from the original array. While this approach is clean and easy to understand, it activates the creation of an additional array to store the intermediate values, which can be a performance concern, especially with larger datasets. Next, we will write the following optimized code, where we iterate over the original array using a for loop to identify even numbers directly. In this code, we declare an empty array called even numbers and populate it by appending numbers that meet the even criteria during the iteration. This method not only improves memory efficiency by avoiding unnecessary intermediate collections, but also streamlines the process, thereby contributing to better app performance. Always remember that in performance-critical applications, opting for more efficient data handling strategies can lead to significant improvements in resource management. The figure titled Key Aspects of Optimizing an iOS App displays 5 distinct bars for memory management, 85, performance optimization, 90, UI responsiveness, 88, error handling, 80, and user feedback, 92. Each annotated with its numeric score above the bar and aligned against a y-axis grid. From the values shown, user feedback ranks highest at 92, followed closely by performance optimization at 90 and UI responsiveness at 88, indicating that end-user input and overall runtime performance are the top priorities in this dataset. Memory management, with a score of 85, remains a strong priority but slightly lower than the performance-related areas, while error handling is the lowest at 80, though still notable. The clear ordering and small gaps between the top 3 bars suggest a strategy that emphasizes collecting and acting on user feedback while simultaneously investing in performance and UI smoothness. Memory improvements should be maintained to support those goals, and error handling, though comparatively lower, should not be neglected because it underpins user trust. The numeric labels and horizontal grid lines make it easy to compare magnitudes and see that differences are moderate rather than extreme, supporting a balanced optimization effort across these areas. Now let's see how we can implement asynchronous data fetching to optimize our app's UI performance. In this code, we begin by using Grand Central Dispatch, GCD, to create a task that runs on a background thread. This ensures that any heavy processing, such as fetching data from a remote server, does not block the main thread where the UI runs. First, we specify the task to be dispatched to a global queue with a background quality of service, signaling that it's a lower priority task allowed to run in the background. Within this block, we construct a URL that points to the data source we want to access. The try syntax allows us to attempt to fetch the data synchronously. If the request fails, it simply returns nil without crashing the app. After we have retrieved the data, we switch back to the main thread to update the user interface. It is crucial to make UI updates on the main thread to maintain responsiveness and prevent possible glitches. Here, we check if the data retrieval was successful, and if so, you would typically process the data and update the UI accordingly. This design pattern is fundamental for creating a smooth and responsive user experience in your app. Now let's see how we can implement error handling in our code using Swift SwiftUI construct. This approach is particularly useful when dealing with potential errors that may arise during operations like data fetching. In the example, we define a function called fetchData that initiates the process of retrieving data from a specified URL. We start by constructing a URL object with a given string, ensuring that it points to a valid resource. Next, we enter a do block where we attempt to fetch the data using data contents of. This method can throw an error if the data cannot be loaded, such as in cases of connectivity issues. If the data loading is successful, we can proceed to process it as needed. However, if an error occurs, the execution will jump to the catch block, where we handle the error appropriately. Here, we print an informative message that includes the error's localized description. This feedback is essential because it allows us to notify users of the issue gracefully instead of allowing the app to crash. Implementing such error handling practices not only improves code robustness, but also enhances user experience by providing clear communication about problems. Now let's see how we can implement a simple UI test case using the Xcode framework in Swift. This code sets up a test class named MyAppUITests, which inherits from Xcode test case, allowing us to write tests related to our app's user interface. the main method, test_button_tap, is defined to execute our UI interactions. In this method, we start by creating an instance of Xcode application, which represents the app we will be testing, and then we launch the app to simulate its initial state. The next step involves selecting a button within the app by its accessibility identifier, MyButton. We use XCT assert true to verify that this button is present on the screen, which assures us that the UI element is correctly loaded. Following this, we simulate a user action by tapping the button. After performing the tap, we need to validate the expected outcome of this action. Here, we check if a label designated as result label displays the text expected result. The use of XCT assert equal allows us to confirm that the UI behaves as intended after the user interaction. This structured testing ensures confidence in the app's functionality with every update, capturing potential issues before they reach the user. Now let's implement a feedback mechanism within our app to gather user insights, which is crucial for enhancing user experience and engagement. The code begins by defining a function named presentFeedbackAlert, which displays an alert to the user when invoked. Within this alert, we set a title and a message that expresses the value of user feedback. Next, the alert includes a text field, allowing users to enter their thoughts or suggestions directly. This interaction is essential as it enables users to communicate their opinions, fostering a sense of community and collaboration. After the user types their feedback, the code adds a submit button, which will trigger an action when tapped. In this action, we check if the text field contains any input. If so, we capture the feedback and handle it accordingly. Currently, we print the feedback to the console for testing purposes. This straightforward implementation showcases how to effectively collect user input, paving the way for future improvements based on user insights. Engaging in such practices will not only enhance your app's development, but also build a loyal user base that feels valued. In summary, after running your first iOS app, the next steps are crucial. We covered performance optimization, memory management, UI responsiveness, error handling, UI testing, and the importance of user feedback. These elements are foundational for developing a polished and effective application that users will love. So keep these principles in mind as you continue your journey in iOS development. The world of app creation is vast, and there's so much more to explore and learn. Thank you for joining me, and I look forward to our next lesson, where we will delve into even more advanced concepts. Happy coding! Running your app on an actual iOS device is a crucial step in the development process. While the simulator offers convenience, it cannot replicate all the hardware functionalities and software APIs that your app might rely on. Testing on a real device ensures you get accurate feedback, performance data, and a genuine user experience. So far, we covered the fundamentals of executing your iOS app on a real device, emphasizing performance optimization, memory management, and UI responsiveness. Now we will talk about how to run your app on an actual iOS device, outlining the steps and considerations involved in the process. To begin with, let's understand why testing on a real device is essential. The iOS simulator can mimic various screen sizes and orientations, but it doesn't provide accurate data for features like the camera, accelerometer, and GPS. Testing on a real device gives developers a realistic view of how the app performs under different conditions, such as varying network speeds, battery levels, and hardware compatibility. Not to mention, user interactions feel markedly different on a physical device versus a virtual one. There are a few preliminary steps to prepare for this journey. First, you need to ensure you have a valid Apple developer account, which grants access to essential resources and tools necessary for app distribution and testing on devices. You can sign up at the Apple developer website if you don't have an account. Once you have your account ready, you will need to install Xcode if you haven't already. Xcode is Apple's integrated development environment, and it's your primary tool for developing apps for iOS, as well as macOS, watchOS, and tvOS. The displayed figure is a bar chart titled Steps to Run iOS App on Real Device that maps 5 sequential setup and deployment steps on the x-axis. Set up Xcode, connect device, trust device, select device in Xcode, and run app to the time taken in hours on the y-axis. Each bar is labeled with its exact duration, 2, 1, 1, 3, and 4 hours respectively, making it clear that the initial setup tasks, set up Xcode, connect device, trust device, consume relatively little time compared with the latter stages. The most prominent pattern is that the final two steps, selecting the device in Xcode and actually running the app, require a disproportionate share of overall time, with Run App being the highest at 4 hours and Select Device in Xcode at 3 hours. From this we can conclude that configuration, provisioning, build signing, and the first run debug cycle are the main time sinks in the process. The implication for planning and workflow is straightforward. Invest effort up front to have Xcode properly configured and provisioning profiles ready, and be prepared for longer iterations once you begin deploying and debugging on hardware, since those steps dominate the total time budget. Now let's dive into setting up your actual iOS device for development. First, connect your iOS device to your development machine using a USB cable. Once connected, open Xcode. Navigate to Xcode's Preferences through the menu bar by selecting Xcode and then Preferences. Under the Accounts tab, log in with your Apple ID associated with your developer account. This process gives Xcode permission to interact with your device. Next, you need to trust the connected device. A prompt will ask you to trust this computer on your iOS device. Tap Trust, and if prompted, enter your device's passcode. This is an essential step that lets your device communicate securely with Xcode. Once Xcode recognizes your device, a quick check is to navigate to the Window menu, then Devices and Simulators. In the Devices section, you should see your connected iPhone or iPad listed, indicating it is ready for development. If it's not showing up, you might want to troubleshoot your connection or ensure that iTunes is updated, as outdated versions can cause compatibility issues. Up next, you're going to set your project to run on the real device. Make sure your app project is open in Xcode. Locate the top left corner of Xcode where you will find the scheme selector, the drop-down that typically shows the name of your project. Click it and select your device from the list. At this point, your iOS device is still not set to run your app just yet. You need to configure a free provisioning profile if you haven't set up a paid developer account. Now let's implement a simple piece of Swift code that showcases the essential elements of a basic user interface for our app. This code defines a subclass of UI View Controller, named ViewController, which is a crucial component of any iOS app as it helps manage the app's views. Within the ViewDidLoad method, which is called after the ViewController has loaded its view hierarchy into memory, we start by setting the background color of the view to white. This step creates a clean and neutral background that enhances readability and visual appeal. Next, we create a UI label, a fundamental UI element used to display text. We set its text property to Hello World and align the text to the center of the label. To ensure that the label is positioned correctly on the screen, we define its frame size and center it within the parent view. This positioning is crucial as it demonstrates how elements can be centered dynamically, making our interface adaptable across different device sizes. Finally, we add the label as a subview to the main view. This step is necessary for the label to be visible on the screen. By running this code on an actual device, you can observe how the UI adapts to various screen configurations, which would not be fully realized in a simulator environment. After clicking Run, your app should launch on your real device. If this is the first time you're running the app, you may encounter a message indicating that the app is from an untrusted developer. Navigate to your device's settings, General Device Management, and trust your developer account. This process effectively tells iOS that you are, indeed, the person behind the app. Once everything is set, you're all geared to interact with your app on the device. Use gestures, tap buttons, and simulate interactions. This phase is crucial. You need to observe performance, UI responsiveness, and overall user experience. Take notes on any anomalies or behaviors that seem out of place. Next, we will implement the function ViewWillTransition to With to handle device orientation changes effectively. This method is called whenever the interface orientation changes, allowing us to adapt our user interface, UI, accordingly. As we define this method, we start by calling super ViewWillTransition to size with coordinator to ensure the superclass handles its own actions during this transition. This is important for maintaining the expected behavior of our view controller as it processes the orientation change. Next, we use the coordinator parameter, which provides an animate alongside transition closure. Within this closure, we can update the UI elements to reflect the new orientation. For instance, we might want to adjust layout constraints, reposition views, or even change element sizes to accommodate the new screen size. This approach ensures that our app's UI responds smoothly to changes, enhancing the user experience by maintaining visual consistency no matter how the device is oriented. This dynamic adaptability is crucial for modern app development, where users frequently switch orientations, especially on iPads. Now let's explore how to implement effective error handling in your app using Swift. In real-world applications, unexpected circumstances can arise, and it's crucial to manage these scenarios to maintain a smooth user experience. Here, we utilize Swift's do-catch statement to handle potential runtime errors gracefully. First, within the do block, you initiate the execution of a function, in this case, perform risky operation. This represents an operation that could throw an error, such as network requests, file I/O, or any other task that might fail under certain conditions. If something goes awry during the execution of this line, control will move to the catch block. In the catch block, we handle the error by printing a user-friendly message that includes the error's localized description. This feedback is invaluable for debugging, allowing you to understand what went wrong and why. Implementing this structure not only enhances your app's resilience but also improves user satisfaction, as it prevents abrupt crashes and provides meaningful feedback when things don't go as planned. Always remember that effective error handling is key to developing robust applications. Now, as you reach the end of this segment, it's essential to emphasize the importance of ongoing testing and iteration. Once you finish testing your app on your device, consider collecting feedback from other users. This approach can help identify usability concerns that you may not have noticed. Utilizing TestFlight, Apple's beta testing service, lets you distribute your app to a group of testers effortlessly. Feedback from real users can drastically shape the evolution of your app. Remember, every iteration based on testing leads you closer to a polished product that users will enjoy. Testing on a real device uncovers insights that the simulator simply cannot provide, ensuring that your app meets user expectations and performs under real-world conditions. In summary, testing your iOS app on an actual device was our focal point today. We explored how to set up your device for development, move through the app deployment process, and utilized various tools and techniques for a comprehensive testing experience. So, ready yourself to go forth and continue refining your app. Let's dive into a comprehensive guide on running apps on an actual iOS device. Testing your iOS applications on a real device is crucial for understanding how they perform in the wild, providing a user experience that the simulator simply cannot replicate. In this session, we'll discuss the technical aspects of deploying your app to a real device, explore essential tips for effective testing, and provide code examples to make the process clearer. By the end of this lesson, you'll be equipped with the knowledge to confidently deploy and test your apps on actual hardware. So far, we learned about the importance of testing your iOS app on a real device, which offers a more accurate representation of performance and user experience than the simulator. We covered the essential setup steps, including obtaining a developer account, installing Xcode, and connecting your iOS device. Additionally, we discussed how to run the app on the device, handle potential errors, and utilize debugging tools effectively. Finally, we emphasized the need for ongoing testing and gathering user feedback to refine your app further. Now, we will talk about the best practices for deploying your app to an actual iOS device, including device provisioning, code signing, and testing features unique to hardware. Let's start with device provisioning. To run apps on a real iOS device, you need to enroll in the Apple Developer Program and set up a provisioning profile. This profile links your app with the device for testing purposes and ensures that only authorized apps can run on your devices. It's a simple process, but one that is vital. First, log into your developer account and navigate to the Certificates, Identifiers, and Profiles section. Here, you'll create an app ID that uniquely identifies your app. After that, create a provisioning profile by selecting your app ID and the devices you want to use. This is critical. Without including the devices in your profile, your app will not install. Next, download the provisioning profile and open Xcode. In Xcode, select your project, go to the Signing and Capabilities tab, and select your provisioning profile from the drop-down. This step ensures that Xcode recognizes that your app can run on the specified devices. Now let's address the code signing process, a key element of the app deployment. Code signing is what verifies the integrity and origin of your application, ensuring the system that your app hasn't been tampered with. For code signing to work effectively, your app must be correctly configured with the necessary certificates and provisioning. To facilitate this, navigate back to your developer account and create a signing certificate. You'll need to download and install this certificate on your machine. After this, go once more into Xcode. There's no magic trick here. You just want to ensure that your project settings correctly align with the provisioning profile you set up before. Here's a little trick that may save you some time. Ensure that your project uses automatically manage signing. This checkbox can be found under the Signing and Capabilities tab in the project settings. Once you enable it, Xcode takes care of the rest, creating the necessary code signatures on the fly. Next up is connecting your iOS device to your development machine. Make sure your device is connected via USB and trusted by your computer. A quick pop-up on your device will ask you to trust this computer. Go ahead and tap Trust. This step is crucial as it establishes a secure connection between your iOS device and your development environment. Once connected, go back to Xcode and select your device as the target. You'll see your device listed in the Device Selection drop-down on the toolbar. If everything is set correctly, you should be good to hit that magical Run button. Your app should now build and deploy to your connected device. This real-time deployment allows you to see how the app performs with actual hardware capabilities. For instance, you can test interactions with the camera, GPS, and other sensors not available in the simulator. Now let's implement the following code to measure the performance of an operation on a real iOS device. This example utilizes the date class to capture the start and end times of an operation. Initially, we declare a variable named start time, assigning it the current date and time at which the operation begins. After this, you insert the code that executes the task you want to measure. Once the operation is complete, we create another variable, end time, which holds the end time of the execution. To assess the duration of the operation, we use the timeIntervalSince method on the end time, passing in start time as the argument. This method computes the time interval in seconds between the two date objects. Finally, the print statement outputs the total time taken for the operation in seconds, giving you insight into how efficiently the code executes on the actual device. This real-time performance monitoring is invaluable for optimizing app functionality and ensuring a smooth user experience based on the device's capabilities. Now let's see how we can implement a tap gesture recognizer in our app, a vital part of improving the user experience on an actual iOS device. The first step is to create an instance of UI tap gesture recognizer, which will listen for tap gestures. You assign it a target, which is typically your view controller, and specify an action, in this case, the handle tap method that you've defined. This method will be executed whenever the tap gesture is recognized. After creating the gesture recognizer, it's time to add it to your view. This is done by calling the addGestureRecognizer method, attaching the tap gesture to your view. This action allows your application to respond to user taps on that specific view, enhancing interactivity. Next, let's take a closer look at the handle tap function. This method simply writes a message to the console, indicating that the view has been tapped. While this is a basic initial implementation, it lays the groundwork for more complex interactions you might want to handle later, such as triggering animations or navigating to another screen when the user taps the view. Performance profiling is another significant aspect of deploying your app on a real device. The Instruments tool in Xcode is your best friend for this. It monitors your app's performance metrics, such as memory usage, CPU load, and more while it runs on the device. The insights gleaned from Instruments can help you optimize your code effectively. To get started, run your app on the device and navigate to Xcode's menu bar. Select Product, Profile, or use Command+I once the Instruments app opens. You can choose from various profiling options, like Time Profiler, Allocations, or Energy Log. Each provides unique insights into different aspects of your app's performance. For example, using the Allocations instrument allows you to track memory usage. You can see live memory allocation and identify potential leaks or retained cycles that might be causing your app to lag or crash. The displayed chart titled Key Aspects of Testing iOS Apps on Real Devices shows 6 labeled bars with explicit numeric labels: device provisioning 25, code signing 15, testing 20, debugging 10, user feedback 20, and performance profiling 10. The highest single value is device provisioning at 25, indicating that setup and authorization of devices are the most emphasized activity. Testing and user feedback both score 20, forming a second tier of priority that highlights the dual focus on technical verification and user-driven validation. Code signing at 15 is lower but still notable, reflecting its essential role as a prerequisite to deployment. Debugging and performance profiling each register at 10, the lowest values, which indicates they are important but receive relatively less emphasis in this breakdown. The distribution therefore reveals a pattern. Initial setup tasks, provisioning and signing, plus active testing and feedback capture the bulk of attention, while iterative runtime analysis, debugging and profiling is treated as a continuing but smaller slice of effort. From this representation, we can conclude that resource allocation should prioritize getting devices properly provisioned and ensuring comprehensive testing and feedback channels, while scheduling regular but less frequent debugging and profiling cycles to refine performance after core functionality and user validation are in place. Now let's take a look at a practical implementation for monitoring network connectivity in your app. The provided code utilizes the Reachability Swift library to check and respond to the current network status effectively. The function begins by creating an instance of the Reachability class, which will notify us of any changes to the network connectivity. Using a closure, the code defines actions to be taken when the network is reachable. Inside this closure, we check if the connection is via Wi-Fi or cellular, enabling tailored logging or actions based on the specific type of connectivity. Next, we call the Start Notifier method to begin monitoring changes in the network status. This function runs in the background and keeps the app informed about the connectivity state, which is essential for maintaining a responsive user interface during varying network conditions. If there's an issue with starting the notifier, it gracefully handles the error by printing a message to the console. This implementation ensures that your app can adapt dynamically to the current connectivity, ultimately enhancing the user experience while handling network requests. Now let's examine how we can implement an in-app feedback mechanism to enhance user engagement during the testing phase. The code snippet defines a function that triggers when the feedback button is tapped. First, it attempts to create a URL object formatted for sending an email via the Mailto protocol, using the specified email address for user support. The use of guard statements here ensures that if the URL is invalid, the function exits gracefully without proceeding to the next step, preventing potential crashes. If the URL is valid, the application invokes the URL to open the user's default email application, populated with the recipient's email address. This creates an effortless way for users to report bugs or share their experiences directly, streamlining communication and fostering a collaborative approach to improving the app's user experience. By leveraging this simple feedback loop, developers can gather invaluable insights directly from real users, ultimately helping to refine and enhance the application before its official launch. As we wrap up this extensive guide to running apps on actual iOS devices, remember that each step from provisioning profiles, code signing, testing gestures, analyzing performance, to gathering invaluable user feedback plays a significant role in the overall development cycle. The insights and experiences gained from testing on real hardware will sharpen your ability to deliver polished, high-quality apps in the competitive mobile landscape. Now go ahead, deploy that app you're so passionate about, and remember, the device is your best testing companion. Happy coding. Welcome. In today's session, we will dive into the fundamentals of the Swift programming language using Swift Playgrounds, a fantastic tool for both beginners and seasoned developers. We aim to increase your understanding of simple values and types implemented in Swift, setting a strong foundation for your coding journey. So far, we learned about the process of device provisioning, which is essential for deploying apps on real iOS devices. We also covered code signing to ensure app integrity, as well as the steps to connect your device for real-time testing. Additionally, we discussed the importance of testing user interactions and performance profiling to optimize your app based on actual hardware capabilities. Finally, we highlighted the significance of gathering user feedback to improve the overall user experience. Now, we will explore the striking features of the Swift programming language, focusing on how we can handle simple values and types effortlessly in Swift Playgrounds. Now let's see how we can declare and manipulate simple values in Swift using variables and constants. First, we declare a variable named myNumber of type int and assign it the value 42. This straightforward syntax showcases Swift's clarity, where the type can also be inferred, making it possible to write the declaration without specifying int explicitly. Next, we update the value of myNumber to 50, demonstrating the flexibility of variables in Swift, allowing for dynamic changes. Conversely, if we declare a value using let, we create a constant. For instance, we define constant number as 100, but attempting to reassign it to another value like 200 results in a compile time error. This distinction between variables and constants is crucial for ensuring that certain values remain unchanged throughout the program. Grasping these foundational concepts of mutable and immutable data types is essential for writing effective Swift code. The accompanying figure titled Distribution of Simple Value Types in Swift displays a horizontal arrangement of colored bars for 5 categories: integers, floats, booleans, characters, and strings, with numeric frequencies shown above each bar. The raw frequencies are 20, 15, 25, 10, and 30 respectively, which sum to 100, so each bar directly corresponds to a percentage of the total. Strings 30%, booleans 25%, integers 20%, floats 15%, and characters 10%. From this visualization, we can conclude that strings are the most prevalent simple value in this dataset, nearly 1/3 of all occurrences, followed closely by booleans. Integers occupy a meaningful but smaller share, floats are used less often than integers here, and characters are the least common. The clear ordering and the numeric labels above each bar make these relative differences easy to read at a glance. Practically, this distribution suggests prioritizing instruction and examples around strings and booleans when teaching simple values in Swift, while still covering integers and floats for numeric operations and treating characters as a specialized, less frequently used type. Next, we will explore how to work with floating point numbers in Swift, which are essential for precise calculations. In our example, we declare 2 variables, pi as a double type and e as a float type. The double data type allows us to store larger and more precise numbers because it occupies 64 bits, making it ideal for representing irrational numbers like pi. By contrast, float, which uses 32 bits, is less precise but may be useful when you need to save memory or in situations where less precision suffices. Now let's see how we can implement mathematical operations with these floating point numbers. We declare a variable named radius as a double with a value of 5, which represents the radius of a circle. Next, we calculate the area of the circle using the formula pi radius radius. This computation leverages the variables we initially set up to determine the area straightforwardly, demonstrating the clarity and efficiency of Swift syntax for mathematical operations. When the area is calculated, it stores the resulting value, showcasing how easily we can conduct more complex calculations in Swift programming. Next, we will take a look at the Boolean data type, which is crucial for controlling the flow of our programs through conditions. In Swift, we declare a Boolean variable by specifying its type followed by the variable name and its initial value. For instance, we define a variable named isSwiftAwesome and assign it the value true, indicating a positive statement about Swift. Now let's see how we can implement this variable within a conditional statement. We use an if statement to check the value of isSwiftAwesome. If it evaluates to true, the program will execute the code within the curly braces following the if condition, which in this case prints Swift is indeed awesome. However, if isSwiftAwesome were false, the program would follow the else block, providing an alternative output. This use of Boolean values allows for dynamic decision-making in our code, showcasing Swift's clarity and ease of use, which helps us focus on solving problems rather than getting lost in more complex syntax. Next, we will write the following code to introduce characters and strings in Swift. First, we declare a variable named letter of type character and assign it the value a. This demonstrates that in Swift, a character is represented by the character type, which is perfect for holding single characters. Next, we move on to strings using the string type. We declare a variable called greeting and assign it the text hello Swift. This illustrates how straightforward it is to create and assign strings in Swift, which can hold sequences of characters. Now let's see how we can manipulate strings more dynamically. We set up a constant name for student and then create another variable, welcome message, that combines this constant within a string using string interpolation. By using the backslash in parentheses, we can embed the value of name directly into the string. When this code runs, welcome message will contain the personalized message, welcome to student Swift Playgrounds. showcasing the power of Swift's string handling capabilities. This flexibility allows you to create dynamic and engaging content simply and effectively. Now let's take a look at how Swift's type inference works in practice. In Swift, when you declare a variable or constant, you often don't need to specify its type explicitly, as Swift can automatically determine the type based on the value you assign. For example, when we write let score equals 100, Swift infers that score is an integer or int because the value 100 is a whole number. Similarly, in the line let temperature equals 36, Swift recognizes this as a double due to the decimal point in the number. This ability to infer types not only streamlines the code, but also enhances readability, allowing developers to focus on the logic rather than get bogged down with type definitions. This flexibility is especially beneficial when working with functions or building collections, as you're not required to repeatedly specify types, making for neater and more efficient code structures. Next, we can explore more complex data structures, or how type inference integrates into various programming scenarios. Now let's delve into arrays in Swift, which are a fundamental aspect of managing collections of data. We begin by declaring an array to hold multiple fruit names, using a type annotation to specify that this array will contain strings. This declaration sets the stage for us to store and manipulate an ordered collection of values. Next, we can access the elements within our array using their respective index numbers. It's crucial to remember that in Swift, array indices start at 0. Therefore, to retrieve the first fruit from our array, we reference it by its index, presenting a clear and concise way to access individual elements. Now let's implement a feature to add new items to our array. By using the append method, we can easily add another fruit to our existing list of fruits. This method not only enhances our array, but also demonstrates Swift's dynamic and flexible nature when it comes to managing collections. With these basic operations, declaration, access, and modification, we gain control over our data, allowing us to build more complex programs as we continue exploring Swift. Now let's take a look at dictionaries, which are essential for storing key-value pairs in Swift. By declaring a simple dictionary named ages, we can efficiently map names to their corresponding ages. This structure allows for quick retrieval of values, making it easy to access the age associated with a particular name. Next, we will write the following code to demonstrate how to retrieve an age from the dictionary. Using an optional binding with if-let, we can safely attempt to access the age value for Alice. If the age exists, the code will print a neatly formatted message indicating Alice's age. This method is not only simple but also illustrates the importance of safe coding practices in Swift, avoiding potential errors that may arise if we try to access a key that doesn't exist. Through this example, you can see how dictionaries can simplify data management and retrieval in your programs, making them a powerful feature in Swift's collection of data types. Now let's take a look at optionals, a unique feature in Swift that significantly enhances code safety. To declare an optional, we start with a variable followed by a question mark, indicating that this variable can hold either a value or nil, which means no value at all. In our example, we initialize optional name to nil, highlighting that it does not have an assigned value initially. Next, we can assign a value to optional name, setting it to Swift student. This allows us to capture meaningful data while maintaining the safeguard against unexpected nil values. Now, to safely access the value contained within this optional, we employ optional binding using if-let. This statement checks if optional name has a value. If it does, we unwrap it and assign it to a new constant, name, allowing us to safely print a greeting. If the optional is nil, the else clause ensures we handle that case by providing a default message, which further illustrates Swift's commitment to safe coding practices. Now let's explore typecasting in Swift, which is essential when dealing with class hierarchies, such as parent-child relationships. In our example, we begin by defining a base class called vehicle and a subclass called car, which inherits from vehicle. This relationship sets the stage for how we can manage and differentiate between different types of vehicles in our code. Next, we instantiate a variable named myVehicle and assign it a new car object. Here, myVehicle is declared with the type vehicle, demonstrating polymorphism, where a parent class reference can hold a child class object. Now let's see how we can utilize optional downcasting using as. We attempt to cast myVehicle to the car type. If the cast is successful, we print a message confirming that it's indeed a car, otherwise we acknowledge that it is. This approach provides a safety net since optional downcasting avoids runtime crashes by checking if the conversion is valid before proceeding. This emphasizes Swift's commitment to safety in coding practices, allowing developers to handle object types with confidence. As we wind down today's session, we've tackled quite a lot, from simple values and types to collections and optionals. The beauty of Swift lies in its simplicity and safety features, giving you the tools to express complex ideas in manageable ways. Whether you're tweaking a variable or creating a sophisticated data structure, Swift's syntax is designed for clarity and ease of use. So to wrap up, remember, Swift's simple values are robust and foundational. As you familiarize yourself with these structures, you'll build the confidence necessary to advance your programming skills. In our next session, we will build on these concepts and start constructing more complex functions, leading us deeper into the Swift language. Thank you for joining me today. Keep coding and experimenting, and I'll see you next time. Managing developer certificates and running apps on an iOS device is essential for any aspiring iOS developer. In this guide, we will explore the process of enabling developer mode, how to manage your developer certificates, and the steps needed to install, run, and debug apps on devices running iOS 16 or greater. So far, we covered the fundamentals of the Swift programming language, including basic types, collections, and typecasting. Now, we will delve into managing app installation on iOS and the crucial role of developer certificates. First things first, let's get ourselves set up to run our apps on a physical iOS device. Developer mode is a feature that was introduced by Apple during the Worldwide Developers Conference in 2022. If you want to test your app while developing, you must enable developer mode on your device. To start, navigate to the Settings app on your iOS device, scroll down to Privacy and Security, and look for developer mode. You will see a toggle to enable developer mode. Once enabled, your device may prompt you to restart. After rebooting, you'll need to confirm that you indeed want to enable developer mode. This is a critical step because without developer mode, your apps cannot be installed or debugged on your device, which would severely hinder your development process. Next up, let's talk about developer certificates. These are digital certificates that prove your identity as a developer and are required for signing your apps before you can install them on devices. Signing an app ensures that it comes from a known source and hasn't been altered. Certificates are part of your provisioning profiles, which also include information about the devices on which you are allowed to run your app. To manage certificates, you'll need to access your Apple developer account at developer.apple.com. Once logged in, go to Certificates, Identifiers, and Profiles. You can create a new certificate under the Certificates section. There are different types of certificates, such as development certificates, distribution certificates, and more, depending on your needs. For instance, to create a development certificate, you will need to generate a certificate signing request, CSR, using the Keychain Access application on your Mac. Open Keychain Access and go to Keychain Access Certificate Assistant, request a certificate from a certificate authority. Fill in the required fields and make sure to save the CSR file when prompted. After generating the CSR file, go back to your developer account and click the plus button to add a new certificate. Choose the type of certificate you want to create, in this case, a development certificate, and follow the prompts to upload the CSR file you just generated. Once your certificate is created, download it and double-click it to install it in your keychain. In Xcode, you can set your project to use this certificate by going to your project settings, selecting the Signing and Capabilities tab, and selecting the appropriate team. Doing this will allow Xcode to automatically manage the signing process for you, provided you've set up the correct profiles. Now that we have the developer certificate sorted out, let's move on to provisioning profiles. Provisioning profiles link your developer certificate with the app ID and the list of devices that you are allowing your app to run on. You can create a new provisioning profile in your Apple developer account under the Profiles section. Choose the type of provisioning profile you need. Again, typically you will use a development profile during the coding phase and a distribution profile when you are ready to publish. Select your app ID and then link the profile to the certificate you created earlier, and finally, select the devices on which this app can run. Once created, download the provisioning profile. Back in Xcode, ensure that you select this provisioning profile for your project. This can usually be done automatically by selecting Automatically Manage Signing. The displayed bar chart titled Key Steps in Managing Developer Certificates and Running Apps on iOS quantifies the relative importance of 5 tasks. Enable developer mode 30%, manage developer certificates 25%, install apps 20%, debugging tools 15%, and provisioning profiles 10%. The pattern shows a clear descending order of emphasis. Enabling developer mode and managing certificates together account for more than half of the total importance, 55%, indicating these are foundational activities that demand the most attention. Installing apps and using debugging tools occupy the middle ground, 20% and 15%, highlighting that while practical deployment and iterative troubleshooting are essential, they build on the earlier setup steps. Provisioning profiles, though shown as the smallest single slice at 10%, remain a necessary element. Its lower percentage suggests it is a more narrowly scoped but still mandatory task. From these values, we can conclude that prioritizing time and effort on enabling developer mode and correctly managing certificates yields the greatest return for getting apps running on devices, while ensuring provisioning profiles and debugging workflows are in place completes a robust end-to-end development process. At this point, you have your certificate and provisioning profile ready to go. It's time to install your app on your device. Make sure your iOS device is connected to your Mac via USB. Now, in Xcode, select your device from the Device menu at the top of the window. Next, build your app by clicking on the Play button. Xcode will compile your code and install the app on your selected device. If everything has been set up correctly with your certificates and provisioning profiles, the installation process should go smoothly. It's important to note that since iOS 16, you might need to trust the developer on your device. To do this, navigate to Settings, General, VPN, and Device Management, and tap on your developer app under the title section. You should see a button to trust the certificate. This might sound like a minor step, but it's crucial to ensure that your application can be run on your device. Now let's take a look at a simple implementation that demonstrates basic application logic in Swift. This code defines a ViewController class, which inherits from UI ViewController, making it a key component of any iOS application. In this class, we start by declaring a variable counter of type int and initializing it to 0. This variable will keep track of how many times a user interacts with the increment button. Next, we create a function, incrementCounter, which is connected to a user interface element, specifically a button through and at IB action. This function is triggered every time the button is pressed. Inside the function, we increment the counter by 1 and then print its current value to the console. This print statement allows us to see how the counter changes with each button press, providing a clear way to debug and verify the application's behavior. By placing a breakpoint on the print line during debugging, developers can inspect the value of counter in real time and step through the execution flow, providing critical insights into the app's logic as it runs. Now let's see how we can implement camera functionality in our iOS app using Swift. The code begins by importing the necessary frameworks: UI Kit for building the user interface and AV Foundation, which provides access to device media, including the camera. Inside the Camera ViewController class, we override the ViewDidLoad method. This method is called when the view has loaded into memory, making it a suitable place to initiate important setup tasks. Here, we request access to the device's video camera. The AV Capture Device Request Access for Video function prompts the user for permission to use the camera. The completion handler provided within this method checks whether the user granted permission. If permission is granted, the app can then proceed to access the camera for tasks such as capturing photos or recording videos. But if permission is denied, it's crucial to handle this case appropriately, ensuring that users are informed about the restrictions of the app without crashing or behaving unexpectedly. This approach not only respects user privacy, but also reinforces a smooth user experience while using camera-based features in your application. When you're finished with testing your app, you might wonder how to clear up some old versions or unwanted applications from your device. You can uninstall an app just like you would any typical iOS application. Press and hold the app icon until a menu appears, then select Remove App. However, if you have multiple versions of the same app installed, Xcode will handle deleting previous versions automatically when you run the most recent build on your device. As you can see, managing developer certificates, provisioning profiles, and testing your app on a real device can feel quite intricate, but all these pieces tie together to create a smooth development experience. In conclusion, we have covered the essential steps to manage developer certificates, provision your app, and run it on a physical iOS device. We went through enabling developer mode, creating and managing certificates, working with provisioning profiles, and debugging your app effectively in Xcode. Understanding these components is crucial for your journey as an iOS developer, as mastering them will empower you to create high-quality apps that can run smoothly on user devices. Remember, always maintain an organized workflow when dealing with certificates and profiles, as a small mistake can lead to significant distractions in your development process. Happy coding! To truly harness the power of iOS development, it's crucial to run your applications on an actual iOS device. While the simulator provides a helpful environment to test your applications, it doesn't fully replace the experience and fidelity of testing on real hardware. In this lesson, we'll discuss how to run your app on an iOS device, ensuring that you can make the most of the various hardware features and APIs that make iOS unique. So far, we learned the importance of managing developer certificates and enabling developer mode to successfully run and debug apps on iOS devices. We explored how to set up developer mode, create and manage certificates, and establish provisioning profiles. Additionally, we discussed the debugging process in Xcode, emphasizing its role in resolving code issues during development. Lastly, we highlighted the significance of testing apps on real devices to ensure smooth functionality and user experience. Now we will talk about the steps necessary to run your application on an iOS device and the benefits that come with it. Let's start with connecting your device. The first step in running an app on an iOS device is to connect the device to your Mac. Use a USB cable to link your iPhone or iPad to your system. Once connected, unlock your device, and you should see a prompt on both your device and Xcode confirming the connection. Make sure to trust the computer on your iOS device when prompted. This allows your Mac to communicate with your phone securely. After a successful connection, you need to select your device as the active target in Xcode. Open your project in Xcode, navigate to the top bar where you see the current target next to the Run button. Click that target drop-down and select your connected iOS device from the list. If your device appears grayed out, it may not be properly connected or not recognized due to an underlying configuration issue. Make sure developer mode is enabled. Once your device is recognized, you might be eager to deploy your app directly, right? Well, before that, let's ensure that you have the right provisioning profile set up to allow the app to run. Provisioning profiles serve as a bridge between the app, your developer account, and the iOS device. In Xcode, you can manage your provisioning profiles in the Signing and Capabilities tab of your app target. Ensure that both the team and provisioning profile are correctly set to match your connected device. If there are issues, Xcode often provides hints or errors that guide you toward resolving them. Make sure that the Automatically Manage Signing option is checked, which allows Xcode to handle certificate and provisioning profiles for you seamlessly. Once everything is set up, you can build and run your app on your device. Click the Run button and watch as Xcode compiles your app and installs it on your iOS device. If everything is configured correctly, within seconds, you should see your app launch on the device. This is where the magic of real device testing begins. The displayed bar chart, titled Key Concepts in Running iOS Apps on a Device, presents 6 labeled concepts on the x-axis: connecting device, developer mode, provisioning profiles, debugging, performance metrics, and real device testing, and maps each to an integer value on a 1-10 importance scale shown on the y-axis. The heights and top labels indicate the following values: connecting device equals 7, developer mode equals 8, provisioning profiles equals 5, debugging equals 6, performance metrics equals 9, and real device testing equals 10. 2 clear patterns emerge. First, real device testing 10 and performance metrics 9 are the most prominent priorities, forming the upper end of the importance spectrum. Second, provisioning profiles 5 and debugging 6 sit lower, indicating comparatively less emphasis in this ranking. The ordering implies a practical focus where ensuring the app runs on real hardware and measuring how it behaves under real conditions are top priorities, while support process items like provisioning and debugging, though necessary, receive relatively lower weight. The uniform integer labels on each bar make the relative gaps explicit, e.g., a 1-point gap between performance metrics and real device testing, and larger 2 to 5-point gaps versus provisioning profiles, supporting the conclusion that hands-on testing and performance assessment should guide where you invest most effort when preparing an app for real device deployment. Now let's see how we can implement motion detection in our app using the Core Motion framework. First, we import the Core Motion module, which provides access to the motion-related data from the device's sensors. We then define a new class, MotionViewController, inheriting from UIViewController, which is a fundamental building block for creating user interfaces in iOS apps. Inside this class, we create an instance of CM Motion Manager, which is the main interface for accessing motion data like acceleration. As our view loads, we call a method to start receiving updates from the accelerometer. This method checks whether the accelerometer is available on the device, ensuring our app won't crash on unsupported hardware. We set an update interval of 0.2 seconds, determining how often we want to receive acceleration data. By starting accelerometer updates, we provide a closure that processes the incoming data and checks for errors. Within this closure, if valid acceleration data is received, it prints the X, Y, and Z values reflecting how the device is being tilted and moved. This real-time data is critical for creating responsive apps that utilize the phone's physical movements for interactivity. Moreover, testing on an actual device allows you to evaluate performance metrics that are essential for the success of any application. For instance, you can check how your app performs under battery constraints and how it handles network conditions in mobile environments. These constraints can drastically affect user experience, and understanding them is key to developing a robust application. A valuable tool for performance assessment is Instruments, which is embedded within Xcode. You can launch Instruments while your app runs on your device to gather data about CPU usage, memory allocation, and even the responsiveness of your app. Profiling your app this way gives insights that are critical for optimizations. Here is how you would start profiling. 1. With your app running on the device, navigate to Xcode's product menu. 2. Choose Profile or press +I. 3. This will launch Instruments where you can choose different profiling templates, like Time Profiler to track performance or Lakes to check for memory leaks. Let's explore how to leverage the Core Motion framework to access and react to accelerometer data within our application. We start by importing the Core Motion framework, which equips us with the necessary tools to tap into motion-related data sourced from the device's hardware components. We will then create a class named MotionViewController that extends UIViewController, serving as the foundation for our motion functionality. Within this class, we instantiate CM Motion Manager, which serves as the main interface for motion-related tasks. In the ViewDidLoad method, executed when the view controller's view is loaded into memory, we initiate the accelerometer updates by invoking a custom function. Next, we will define the Start Accelerometer Updates function. In this method, we first verify the availability of the accelerometer on the device. If it is indeed available, we set our update interval to 0.2 seconds, which dictates how frequently updates are received. We proceed to initiate accelerometer updates, ensuring that they are processed on the main thread by passing in the main operation queue. Within the closure associated with this function, we safely unwrap the accelerometer data and print out its X, Y, and Z acceleration values. This setup enables our application to dynamically adjust to motion changes as the user tilts or moves their device, highlighting the distinctive capabilities of Core Motion that cannot be mirrored in the simulator. Now let's take a look at how to observe your application's behavior when it enters the background. The code implements an observer method that triggers every time the app transitions to the background state. In this snippet, we override the application.enterBackground function from the UI application delegate. This specific method is a part of the app lifecycle, called automatically by the system when the app is no longer active and is sent to the background. Within this method, we include a simple print statement that logs a message to the console indicating that the app has entered the background state. This action not only helps in confirming that the function is being executed as expected, but it also allows us to debug and analyze what happens during state transitions. By implementing this observer, you can systematically evaluate how your app behaves when faced with interruptions, such as incoming calls or notifications, enhancing the app's reliability. This will be crucial as you test your app in real-world scenarios to ensure data persistence and user experience remain intact when users switch back to your app. In conclusion, effectively running your app on an iOS device will smooth out any bumps you may encounter during the development phase. From hands-on performance assessments to making the most of the hardware features at your disposal, a real device provides an irreplaceable testing environment. By understanding how to connect your device, manage provisioning profiles, optimize performance with instruments, and handle different scenarios, you can maximize the quality of your application significantly. As you proceed with your iOS development journey, remember to keep testing on your devices. It's an influential practice that leads to better apps, happier users, and ultimately, a more successful offering on the App Store. Happy coding! To connect your iOS device to Xcode and run your applications, you'll need to navigate through several essential steps. This process is crucial because running your app on an actual device provides a more authentic representation of how users will experience your app compared to using the simulator. Devices come with hardware features that cannot be simulated, making real device testing indispensable. So far, we learned about the critical steps to run iOS applications on actual devices, emphasizing the importance of connecting your device to Xcode and ensuring developer mode and provisioning profiles are properly configured. We discussed how real device testing allows for a more accurate assessment of app performance, access to hardware features, and the debugging process. Now we will dive into the specifics of connecting an iOS device to Xcode, troubleshooting common issues, and ensuring that all configurations are correct for smooth development. Before diving into the connection process, it's important to prepare your iOS device. Make sure your device is updated to the latest version of iOS that is compatible with your version of Xcode. To check for any available updates, head over to Settings General Software Update on your iOS device. Keeping your device updated ensures compatibility and helps you take advantage of the latest features and security improvements. Once you're all set with updates, the first step is to trust your computer on the iOS device itself. When you connect your device to your Mac via USB, a prompt may appear on your device asking if you want to trust this computer. Tap Trust and enter your device passcode if prompted. This step is vital as it establishes a secure connection between your device and Xcode. Now let's look at how to configure Xcode to recognize your device. Open Xcode and navigate to the top menu bar. Click on Window, then select Devices and Simulators. In the Devices tab, your connected iOS device should be listed. If your device does not appear, double-check your cable connection or try a different USB port. In some cases, restarting both Xcode and your iOS device can solve connection issues. Now that you've verified your device is recognized by Xcode, it's time to enable developer mode. If you have an iOS device running iOS 16 or later, follow these steps. On your device, open the Settings app, go to Privacy and Security, and enable developer mode. This is important because it allows your device to run apps that you develop and can significantly streamline your development process. The bar chart titled Key Steps to Connect iOS Device to Xcode presents 6 discrete steps on the x-axis and their assigned importance as percentages on the y-axis, with the 6 values summing to 100%. The chart ranks Trust Computer as the single most important step at 25%, followed by 2 steps tied at 20% each: Update iOS and Deploy App. Enable Developer Mode appears at a mid-level importance of 15%, while Manage Provisioning Profiles and Debugging are each shown at 10%. The data labels above each bar make the exact percentages explicit, allowing a clear comparison across steps. From this distribution, we can conclude that initial trust and readiness actions, updating iOS and trusting the computer, together comprise the largest portion of the importance, with deployment itself equally prioritized. Provisioning and debugging, while essential, are assigned lower individual weights. This visualization therefore emphasizes prioritizing secure device trust and platform readiness before focusing on provisioning details and runtime debugging. With developer mode enabled, the next step involves configuring provisioning profiles. Provisioning profiles are essential as they authorize your app to run on physical devices. You can manage these in Xcode by going to Preferences, Accounts, and adding your Apple ID if you haven't already. Once added, make sure you select your Apple ID and manage the development certificates and provisioning profiles. To create a provisioning profile, navigate to your project settings in Xcode. Under the Signing and Capabilities tab, enable Automatically Manage Signing. This allows Xcode to automatically create or download the necessary profiles for you. Just ensure that your team is selected and verify that the appropriate signing certificate is active. If you set everything up correctly, Xcode will retrieve all the necessary provisioning profiles for the associated devices. Now let's deploy your app to the iOS device. Select your device from the Device Selection drop-down menu located at the top of the Xcode window. Build your app by clicking on the Play button or using the shortcut Command plus R. If everything is correctly set up, your app should now be installed and launched on your iOS device. This is where the magic really starts to happen, as you can interact with your app in real time, test various functionalities, and engage with hardware features such as the camera or GPS. While your app runs on the device, you will want to keep an eye on debugging information. Xcode provides a console that shows logs, errors, and other essential messages. If you encounter any crashes or issues, the console can help you identify the root cause. Now let's implement the following code that will help us track a score in our application. We begin by initializing a variable named score with a value of 0. This variable serves as a counter that will be updated as certain interactions occur within the app. Next, we use the statement score plus equals 10, which increments the score by 10. This is a crucial step, as it allows us to increase the score in response to user actions, such as completing a task or achieving a milestone within the app. Setting a breakpoint on this line of code is particularly useful when debugging. It allows us to pause the execution right before the score is updated. By doing this, we can inspect the current value of score to ensure that it is as expected before any changes occur. Finally, using the print statement, we display the current score in the console. This provides immediate feedback during development, enabling us to verify that our score updates are working correctly. By effectively employing breakpoints and debugging tools, we guarantee the logic behind score management is functioning as intended, laying a solid foundation for our app's gameplay or functionality. Sometimes, testing an iOS app involves scenarios that can cause interruptions, such as incoming calls or notifications. Real devices allow you to witness how your app behaves under these circumstances, providing valuable insights into user experience. Make sure to test these edge cases and note how your application responds. Using instruments is a tool within Xcode that further aids in performance tracking. Instruments provides you with detailed statistics about memory usage, CPU usage, and more while your app is running. To use instruments from Xcode, choose Product Profile, which will launch instruments. Select the relevant profiling template based on what you want to analyze. For instance, if you are focusing on memory issues, select the Allocations template to monitor memory allocations during your app's runtime. Let's wrap up with a few troubleshooting tips. If you experience connectivity issues, verify your USB cable and port. If your device fails to appear in Xcode, try restarting both Xcode and your device. Sometimes a simple reboot can solve persistent issues. Additionally, ensure you have allowed connections in your device's settings and check for any pending iOS updates that might hinder performance. Remember, building apps for iOS and running them on actual devices can be full of challenges, but each step enhances your development skills and ultimately strengthens the app quality. Embrace these experiences as part of your learning journey. The goal is to make sure your app not only works on a simulator, but also shines on real devices. In summary, connecting your iOS device to Xcode is not just a matter of plugging it in. It's a multifaceted process that ensures you can develop, debug, and optimize your app efficiently. By following the steps we've covered, from updating your device, enabling developer mode, managing provisioning profiles, and utilizing Xcode debugging tools, you enable your app to leverage the full capabilities of iOS devices. So to recap, we explored the vital steps of connecting to an iOS device, configuring Xcode, troubleshooting common issues, and ensuring robust debugging practices. This knowledge serves as a foundation, enhancing the quality and performance of your apps on actual hardware. Now get out there, connect your device, and start building fantastic apps. To successfully run your app on an iOS device, you'll need to understand several critical steps that ensure seamless integration between your application and the device. Testing on an actual device provides you with the most accurate representation of app performance, which is essential for debugging and optimizing user experience. So far, we learned the essential steps for connecting an iOS device to Xcode, including updating the device, enabling developer mode, and managing provisioning profiles. We emphasized the importance of real device testing for accurate app performance and debugging. Additionally, we discussed troubleshooting common issues to streamline the development process. This foundational knowledge is crucial for optimizing app capabilities on actual iOS devices. Now we will cover how to build, run, and debug your app effectively on an iOS device, exploring various code examples to illustrate the processes. The displayed bar chart titled Key Steps for Running an App on an iOS Device maps each discrete step on the horizontal axis to an integer importance level from 1 to 5 on the vertical axis, with numeric labels placed directly above each bar for clarity. From the date as shown, Connect Device and Run on Device receive the maximum importance rating of 5, indicating they are the highest priority actions in the workflow. A middle tier of importance, value 4, includes Update Device, Enable Developer Mode, and Debugging, showing these are significant tasks that directly affect successful deployment and troubleshooting. Lower importance values 3 are assigned to manage provisioning profiles and handle permissions, suggesting these are necessary but comparatively less critical in the immediate run and test cycle. The vertical grid lines and y-axis scale allow straightforward comparison of these importance levels, and the categorical ordering along the x-axis groups the distinct steps so it is easy to see which phases demand the most immediate attention. The clear pattern, high importance for device connection and execution, moderate for setup and debugging, and lower for administrative tasks, supports the conclusion that developers should prioritize establishing a reliable connection and executing on the device, while allocating sufficient but proportionally less time to provisioning and permission management during initial test cycles. Now let's see how we can implement the API configuration for our application. The code begins by creating an instance of API configuration, which is essential for setting up communication with the external service we'll be using. By initializing this object, we are setting the foundational parameters required for API interaction. Next, we assign the API key property with the value YourAPI-Key. This key is crucial since it's how our application authenticates requests to the API, ensuring that we have the necessary permissions to access the data or services provided. We also set the base URL property to the specified endpoint https://API yourservice.com. This URL serves as the base for all API requests made from our app, effectively directing traffic to the correct server. It's important to ensure that this URL matches the service we intend to use, as any discrepancies could lead to failed requests or unexpected responses. By configuring these parameters before building the app, we ensure that all linked components can function correctly and interact seamlessly with the external services, ultimately enhancing our app's capabilities and user experience. Now let's take a look at how we can handle user interactions in our app by implementing a button action. The provided code defines a function called button_tapped, which is triggered when a user taps a button in the interface. Within this function, we include a simple print statement that outputs button was tapped to the console. This serves as a basic confirmation that the button interaction is functioning as expected. Importantly, we can set a breakpoint at this line in Xcode, which allows us to pause execution of the app when the button is pressed. By doing this, we can step through the code line by line, inspecting variables and the overall flow to ensure everything operates smoothly. Using breakpoints is an essential debugging technique that helps isolate issues in our code, making it easier to determine if the button action is processed correctly and to assess any subsequent effects it may have on the application. This approach is invaluable as we refine our user experience and enhance functionality based on real-time feedback from our app's interactions. Next, we will write the following code to log memory usage within our app, a vital step in assessing performance. The code begins by calling a function named reportMemoryUsage, which is responsible for gathering memory metrics. This function isn't built in, it needs to be implemented separately, potentially leveraging the TaskInfo API for accurate reporting of memory data in a Swift environment. Once reportMemoryUsage returns the relevant memory metrics, the code stores this information in a variable named memoryUsage. By capturing this value, we gain insight into how much memory our app is utilizing at that point in execution. Finally, the code prints the current memory usage in megabytes to the console, providing developers with a clear understanding of the app's resource consumption. This is particularly useful when optimizing the app for performance, as high memory usage may indicate possible leaks or inefficiencies that need to be addressed. Monitoring memory effectively ensures a smoother user experience and helps in maintaining the app's stability on an iOS device. Now let's see how we can handle camera access in our app by implementing the necessary permissions and request processes. First, we need to add a descriptive entry to the info.plist file, specifically including the NS camera usage description key. This key provides users with a clear understanding of why the app needs camera access, enhancing their trust and willingness to grant permission. In our case, we describe that our app requires access to the camera for capturing photos. Next, let's implement the function to request this camera access within our code. By importing the AV Foundation framework, we gain access to critical media functionalities, including the ability to query and request access to camera features. In the request camera access function, we use AV Capture Device Request Access for video, which presents a system prompt to the user asking for their permission to access the camera. The closure evaluates the user's response, allowing us to handle both outcomes gracefully. If access is granted, we can proceed with functionalities that rely on the camera. If denied, we notify the user appropriately. This structured request process is essential for ensuring our application adheres to user privacy standards and maintains a positive user experience. Next, we will look at how to handle permissions for location services in your app. First, it's essential to include the necessary key in your info.plist, which provides a description to users explaining why your app needs their location. The NS location when in use usage description key allows you to specify that the app requires access to the user's location to deliver location-based services effectively. Now let's implement the Location Manager class to manage location services. This class inherits from NS object and conforms to CL Location Manager delegate. Within it, we define an instance of CL Location Manager. The method startLocationServices is crucial as it sets the delegate and requests permission for location access from the user. It's important to call request-when-in-use authorization to ensure the app can access the location when it is in use. Once permission is granted, the app begins fetching location updates with start updating location. Additionally, the delegate method Location Manager did update locations handles location update callbacks. Here we can retrieve the most recent location and print its latitude and longitude. This setup is vital for delivering accurate location data in your app, but remember, testing on an actual device is necessary since the simulator cannot provide reliable location services. Now let's see how we can implement the necessary configurations for handling push notifications. The first step involves modified entries in the application's info.plist. Here, we declare that our app will support background capabilities, specifically for fetching data and handling remote notifications. This declaration ensures that your app can receive notifications even when it is not actively running, thereby enhancing user engagement. Next, we will write a function to request notification permissions from the user. By utilizing the UN User Notification Center, this function prompts users to authorize notifications, specifying the types of alerts they would like to receive, such as banners, badge updates, or sounds. The granted permission is crucial as it determines whether notifications will reach the user or not. If permission is granted, you can implement further features like scheduling local notifications or responding to incoming remote notifications. With the proper configuration and permission handling, your app will be well equipped to deliver a seamless notification experience, an essential element for increasing user interaction and retention. As we wrap up this segment, we've established not only how to build and run an app on an iOS device, but also touched upon handling essential functionalities like permissions for the camera, location services, and notifications. These features contribute significantly to user experience and app performance. In our likely future discussions, we will dive deeper into optimizations and best practices for using third-party libraries. This knowledge is vital for harnessing the extended capabilities of iOS while ensuring your application operates efficiently across different devices. Overall, remember that testing on an actual device reveals the real performance characteristics of your app that a simulator cannot provide. So take the plunge and get your hands on your iOS device, get testing, improve user interactions, and let your app reach its full potential. In this video, we will dive into the comprehensive guide for developing iOS applications. Today, we're going to cover how to effectively set up Xcode on your Mac, explore its user interface, and create your very first iOS app. We'll also understand how to run your app on a simulator and connect to a physical iOS device for testing. So far, we learned the critical steps to build and run an iOS app on a physical device. emphasizing the importance of real device testing and proper configuration within Xcode. We covered setting the target device, managing app signing, and troubleshooting errors during the run process. Additionally, we discussed handling permissions for features like the camera and location services, which are essential for a quality user experience. Now we will talk about downloading and installing Xcode, getting familiar with the interface, and creating a simple app. Let's start with downloading and installing Xcode. First, you'll want to head over to the Mac App Store. Simply open the App Store on your Mac and use the search bar to type in Xcode. It's usually the first result that pops up. Once you find it, click the Get button, which will change to Install once the download is initiated. Xcode is quite a hefty application, so grab a cup of coffee while it installs. The displayed pie chart titled Understanding Key Steps in iOS Development breaks down the relative emphasis across 5 core activities: Xcode setup 25%, simulator usage 20%, physical device testing 30%, App Store submission 15%, and testing 10%. The most prominent slice is physical device testing at 30%, which indicates that real device verification is considered the single largest focus area. This supports the lesson's emphasis on testing apps on actual hardware to validate touch interactions, performance, and hardware integrations. Combined, the simulator usage 20%, physical device testing 30%, and testing 10% constitute 60% of the chart, highlighting that testing, both in simulator and on devices plus general test practices, should consume the majority of development effort. Xcode setup at 25% appears as the next significant portion, underscoring the need to invest time in properly configuring your development environment and signing settings early on. App Store submission at 15% shows a smaller but non-negligible slice, reminding us that preparing for distribution, provisioning profiles, metadata, and submission steps requires dedicated attention late in the development cycle. From these proportions, we can conclude a practical workflow: prioritize environment setup, allocate substantial time to both simulator and device testing, and ensure you reserve effort for a careful App Store submission process. After the installation, you can find Xcode in your Applications folder. The first time you launch it, Xcode may take a moment to set up its components. Once that's done, you'll be greeted by the welcome window. Here you can choose to create a new project, open an existing one, or check out the latest iOS documentation. It's important to familiarize yourself with this window because it sets the stage for your development journey. The Xcode interface consists of several key components: the navigator, the editor area, the utility area, and the debug area. Let's break these down further so you'll know exactly what you're looking at. Just on the left, you have the navigator, which helps you keep track of your project files, issues, breakpoints, and test results all in one place. The editor area is the heart of Xcode, where you'll write your code, design your user interface, and manage your resources. In the utility area, you can find useful information about selected items, as well as access to libraries that contain UI elements like buttons and labels. Finally, the debug area is where you'll see your app's output when you run it, making it a crucial tool for troubleshooting issues. Understanding these components is vital for smooth navigation as you develop your iOS applications. Now let's create our first iOS app. Back on the welcome screen, select Create a new Xcode project. When prompted, choose App under the iOS section. Click Next, and you'll be asked to enter some basic information about your app. In the product name field, you can name your app. For our example, let's call it Hello World. Make sure the team, organization name, and organization identifier are filled in appropriately. The bundle identifier is a unique identifier for your app, typically formatted as a reverse domain name like your company, Hello World. Under Interface, you can pick Storyboard to use the drag-and-drop interface. For language, ensure you select Swift, as that's the focus of our course. Finally, be sure to check Use Core Data and include tests if you would like to add testing capabilities to your app. When you've got all that set, click Next, choose a location to save your project, and hit Create. Once your project opens, take a moment to explore the files created for you. By default, Xcode generates AppDelegate Swift, SceneDelegate Swift, and ContentView Swift. These files are the backbone of your app's lifecycle and UI management. AppDelegate handles app-wide events like launches and background transitions, while SceneDelegate manages the app's visible UI aspects. Let's dive into coding some basic functionality now. We will start by customizing our ContentView Swift file. Inside this file, you'll notice a struct named Content View, which conforms to the View protocol. The body property of this struct is where you define what your user interface will look like. Now let's take a look at a simple piece of code that will help us display a label on the screen with the text, "Hello, World." This is a fundamental step in iOS app development that showcases how user interfaces are structured in SwiftUI. First, we start by importing the SwiftUI framework, which is essential for building our app's user interface in a declarative way. Within this framework, we define a structure called Content View that conforms to the View protocol, a requirement for any SwiftUI view. Inside this structure, we have the body property, where we describe what our user interface looks like. Here, we utilize the text view to display our desired text. To enhance the visual appeal, we apply a large title font to the text and add padding around it, ensuring it looks good and is spaced nicely on the screen. These small yet impactful details contribute significantly to the overall user experience. This block of code is the foundation of our app, and running it will render our first visual output in the simulator, marking an exciting milestone in our development journey. Xcode compiles your project, and soon enough the simulator will launch, showing your app in action. You should see the "Hello, World" text displayed in the middle of the screen, presented in a beautiful font. Congratulations, you have just created and run your first iOS application, and it wasn't so tough, was it? Now that you have a grasp on running a simple app, let's also connect a physical iOS device to Xcode. To run your app on an actual device, connect it via USB and make sure your device is unlocked. Open Xcode and select your device from the Scheme dropdown. Essentially, Xcode will recognize the connected device if you have all the necessary settings in place. Namely, you need to have a valid Apple developer account, whether free or paid. If prompted, accept any helpful permission requests on your iOS device to trust the computer. You may also need to configure your personal team for signing, which can also be done in the Xcode project settings under the Signing and Capabilities tab. Once everything is set, hit that play button again, and your app should launch on your physical iOS device. The experience on an actual device can significantly differ from the simulator. For instance, interaction feels more natural, and you can test things like tapping, swiping, and other touch gestures directly. Testing on a real device is crucial for a lot of reasons, including performance assessments, checking camera functionality, location services, and hardware integrations. So always be sure to conduct tests on physical devices whenever possible. As our session nears the end, let's briefly recap. We have walked through downloading and installing Xcode, explored its user interface components, created our first iOS app, and even ran it on a physical device. Remember that learning to develop iOS applications is a journey, and each step builds a crucial skill that leads you to more complex functionalities and designs. In the next steps, we will delve deeper into optimizations and best practices for leveraging third-party libraries, ensuring that your apps not only function well, but also offer a richer user experience. Get ready to enhance your development skills further. Keep practicing, embrace the learning curve, and soon you'll be wielding Swift like a seasoned developer. Happy coding, everyone. In this final section, we will do a project challenge to apply what we have learned so far. Your task is to develop a fully functional journal application using Swift and SwiftUI, where you will demonstrate your understanding of Swift syntax, the MVC design pattern, and the abilities to create a user-friendly interface with Xcode and SwiftUI components. The app will feature a main screen that lists all journal entries, with options to add, view, edit, and manage each entry while allowing users to input a title, body, rating, and an optional image. You'll need to implement CRUD operations while ensuring smooth navigation throughout the app. As you embark on this challenge, remember to focus on code quality, organization, and clarity to create a polished final product. Don't forget to check the GitHub repository linked in the description for the final project details and resources. Good luck and enjoy building your app.